All right, so I guess we can slowly get started. So welcome everybody to our workshop. So I think it's the first time we are organizing workshops for CORE, which is actually a very exciting setup this year. First of all, I would just like to know if the guys that are online, if audio and share like screen sharing is fine. So can you just probably in the chat just give me a just some feedback? Just to double check. All right, seems fine. Okay, great. So good morning, everyone. So my name is Leonel. I'm one of the co-organizers of the workshop on geometry, physics, and human knowledge as inductive bias in robot learning. And just to get started, I would like just to share with you like why we wanted to kind of organize a workshop that was focused on these three topics. And the idea was basically that we have seen like a huge development in terms of end-to-end learning frameworks, right, that are being applied in different kind of robotic domains. But I think it's clear by now that we are kind of disregarding a lot of information that we had already before, like for different kind of problems. And now it seems that more and more researchers are trying to actually to include different kind of inductive bias in robot learning frameworks in order to ensure like a more robot behavior in favor of data efficiency or safety, for example. So even though there are like different ways to include or to induce some inductive bias in robot learning applications, we wanted to focus on three different types of inductive bias, so namely geometry, physics, and human knowledge. And that's actually the focus of the talk that we're going to have today. So, and the idea is to try to actually answer probably some of the questions that we have here in the slide, like which kind of priors we could actually use in different kind of robot learning applications. How can these inductive bias be represented according to which kind of approximators we may be using, and so on and so forth. And for that, basically, we get a very cool organizing committee. So I just want to, for sure, acknowledge the hard work of Fabian and Alexander, who are PhD students in KIT and Tübingen, and that did basically all the work to make this happen. But of course, we also have very nice co-organizers as well, like Nadia, that is with us here in New Zealand, David, Angela, Avid, and Andy. So all of them gave us really nice feedback regarding how to set up our workshop, and also give us very nice inputs as well regarding how to actually steer this. We do have some companies involved, and this is actually because we want as well to analyze how all the domain knowledge that engineers may have in different kind of industrial processes may be used or leveraged as inductive bias when it comes to take robot learning in real applications. And of course, they sponsor our organization, so we should definitely be grateful for that. And during the organization, we really try to strive for diversity, the diversity at different levels. And I think that I can speak on behalf of the organizers. We are really proud of this because we managed to bring like researchers working already like as professors, but also very young researchers as well, from all different parts of the world, different kind of organizations. So we have speakers from companies, as well as research institutes and universities. And I think this is a very nice setup to actually bring different kind of views on how we can understand inductive bias in robot learning. So we're gonna have a first bunch of speakers, starting with Noémie Jacquier, then Shuren Zong and Byojim Kim. And after that, we're gonna have a small coffee break. Of course, all that is synced with the full organization of CORE. So you're gonna meet all the guys, of course, during the coffee break that are also attending the other workshops. After that, we have a second set of talks given by Michal Luta, Francisca Maya, and Kelsey Allen. And after that, we're gonna go for the lunch break and the CORE opening session. So basically all this, as you may know, is synced with the CORE program. And when we're gonna close with the third session that is opened by Joseph Lim, then we have Deepak Phatak and then finally Anki Dragon. So we apologize in advance because we actually had to do some changes in the schedule kind of last minute to be able to come with some, with some solutions here due to some different restrictions. Originally, we have planned for like an hour panel discussion, but due to these changes, we basically go for half an hour. Still, we believe that we can actually get a fruitful discussion with the speakers and with the audience as well. That should be it for today. So I guess we are kind of on time to start the first session. So I'm going to hand over to Nadia Figueroa, who's going to chair the first session. And then that's it. So thank you, everyone.
Hi, everyone. Thank you so much for attending here in person and also online. So I'm going to introduce our first speaker, Noemi Jacquia. She is a postdoctoral researcher at the Karlsruhe Institute of Technology, KIT. Before that, she was a PhD student affiliated to EPFL and working at the EDIAP Research Institute. She obtained a bachelor in microengineering and a master in robotics and autonomous systems and a minor in computational neurosciences from EPFL. Noemi, the floor is yours. I think I need to unmute you, or you can do it yourself. Yeah.
I think I can do it myself.
Okay, perfect.
But you have to allow me to share the screen.
Oh, yeah. How can we do that? Oh, so I stop share. Yeah.
Yeah,
Okay,
now it seems to be fine. Let me try.
Yeah.
Now you should see it, right?
Yes, but I think, how can we do it so that we only see her? Not everyone else. Maybe. Let's see, remove pin. Oops. Okay, there. That's it. Okay, go ahead.
Good, thank you. Okay, thank you very much for the kind introduction and also for the invitation to this really cool workshop. So my title of today is From Data Structure, Physics and Human Knowledge, a Manifold of Robotic Geometries. So my goal here is to show you basically how we can introduce inductive bias in robot learning by considering different robotics geometry. Okay. So can you actually see the entire screen or?
Yes.
Yes, okay. Okay, so basically, when we consider robot manipulation, this involves complex skills which can be learned by robot in different ways. So one popular approach is learning from demonstration, where we have a human that demonstrates a skill to a robot and the robot learns a model and imitates the skill. And the goal here is that the model encompasses the important requirements of the demonstration. And in this case, in our scoring example, is the fact that the end effector pose needs to be precise and that the robot needs to be compliant or stiff in different directions. Moreover, we would like our robot to be able to cope with uncertainty and to also generalize to unseen situation. So it means that we may need to adapt our initially learned policy to a new situation. So to do so, we have several options. So we can adapt via trial and errors, and we can also adapt via interactions with humans. So on top of that, we would like actually our robots to be able to continuously learn and hopefully in real time. So it means that we would like to be able to learn from few demonstrations, to have data efficient skill learning and adaptation, and to adapt via only few interactions. And one way to actually, I think, reach this goal is actually to introduce inductive bias in our algorithm. So as I showed here, several of our data actually have non-Euclidean geometries. So I talked here about orientations, which are usually represented as unit norm quaternions, and about stiffness ellipsoids, which are symmetric positive definite matrices. So it means that we have an intrinsic geometry for our search space. And I think we can use this geometry as a domain knowledge or as inductive bias to guide the robot learning process and then improve the performance and the efficiency of our algorithm. So my goal of today is to show you how we can introduce inductive bias and view it through the lens of geometry. So I want to consider this from three different perspectives. So the first perspective is the one that I just presented in my example. So I want to consider the intrinsic geometry of the data, so to consider the data structure and to incorporate this in our algorithm. For a second perspective, I would like to see geometry that can arise from physics, and I would like to show that geometry naturally arises from robot dynamics and can be used to generate and transfer energy efficient motion and transfer motions from human to robot. And for a third perspective, I would like to see inductive bias, this time from human knowledge, and I will consider human knowledge in the form of robotics taxonomies, and I would like to show how such inductive bias can be incorporated in latent representation based on the geometry that we give to this latent representation. So just here a short disclaimer. So due to time constraint, I will actually just provide an overview of those three topics. And if you want to dig deeper, I will provide references at the end of the talk. So let me start with inductive bias as geometry from data structure. So as I told you, we have a lot of robotic parameters that are relevant and that feature a variety of geometries. So among those, we have the Euclidean space for position, force, and torques. We have the sphere for orientation and directional data. We have symmetric positive definite matrices for control gains, inertia matrices, manipulable ellipsoids. We also have the torus for joint configuration and periodic functions, and the special orthogonal group for orientation and as a building block. So the goal here will be to actually design learning algorithm that takes into account all those geometries. So the common point between the mathematical spaces that I just showed is that all of them are so-called Riemannian manifolds. So Riemannian geometry is really the backbone of all the approaches that I'm presenting later. So I will just take here 1 minute to introduce the basics of it. So a Riemannian manifold is a curved mathematical space which locally looks Euclidean. What that means is that you can, for each neighborhood on the manifold, design a one-to-one function towards a Euclidean space. This allows us to define the notion of tangent space, which are really useful. So there are spaces that are tangent to the manifold at a point X, and those spaces are Euclidean, so we can do usual calculus on them. On those tangent space, we can define the notion of Riemannian metric, which is basically an inner product that is defined on the tangent space. And this Riemannian metric varies smoothly on the manifold. And it's actually very important because this Riemannian metric fully captures the entire intrinsic geometry of the manifold. So it allows us to do everything we need on the manifold. So as we saw, it defines this notion of inner product, but it also defines the notion of norms and also the notion of length of the curves and of distances between points. And finally, it also allows us to generalize straight lines to those curved space. And these generalizations are geodesics. So those are minimum energy and minimum length curve, and I will use them later in the talk. And finally, we can define maps between the tangent space and the manifold, which allows us to move points from the manifold to the tangent space, do Euclidean calculus there, and then map the result back. So using then this Riemannian geometry framework, I would like to show you how we can actually introduce inductive bias in one specific robot learning algorithm, which is Bayesian optimization. So Bayesian optimization is popular, is a widely used method for data efficient skill learning and adaptation. So Bayesian optimization aims at globally minimizing a function, and this function doesn't have a simple closed form solution, but can be actually observed in every point of the space. So Bayesian optimization works in 2 steps. So the first step, we model the objective function, typically with the Gaussian process, prior, and then we can obtain a posterior for our function in the full space, which means a means and a quantification of uncertainty about how certain we are about our function. So based on this posterior, we can then define an acquisition function, which trade-off between exploration and exploitation in order to evaluate the utility of candidate points. We can then maximize this acquisition function, and that gives us where we want to query our next point. And by iteratively repeating those 2 steps, at the end of the day, we usually obtain the global minimizer of our function. So now what I would like to show you is actually what we need to change in this Bayesian optimization algorithm when we want to consider data that lie intrinsically on Riemannian manifolds. So for this, there are 2 modifications that we have to do. First, we have to consider that the Gaussian process is completely specified by the mean and the kernel. And the kernel usually in Euclidean space is defined as a function of the Euclidean distance. And as we have seen, the Euclidean distance on Riemannian manifold doesn't really make sense. So if you want to measure the distance between 2 points on the sphere, you shouldn't take the distance that is actually crossing the sphere. So what we propose to do is to use Riemannian formulation for the kernels, which are based on the Riemannian distance. I will give you here an example. So this is the kernel for the circle, and you see that this kernel is expressed as an infinite sum of terms, of exponential terms, and each of those exponential terms actually contains a notion of distance between the 2 points on the manifold. So each of them gives you how many loops you actually do to link your 2 points on the circle. So this is for the first step. The second point that we have to consider is that the quality of the next query point depends on the optimization of the acquisition function. So usually we optimize the acquisition function in a Euclidean space, and if we are on Riemann manifolds, we have actually to use a constraint optimization. So what we can do is instead here to use a Riemannian optimization framework, which then frames the optimization problem as an unconstrained optimization, which is guaranteed to stay on the manifold, and it's usually more efficient optimizations. So this is based on the computation of gradients, which are on the tangent space, and then on the use of the exponential map to project the gradient back onto the manifold and iterate then the optimization steps. So now that we have our Bayesian optimization on Riemannian manifolds that is ready, let me just show you one example of results. So here we consider a task-compatible manipulability optimization scenario, and this is a common problem in robotics where usual solutions do not exploit the geometry of manipulability ellipsoids. So in the problem here, we consider a robot that is tracking a line down with a velocity controller, and this robot is also tracking a desired manipulability ellipsoid. And the goal here is that we would like to optimize the desired manipulability that we are tracking so that the robot can smoothly and fastly follow the trajectory down the line. So basically, our cost function is that we would like to find the desired manipulability so that the end effector jerk is minimized, so that the manipulability, the desired manipulability is aligned with the direction of motion, and so that the robot is actually able to track the manipulability that we give it. So here you will see some of the iteration of the Bayesian optimization algorithm. So you have the desired manipulability here in green. This is what we are optimizing. And the one that the robot, the current manipulability of the robot is in purple. So you see that at the beginning, you have the cost on the right. So the Bayesian optimization slowly decreases the cost. The manipulability are slowly changing. They are aligning a bit more with the axis, and they are getting a bit smaller so that the robot can actually track them along the trajectory. And then I will show you now the results after 100 iteration. So this is the best desired manipulability that we obtain after 100 iteration. So you see that we have a smooth trajectory, so a low end effector jerk. We are able to track the desired manipulability, and the manipulability is aligned with the direction of motion. So what is interesting here is actually to check the convergence statistics and to compare the performance of the Riemannian methods, which is here the orange curve that you can see here, with the performance of Euclidean methods, which are the curves that are here up. And you can see that basically introducing inductive bias in the form of geometry allows us to have an algorithm that converges faster, that finds better solution, and that has at the end of the day a lower solution variance. So let me wrap up for this part. So basically what I wanted to show you here is that if we introduce geometry from data structure as inductive bias, we have faster convergence, better accuracy, lower solution variance for our algorithm. And importantly, we also have mathematical correctness in how we deal with our data, which I think is still important. So let me now switch to the second part and the second perspective I wanted to give, which is how to introduce inductive bias as geometry from physics. So as a motivation, let's consider human movements. So humans are naturally able to generate skillful motions. They efficiently plan optimal trajectories while coping with the redundancy and the high dimensionality of their configuration space. The configuration space of robots is also redundant and high dimensional, especially the ones of humanoids. So to cope basically with this redundancy and high dimensionality and to produce dexterous and energy efficient motion, roboticists have taken inspiration from neuroscience and borrowed the concept of synergies, which are coherent co-activations of motor signals. So synergies have been usually extracted using linear approaches such as principal component analysis, but those approaches actually disregard the intrinsic nonlinearity of the robot's configuration space. Other approaches, more recent, have been based on latent variable models. And here, the resulting synergies are nonlinear, but the resulting synergy space remains physically meaningless. So what we would like to have at the end of the day is synergies that are actually accounting for the robot dynamics, for the robot dynamic properties. So to do so, we can actually see the space of joint configuration through the lens of geometry. And we can define it as a Riemannian manifold. So remember, I told you that as a Riemannian manifold, basically you need to define a Riemannian metric, and this provides you with the full intrinsic geometry of the manifold. So here I will consider the space of joint angles, and I will endow the space with the so-called kinetic energy metric, in which basically the Riemannian metric is equal to the mass inertia matrix of the system. So we then obtain the so-called robot configuration space manifold, which is a manifold in which each point is a robot joint configuration. And basically now if you follow trajectories on this manifold, we obtain trajectories of robot joint configuration. So there is a class of trajectories which is especially important and interesting is when we follow minimum energy and minimum length curve on the manifold. So when we follow geodesics, which I introduced previously. So now if we want to have a look at how those geodesics look like, we can have a look at the commonly called geodesic equation, which I give you here. So you can see that this geodesic equation only depends on the metric, so on the mass inertia matrix, and on the joint acceleration and joint velocity. Now, if we can take a closer look at this geodesic equation, this should actually become familiar to you. So checking the first term, this is actually just equivalent to the multiplication of the mass inertia matrix times the joint acceleration. And then taking a look at the second term, you can actually do the math. This just corresponds to the influence of CoRL forces. So basically what that means is that the geodesic equation corresponds to the classical dynamic equation of motion, simply in the case where we don't have any external forces. So we don't have gravity and we don't have external torques. And this is actually very interesting because it means that if you simply follow geodesics on the configuration space manifold, you actually obtain trajectories which corresponds to passive trajectories of the system. So geodesics correspond to those passive and minimum energy trajectories of the robot. So you directly take into account the dynamics. So we can exploit this, for example, in human motion analysis, because you can also consider the human configuration space as a Riemannian manifold whose metric is the mass inertia matrix. So a hypothesis that have been made often in the literature is that human movements follow minimum effort path. And now if you translate that in the language of Riemannian geometry, you can simply say that human movements follow geodesics in the configuration space manifolds. And this hypothesis has been validated several times in literature, for example, here by Bies and colleagues who analyzed motions of the human arm viewed as an arm with 4 degrees of freedom. And basically, you can see here, this is the motion of the hand in the XY space. And the measured one is in black here. And the one that is reproduced following geodesic is the red one. And it's the one that matches best the measured motion. This has been then extended by Nelson and colleagues, and they proposed the geodesic synergy hypothesis. And then we can make actually one step further and say that complex human movements can actually be modeled as sequences of geodesic synergies. So to verify this hypothesis, what we can do when we have a motion and our joint configuration manifolds is first to segment this motion into different geodesics, so into different geodesic synergies. So to do that, what we do is that we just have a look at the joint velocity along our joint trajectories. And we can simply compare the current joint velocity with the one that we observed at the beginning of the motion. And along a geodesic, these velocities should be equal because the velocity stays constant. So basically, at the moment where your initial velocity and your current velocity have an angle that is bigger than a given threshold, you can assume that you're starting a new synergy. And then when you have an entire segmentation, you can then reconstruct the human motion simply by taking the start and the end point of each synergy and drawing a geodesic between the two. And then you compare it with the motion that you measured. So we actually did that for several human motions. So you can see here, this is a ground truth measured motion. And then we tried to reproduce this motion with our Riemannian approach, and we compared also with a Euclidean approach in which we basically consider the human configuration space manifold as a flat Euclidean space. So you will see here the reproduction of the 2 different motions. So maybe here the difference don't seem obvious, but you will see that when I will show you the graphs, actually they start being obvious. So here we first plot actually the trajectory of the hand during the motion, and you can see also it on the plot here on the right side. So the ground truth motion is actually plotted in black, and you can see that it's fully overlapped by the Riemannian motion that is reproduced by our model. And in contrast, you can see that the Euclidean model that is here in blue quite differs from the ground truth motion. We can also have a look at the joint configuration. So here it's the shoulder joint, elbow, and wrist joints. And again, you see that the Riemannian model actually models pretty well the motions of the joints through the trajectories, while the Euclidean models is quite far from the ground truth. So the Riemannian model successfully predicts both hand and joint trajectories. So having shown that human motions can actually be represented as sequences of geodetic synergies, we would like to exploit the same principle to generate energy optimal dynamic robot motion. So we would like to be able to actually transfer human motions to robots so that the main characteristics of the motion are conserved, but the trajectory is adapted so that it's optimal for the robot. It follows geodesics in the robot configuration space. So the idea here is that we propose a transfer approach, which works in 3 steps. So the first step is that we segment the human motion as I showed previously. Then we map the start and the end point of each geodesic from the human task space to the robot task space. And then we link the start and the end point of each synergies by geodesics in the robot configuration space. So here we retargeted the same motion that I showed you before. So you have here the human motion, and you will see how it looks now on our ARMA 6 robot that is now reproducing the motion. So what is important to see here is that basically the characteristics of the motions are preserved, but the robot is executing it in an optimal way according to its own dynamics. So it means that the motion is following the dynamics of the robot, and it's optimal in terms of energy for the robot. So basically we generate optimal and energy minimizing motions for the robot dynamics. And also notice here that the human, we actually use only 7 degrees of freedom of the arm, while we used 8 degrees of freedom of the arm of the robot. So to conclude this part, if you consider inductive bias as geometry that is naturally arising from the dynamics of the robot, we are able to simply generate dynamic motion. We can just follow trajectories on the manifold. Those trajectories are energy minimizing, and they are optimal for the robot that we are considering. So let me now switch to the last part of the talk. So I would like here to view geometry as an inductive bias that is introduced from human knowledge. Namely, here I will focus on robotics taxonomies, which have been provided for a lot of domains in robotics. And in those robotics taxonomies, researchers have actually inputted a lot of relevant domain knowledge. So we have many taxonomies in robotics, for example, for grasping, for manipulation or bimanual manipulation, and also for whole body support poses. So despite the huge domain knowledge that is actually in these taxonomies, the application remains scarce and barely go beyond applications, beyond analysis applications, sorry. So we think that actually this is due to the lack of computational model that are bridging the gap between the taxonomies, so the hierarchical structures of the taxonomies, and their data. So namely, taxonomies are composed of those 2 elements, so the hierarchical structure and then the data. So if we have a look at the hierarchical structure, it's usually represented as a tree or as a graph, and is a structure that is discrete. So taking here the example of the whole body pose taxonomy, the nodes of the graph are actually different support poses, and the support pose is characterized by a number and a type of contact. So for example, here you have the pose that correspond to a single foot contact. Here you have a pose that correspond to a single foot and a single hand contact. And then the edges of the graph are actually the transition between the support poses, which are characterized by a single contact change. So for example, you can transition from 1 foot contact to 1 foot, 1 hand contact, and then to 1 foot, 2 hands contact, but you cannot transition directly from 1 foot to 1 foot, 2 hands contact because you change 2 contacts. So this hierarchical structure as a graph is basically discrete. And on the other hand, we have the data that are associated with our taxonomy. So in this case is joint configurations. And those data are usually high dimensional, heterogeneous, and importantly, continuous. So we basically have a gap between the discrete hierarchical structure and the continuous data that we have associated to the taxonomy. So what we propose to do here is to learn continuous representation of the data that capture their hierarchical taxonomy structure. So in other words, we are proposing to learn latent representations that are representing the data and the taxonomy structure. So it means that when we want to embed such data into a latent space, basically we would like the data that belong to the same node to be grouped together. So here, this is all data that are belonging to the node with 1 foot contact, so they are close together, and we would like them to be in the distance that corresponds to the distance in the taxonomy of another group of data. So it means that here the distance between the group 1 foot and the group 1 foot 1 hand should correspond to the distance here in the taxonomy graph. And it's the same if we add a third group of data. So here we would like that the pink category is actually at the same distance from the orange and the yellow as we have in the graph. And typically it means that when we go from here, the orange to the pink, we have actually to go here through the yellow category because this is how the edge of the graphs are designed. So we can do that if we have only few nodes and only few data. But if you want to embed the entire taxonomy and you consider the Euclidean space, this actually doesn't scale. So if you check here the tree that we have, you can take, for example, those 2 children, and they are very close together, despite the fact that the common parent is very far here. So this actually doesn't apply. The Euclidean space doesn't have enough volume in order to embed our full taxonomy. So that doesn't work. What we can do instead is choose another geometry for our latent space. So here we choose the hyperbolic space, which basically consists of all the points which are here inside this circle. So the hyperbolic space has very interesting properties, namely that the distances in it grow exponentially when moving away far from the origin. What that typically means is that here you can see you have those blackbirds inside the hyperbolic space. So the areas of all the blackbirds is actually the same in the hyperbolic space. So the area of this bird, even if it looks big to us, is the same as the area of the very small bird here in the hyperbolic space. So it means that this hyperbolic space is actually ideal to embed taxonomies. So you can, for example, embed binary tree completely perfectly in the hyperbolic space. And taking again our whole body superposed taxonomy, here if we want to embed the 3 nodes that we have here, when you take the geodesic going from the pink group to the orange group, the geodesic in the hyperbolic space naturally passes very close by to the yellow group. So it means that we have really a structure that looks like the one of the taxonomy. So based on this, we designed the Gaussian process hyperbolic latent variable model. So it means that you have a latent space which is hyperbolic, in which we embed data. And basically, these data are then mapped to the observation space via a Gaussian process. So the observation space now is joint configurations of the human. So this mapping F corresponds to a Gaussian process. And as our latent space is hyperbolic, we have here to consider Riemannian kernels, so Riemannian hyperbolic kernels in the Gaussian process. And the initial distribution of our latent embeddings follows a hyperbolic wrapped Gaussian distribution. And because the embedding lie in the hyperbolic space, we also train them via Riemannian optimization. So this is cool, but if you just go like that, actually, you still don't introduce any notion about the structure of your taxonomy inside your latent space. So to do that, we actually need to add an additional stress loss, which ensures that the distance between embeddings in the latent space are similar to the distances that we observe in the taxonomy. And we also add a back constraint mapping so that the points that are close together in the latent space are also similar in the data space and similar in terms of nodes in the taxonomy. So now having a look at some results for this. So this is the latent embedding that we obtain. And if you compare it with the taxonomy on the right, you can see that the embeddings are grouped and organized according to the taxonomy node. So if we take, for example, this example here, where we take a transition from 1 foot contact to 1 foot 1 hand, and then 1 foot and 2 hands, you see that actually we recover exactly this transition here in the hyperbolic space. And to go from the 1 foot to 1 foot 2 hands, we actually are passing through the 1 foot 1 hand contact. This is basically the embedding that you obtain if you don't put the additional stress loss and the back constraint. So you see that the taxonomy information is not encoded if we don't put this loss. So interestingly, if we compare also with a Euclidean space where the latent space is simply Euclidean, you can see that the structure of the taxonomy is not respected because we don't have enough volume that is available in the Euclidean space. So you see here, for example, the 1 foot class is very close to the 1 foot 2 hands class, which actually shouldn't happen due to the structure of the taxonomy. And here you have also the stress value for the hyperbolic and for the Euclidean model, and you see that the hyperbolic one clearly outperforms the Euclidean one. So what we can do there is, for example, to expand the taxonomy, add new classes, or to encode and symposes, which I'm not going to show here. What I would like to show is actually that we can also generate trajectories based on geodesics in this latent space. So here I'm just generating a geodesic from a point here in the 1 foot class to a point in the 1 foot 2 hands class. And you see that actually at a certain point, we are passing through the 1 foot 1 hand class. So the contacts in the trajectory that we generate actually respect the structure of the taxonomy. So to wrap up with that part, I showed that we can actually introduce inductive bias from human knowledge by designing latent spaces that have the right geometry. So we can then include human knowledge into our latent representations. So to conclude, what I wanted to show you today is that we can introduce geometry-based inductive bias in 3 different manners. So first, from the structure of our data, where we consider the intrinsic geometry of the data in the algorithm. This leads to faster convergence, better accuracy, and lower solution variance. Then, as a second step, I showed you that we can introduce geometric-based inductive bias from physics, where we can consider the Riemannian configuration space manifolds, which directly embeds the dynamics of the robot and allows us to simply generate dynamic motions, which are also energy minimizing trajectories and that are optimal to the robot at the end. And finally, I wanted to show you that we can also introduce inductive bias from human knowledge, where we basically consider the structure of the taxonomy via the choice of latent space geometry. So it allows us to bridge the gap between continuous data and discrete taxonomy structures. So I hope that with that, I managed to convince you that geometry is a powerful and very expressive form of inductive bias for robot learning, and that we may want to use it more often in our algorithm. So with that, thank you for your attention, and I will be happy to take any questions.
Thank you so much, Noemi. Do we have any questions from the attendees in person? On Zoom? I have a question actually, Noemi. So in all of these spaces that you're talking about, specifically in the joint space, you're assuming kind of like a continuous connected torus, but we know that there are constraints, right? Like joint limits, self collisions, or even collisions of the robots, you know, like with the environment. So how do you like, have you thought of considering these type of constraints, maybe like in the metrics or in the kernels? Because that will make the planning or even the learning a little bit more difficult, right? Because that creates kind of like holes, or like it creates kind of like some discrete structure in these smooth spaces. So can you talk a little bit about that?
Yeah, sure. Yes, it's true that, I mean, at the end of the day, when you put as a metric the mass inertia matrix, you implicitly consider this closed torus, but you don't necessarily need to. So even if you have joint limits or that kind of things, they can be embedded. And actually, in the video that I showed with the robots that is reproducing the motion by the human, we actually here added additional metric on top of the mass inertia matrix so that the robot avoids joint limits and self-collision avoidance. So these are the 2 types of metric that we considered on top of it. So it's actually possible, and we can still transfer the motions without much issues.
Okay, cool. Any other questions from the audience? No? Okay, let's give Noemi another round of applause.
Thank you.
Thank you very much. So now we can prepare for our next speaker. You can go. Okay, so our next speaker is Shuran Song. She is an assistant professor in the computer science department at Columbia University, where she directs the Columbia Artificial Intelligence and Robotics Lab. She got her PhD at Princeton University in 2018. During her PhD, she was a visiting researcher at Google Brain Robotics. Her work has won multiple awards, including the Best Systems Paper at CoRL 2021, Best Paper Award at RSS 2022, as well as 2020 IEEE Transactions on Robotics Best Paper Award. Thank you so much for joining us, and we're looking forward to your talk.
Thank you so much for the introduction. Can everybody, okay, let me see. Can everybody Can everybody hear me? Good. Okay. Good morning, everyone. It is really early. And thank you so much for coming to my talk today. And today I'm going to talk about abstraction as inductive bias. And specifically, I want to talk about how we can do open world 3D scene understanding without necessarily the need for open world 3D data. So it will be pretty like a perception heavy talk. So we're going to talk about robot perceptions. Okay. So I want to start by talking about this idea of abstraction as inductive bias. Right. So for today's workshop, the theme is about inductive bias, and we try to ask the question how we can introduce the right prior knowledge as inductive bias in our learning algorithms. Right. But I want to kind of point out that before we even think about or have any particular method, oftentimes the very first inductive bias that you injected in your learning algorithms or your robotic system is actually the way that we defined or decomposed our problem, right? So in another word, it's the abstraction that we introduced to define the problem or decompose the task. So for example, in computer vision, we have those popular tasks like object detection or pose estimation. And you can basically think that as a one way of we define the abstraction between our perception module and the planning module. And this type of abstraction was the way that we define the task actually has baked in a lot of prior knowledge from like our human understanding about how this task need to be decomposed, right? So just think about why we don't represent object with triangles or polygons, right? Why we choose to use bounding box or pose to represent object. So this kind of decision of abstraction actually has a very profound influence on like how we think about the problem, how we designed our algorithm, or in the end, the overall system performance. However, I think recently there are many works that's really trying to move away from this kind of manually designed abstractions, right? Because there's many obvious limitations, right? So for example, if you manually designed like a hard code abstraction, then it's very hard to adapt it based on different end tasks or downstream tasks. And another bigger problem is that this kind of abstraction or modularization may introduce error propagations, especially if your later module always try to assume that your earlier module is always perfect and correct. So that can cause a lot of problems. But I think we also cannot just ignore the benefits or advantages that's brought in by some good abstractions. Right? So for example, by first decompose a bigger task into smaller modules, we really make each of the submodule like the task simpler. Therefore, potentially each of the decomposed tasks can be learned from a smaller amount of data, and it become a much easier problem to solve. And also, with a good abstraction or the right problem definition, it's more likely we can encourage the learning algorithm to actually learn the underlying structure of the problem instead of trying to memorize the pairs of input and output data. So as a result, with that kind of like underlying structure learned, it's more likely the method or the learned model can generalize beyond the training data. And finally, I think that we should kind of just accept the fact that abstraction as inductive bias will just like be unavoidable. It's always going to be there, right? So just by simply defining the task, we kind of already introduce this kind of inductive bias in our problem or in our system. So I guess instead of like just trying to avoid it or think about it as a hack, we should really like carefully think about how we can properly design the abstraction layers so that we can best leverage its advantage. So that is a limitation and advantages of using abstraction. And in particular, in this talk, I will talk about one of our recent work, semantic abstraction. And I hope to use this work as an example to show how we can leverage those advantages of abstractions, and also hopefully bypass some of those limitations that I just mentioned. And in the later part of, probably towards the end of my talk, I will talk a little bit about why I think this idea of abstraction as inductive bias is going to become more and more increasingly more important, especially in the age of large pre-trained models. Okay, so let's start by talking about this project. So in this project, we're trying to do this task, open world 3D scene understanding. Right? So what do I mean by open world 3D scene understanding? I think in this task, what we really ask the robot to do is to have the ability to recognize a dynamic set of semantic categories. And more importantly, we want to ground those semantic concepts with spatial information in a 3D environment. So just to make it more concrete, let's all think about this particular application or task. Right, so if you ask your robot to try to find your COVID-19 rapid test behind the Harry Potter book, so what will require the robot to do? So first, clearly, the robot need to understand a very large collection of semantic, visual semantic concepts, right? So for example, in this task, both the COVID-19 rapid test and the Harry Potter books are not a typical category that you will see in ImageNet dataset, right? So those are like new concepts, but they are actually very important in your everyday life. So we need the robot to understand those uncommon concepts. And also, in order to do this task, the robot also needs to understand the spatial concept. So for example, what does it mean by behind? And then more than that, in order for the robot to like safely navigate in the 3D environment and also precisely localize the objects in the 3D environment, the robot also needs to have a geometric and like understanding about the geometry of the 3D environment, right? So it also needs to able to kind of perform, for example, shape completion or scene completion in this 3D environment. So those are all the tasks or capabilities we want the robot to understand, right? So if we want to train one model that asks the robot to understand all these different concepts, I think ideally what we need is a really large 3D data set that jointly kind of presents all these different combinations of all these different concepts. And I want to say that although it's not impossible that eventually we will have a data set as big as that and contain all the different concepts, but I would agree that I guess most of us will agree that it will probably take a while for us to get a data set like that, right? So it's kind of really hard, and also like I think right now we really don't have that data. So, but can we actually with the existing data sets that we have, can we actually have a practical way to approach this problem? And this is what we really think about in this project. So the idea is that if you are not looking at all these 3 different concepts jointly, but actually instead try to look at them separately or one by one, you'll start to realize that each of these different concepts actually presents very different properties, right? So as a result, it probably means that we can learn them in a very different manner and also leverage different type of data set. So here are some examples, right? So for example, start with the spatial concept. Right? So the space actually for the whole spatial concept is actually quite small if you think about it. Like the way that we can describe the spatial relations between 2 objects is actually quite limited. And in actually a lot of natural language literature, they actually assume that the spatial concept is a closed set vocabulary, right? Because there's a limited number of vocabularies that we can use to describe spatial concepts. And if we move on to the geometry concept, we know that although the space for all the possible 3D shape is quite large, but oftentimes they are decomposable, right? So in computer vision and graphics, we often use primitive shapes like cubes or generalized cylinders to represent 3D geometries. That kind of shows that the 3D shape is most of the time decomposable. And especially, I think that's argument is particularly true for man-made objects, right? So that kind of shows that the underlying structure for 3D geometries, although it can be big, but it's decomposable, therefore it's more attachable, more solvable with simpler data sets, for example. And but if we move on to the visual semantic concept, we know that they are really large, and also often they are oftentimes not decomposable, right? So it really requires the system to really see all these different type of data in order to really understand the visual semantic concept, right? So we can see that they have very different properties. So as a result, very likely we can tackle these 2 categories of problem with different type of data sets, right? So on the one hand, if the system needs to understand visual semantic concept in the wild, in our 3D environments, it really requires the algorithm to be exposed to the internet scale data sets. Means that we need a very large data set that really covers all the possible visual semantic concept. But on the other hand, for the geometry and the spatial concept, it may be just possible to be learned through a very much smaller or limited synthetic data set. So this observation is actually the key idea behind our approach for semantic abstraction. So for the first problem, like learning the visual semantic concept, we actually already has a pretty good solution, right? So if you know about those large visual language model like Clip or Flamingo, they actually did a very good job on understanding a large collection of visual semantic concepts. They understand a lot of words and nouns that we described in the internet. And those models also shows a great deal of robustness by being able to train on those very large internet scale data. So our idea is that how we can leverage those like pre-trained visual language model that already learned this large visual semantic concept and then apply it into like 3D scene understanding. So basically what we need to do is to add this kind of 3D reasoning skills to this 2D VLM's visual language model. So what we can do, I guess the first message or approach that's coming to our mind is, can we fine tune those large visual language model on 3D data, right? I think that's a very typical way to kind of adapt a large pre-trained model in a specific applications. However, I think unfortunately, there's a lot of recent work in machine learning shows that if we just naively fine-tune those large models on a very task-specific data set or a limited data set, then those large models start to lose their robustness or generalities, right? It kind of makes sense because it kind of forgot about what they learned from the internet scale data. So as a result, if you fine-tune those models, you kind of lose their original like goodness or like their the knowledge that they learned from the internet scale data. So the question is, can we try to add this new 3D reasoning skills without losing their the robustness of the original 2D VLMs? So our solution is what we call semantic abstraction. So basically, what we're trying to do is to introduce abstraction layer between the visual semantic concept and the geometry and spatial concepts, right? So the goal for this abstraction layer is to really try to enable the network or the algorithm able to reason about the 3D concept in a semantic agnostic manner. So what does it mean by that? So here is an example of how to like understand this semantic agnostic reasoning. So for example, we don't want the algorithm to learn many different concepts for like different object categories. For example, we don't want them to learn one concept for behind the Harry Potter book and another concept for behind the trash can. Instead, we just want them the algorithm to learn one semantic agnostic concept, which is behind that object. Right? And then that object is the abstraction that we use, and it's actually represented as a 2D localization of objects in the 3D environment. So this 2D localization of the objects is the abstraction that we use to represent all the possible semantic concepts. And in order just to reason about the spatial concept of behind, they really don't really, the algorithm don't really need to understand what it is, what the object semantic categories is. So that is the general idea. And here is a high-level overview of how this algorithm works, right? So in the middle is semantic abstraction. And in practice, how we represent the semantic abstraction layer is that we will represent it as a pixel-wise relevancy map, where each of the pixel is representing like the probability of the objects existing in that location. And then on the one hand, which we're trying to reason about a visual semantic concept, we'll use 2D VLMs, right? Given an image, a color image, and a text description of particular objects that you'll try to reference, we'll use the 2D VLM try to localize the location of the objects you referenced in the text. And then after we have this 2D relevancy map, on the other hand, we'll try to learn two different types of 3D network, and in order to reason two different type of 3D reasonings, right? So one is trying to do shape completion, which is reasoning about the 3D geometries, and the other is try to do spatial reasoning, which is trying to localize objects in the 3D space given a particular spatial descriptions. And so for the 3D part, for the 3D network, both of those networks actually does not observe the color image input to the system, and it also does not observe the semantic label. So all it sees in the 3D part is only the 2D relevancy map. And as a result, the 3D part can actually naturally generalize to different visual observations or different semantic labels. So that's the high-level idea. And in the next few slides, I'm going to talk about a few like implementation details or like important implementation details of how we can make this algorithm work. Right. So for the first part, we want to talk about how we can actually extract the 2D good enough 2D relevancy map that allows us to do this kind of semantic abstraction, which is what we call relevancy extraction. So in our framework, we use a model called CLIP. I guess most of you guys know. And also because the popularity of this model, like the CLIP model or a similar model, there's a lot of tools actually already exist that allows us to extract the attention maps or relevancy maps from those 2D VLMs. Right, so here I just show the most popular ones is like a GradCam. So what this kind of tool allows us to do is that given an image, and also a text description, they can help us to track back the gradient and then localize which part of the image actually the model needs to look at in order to make the decision. Right. So for example, given an image that contains both a cat and dog, and then a text description of a cat, then this kind of GradCam algorithm will help us to localize, like you need to localize the cat, the region around the cat in order to make this prediction that it is similar to cat. And similarly, if you input the text of dog, it will also localize the part of the image that is corresponding to dogs. So this is the basic algorithm or idea that we use to extract the 2D relevancy map. But there are actually a few like practical issues when we directly apply those methods like GradCam into our system, right? So the issues, first is that those algorithms often give you quite noisy output, and then sometimes they can highlight irrelevant regions in the image that's not directly only related to the objects that you reference to. And another limitation is that they often kind of have problem or struggle to handle smaller objects. So in this case, if you want to ask the algorithm to localize the Nintendo Switch, it actually will have a very hard time to find it. It's actually on the top of the shelf. It's a very small object. And the reason why those algorithms struggle with smaller objects is because the resolution, the patch resolution used in the VIT model. So in order to use it in our system, we actually really need to address these two problems. So in order to address the first problem, which is trying to reduce the possible noise that's produced by those visual language model, we can try to apply many different image augmentations and then ask them to infer the related relevancy map. And then in the end, we can average all this resulting relevancy map in order to reduce noise, right? So the idea is that the noise that's produced on different image, augmented image will actually appear in different locations. So if you average them together, then those noise will average out, right? So that's a very simple idea, but it's very useful that it can actually indeed effectively reduce the noise produced by those relevancy maps. And another thing we can do is to really capture the smaller objects or localize those smaller objects. We can try to extract the relevancy map at multiple different scales, right? So that's, again, it's a very simple and basic idea, but implementation-wise, you need to make sure how to run those like inference fast so that you can actually get the relevancy map in a reasonable time. So with this multi-scale relevancy map extractor, we can actually successfully localize those very small objects like this Nintendo Switch, and also able to kind of make a very tight prediction or boundary around the typical object like that vase. Okay, so with these two modification, we are now able to kind of extract relatively reliably the localization, the location of the referenced object. So now we have this relevancy map. We can try to project it into 3D by using the depth image, right? So here I visualize the relevancy map in 3D because we have the depth image to project it, but the original output is just a 2D image. And then once we have the relevancy map, the algorithm basically can interpret it as a rough indicator to the 3D network or the 3D module about which objects I'm trying to, the system is trying to refer to, and also means that this is the objects that the 3D network need to complete. Right? So in this case, the attention is really on that sofa. So the 3D network learns that I need to do the shape completion on that region. And then for the shape completion module, we actually trained a pretty standard 3D completion network that use implicit 3D representation. Details you can check on the paper and also the code. But the one thing I want to highlight is that in this whole pipeline, actually the relevancy map or relevancy value does not need to be very accurate or perfect, right? Because this 3D network is explicitly trained to correct any potential errors on the relevancy map. So it can actually adapt to those errors that's already kind of typically present in the relevance in the 2D relevancy map. And then once we have the shape completion module that's trained in a semantic agnostic manner, we can combine it with the original text description that we get in the very beginning, and then we can get the completed shape for a particular object referenced in the text. Right. So in this whole pipeline, you can see that in the end, we get a 3D completion for that reference object, which is a sofa. But in the middle of that whole pipeline, actually, it doesn't really observe the label of sofa or even the color image. So it only observed the relevancy map. So that's why later you can see that this network can generalize to different semantic labels. Okay, so we have this one module, and we just can simply run this module k times or n times, each time for different semantic label, and we can put them together. In the end, we can get a complete 3D scene completion for the whole 3D environment. And this system actually can be applied for any kind of text descriptions as long as the 2D VLM is able to localize them. And then another thing to note is that if the input object description is not visible or cannot be localized by the 2D VLMs, the resulting relevancy map will produce a lower value across the whole image, right? So the system does know that whether this object exists or not. And if it exists, it will try to complete. If not, it will also provide that indicator. And then for those objects that cannot be directly observed in the image, then what we can do is try to provide additional spatial reference to help the system to localize that object. So that is also the second task we did in this paper, which we call visually obscured object localization. So the idea for that task is that in this environment, you probably cannot find any CoRL tickets, but if you tell the system that there is a CoRL ticket on the top of the fireplace, then can your system localize it, right? So that is basically the description for this particular task. And so the goal is that we want the algorithm to localize this reference object, the target object CoRL ticket based on the spatial description is on top of the fireplace. And here is how we can do this task in two very simple two steps. So in the first step, we'll basically reuse the same module that we introduced earlier, which is the shape completion module that first try to localize and complete the reference and target object, right? So in this case, the reference object is the fireplace, and the system can localize it and complete it. And the target object is CoRL ticket. And in this case, the system cannot find it in the environment. So it also knows that. And then on the second step, we'll try to localize the target object based on the spatial relations. In this case, it's on top of. So we can actually get these spatial relations, and then we try to compute, first compute a spatial embedding for that spatial relation, and then we'll try to compute the cosine similarity between this spatial relation with the full 3D volume in order to get a 3D localization of that, the referred 3D region of that object. Right, so here we actually need to learn this particular spatial embedding for different spatial relations, right? So on top of, on the right of, on behind, or inside. But we can actually learn this kind of spatial embedding for every single spatial categories that I was thinking about, because there is a limited set of those spatial categories, right? So in our paper, we actually just consider 6 different type of spatial relations. And then we can train them specifically in a 3D data set. And here is data that we used to train this model. So we actually, for different tasks, we actually require different type of ground truths, right? So in the first task, we need a complete 3D shape. In the second task, we need a spatial localization. And we can actually generate like almost perfect ground truths with a synthetic 3D data set. So in this case, we actually modified the AI to through data set to generate the ground truth label for both tasks. But I want to highlight that clearly this training data for this 3D module is very small and limited, right? It doesn't really cover all the possible combinations or scenarios we want the system to handle, right? So it is just a synthetic data set with limited number of rooms and also limited number of objects. But and also if you just want to interpolate between this training data, it's not going to work to generate to the open world 3D thing understanding task. So what we really want the system to generalize to is first, we want it to be able to handle novel vocabularies, means that you use different words to describe the same object. We also want them to generalize to novel semantic classes that actually requires them to handle different geometries and also semantic labels, right? So for example, the teddy bear that's never appeared in the training data. And more importantly, we also want them to generalize to novel domains, right? We want them to actually work in real world, not just synthetic data set. So we really put a lot of emphasis on evaluating directly on the real world environments with real world images. So our hope is that we can inherit all those generalities from those pre-trained large 2D VLMs in order to really extrapolate out from the training, the original 3D training data set. So here I'm gonna just quickly directly jump into our results. So and I'm gonna only show you the results on the real world data because I think that's what we really care about. And in our paper, we also provide more quantitative evaluations on synthetic data set. So here is the qualitative results on the Matterport 3D data set. They are captured from the real world. And here is one example result from that data set. So I actually really like this result because if you look at the image, right, so it has a very colorful wall. And that's something that's very different from our training data. Like in AI store, we never really see a wall with so much paintings. But the system is able to generalize to this kind of environment because the 3D module just never observes the textures in the color image. And they can just complete the 3D wall with very simple geometries. And also this algorithm is able to kind of really localize very small objects like this Rubik's Cube on the table, and also uncommon or long tail object concepts like Harry Potter book that we showed in the earlier is not part of the ImageNet or MS CoCo dataset. And finally, the algorithm is able to do this kind of spatial localization task, even when the object is not directly observed. Right? So it's able to localize the used N95 in the garbage bin. It doesn't really see the mask, but it's able to localize the garbage bin and understand the spatial relations of inside, and then therefore localize the object. And similarly for COVID-19 test behind the Harry Potter book. So that's one result. And I think another nice thing about the whole pipeline is that with this semantic abstraction layer, we're now able to actually look into or examine why the algorithm make particular decisions or predictions by looking at their relevancy extractions, right? So we can actually look into maybe like kind of identify which part makes a mistake by looking at the abstraction layer's prediction. So for example, we can see that it's indeed able to clearly localize like the small Rubik's Cube and Harry Potter book. And that's also why they can do the shape completion in the end. And here is another result. And I think here I want to highlight the spatial localization results, where the basically you can imagine you ask a robot to find your vaccine card in either the red folder or the blue folder. Right? So in this case, you can imagine that basically the CLIP model, they learned very good on like recognizing colors, and we cannot rely on that capability in order to localize the objects based on the text descriptions on their attributes. And here again is the relevancy map. We can see that the algorithm or the model does not see the vaccine card, right? It has a low relevancy map across the whole image, but it's able to like very confidently localize the red folder or the blue folder in the image. And that's why they can make this prediction. And then I'm going to show you another just collection of results on a completely different data set. So this is the Apple ARKit things. And so I just want to highlight that it is a very different distribution compared to Matterport data. And it's even captured with very different cameras. It's used iPads. And then we just, again, directly test our algorithm without any fine tuning. And here's the results. And you can see that the quality of the prediction is actually very similar compared to what we have tested on the Matterport. Sometimes it's actually even better because the image is in higher quality, right? So I also want to highlight that the model is actually able to handle very long descriptions. For example, the hair dryer with the wires tangled behind the chair legs. And we actually find out that the model performs better if you provide a more detailed descriptions than just a generic description that's a hair dryer, right? Because all those description actually helps the CLIP model to kind of localize the particular object in the 3D environment. So I think that is a really advantage of using those visual language models in this kind of task. And here is a relevancy map. And in this example, I actually want to highlight a type of failure case that we observed in this model. Right, so this is actually when we ask the system to localize the light switch. And you can see that they actually localize both the light, which is the lamp on the table, and also the switch, which is like the switch on the wall. But in reality, what we really want them to localize is a switch on the wall. So I think this kind of problem is actually kind of highlights the limitations of today's 2D visual language model. And they don't really understand the like complicated semantic concepts. And sometimes people say that it's just kind of perform like a bag of words model. But I think this kind of limitation or issue can be addressed with the future better 2D visual language models. And finally, final results on yet another data set, right? So this is NYU V2 data set. And we're actually showing you this scene completion result. And I'm actually personally really excited about this result because this is actually for the first time that we are able to test on the all 894 classes in this data set. Right? So if you're familiar with the NYU data sets, you probably know that oftentimes what people do is that they will take those uncommon object categories like puppy toys or the shoe, they will map into a superset of category like the other objects or other furnitures so that they can have a fixed number of lists of object categories you can do classification over. And I have worked on this data set for a very long time, ever since I was a PhD student. And that's what I always do, right? But in this time, we're actually able to test with all the possible labels that's provided by the data set. And actually the result is also pretty good, and especially for those uncommon objects like the puppy toys. That's why I feel like very excited about this particular result. And I think that really highlights the advantage of using those open vocabulary visual language models. Okay, so finally, with this like kind of object localization model, we can eventually connect it or combine it with a navigation model, and then in the end form a full completed system for object search, right? So we have so you can think about this semantic abstraction as a visualization or object localization model, and we can connect it with a particular object like navigation model or exploration module, and then we can have a robot to explore in the 3D environment and actually find the right objects that you refer to. Right, so this is actually another work that we worked on. It's called Clip on Wheels, and we call it CoRL for short. So again, by using this modularized designs, right? So we did like kind of separate localization and exploration. We can directly apply those open vocabulary VLMs to object navigation tasks without additional training on object navigation, right? So just want to highlight, we actually didn't, for the CoRL models, we actually didn't train anything on navigation. We just directly apply it. So we evaluate our many different variants of CoRLs on this new benchmark called Pastures benchmark. And specifically, we want to study capabilities that a close vocabulary object navigation agent cannot do. Right? So for example, we test on task of trying to find those uncommon objects, this llama on the sofa, and or finding objects based on their attributes, either their appearance attribute or spatial attributes, right? This is something that we already see the model can do through the semantic abstraction work. And again, we want the system to find hidden objects like the mug under the bed, or in the end, we want them to do like perform zero-shot adaptation that's directly performed in the real world. And to make the problem actually harder, we actually specifically introduce like destructor objects in this benchmark, right? So for example, if we want the system to find the hidden object like the mug under the bed, we also add mugs on the table, and the system should not find that one. It should try to localize the one that's hidden behind the bag. So that really requires the algorithm to have a deep understanding about the descriptions provided in the text, and instead of just treating them as a bag of words. So it's actually a very challenging problem for today's VLMs, and we actually observe a lot of failure cases in this kind of test. But our hope is that eventually in the future, there are better visual language models that can handle this kind of problem. And here is just one highlight or like a quick summary of the results. And I think so probably the one thing that we found very surprising to us is that this zero-shot CoRL model without any training on the task of navigation is actually able to perform better than a fine-tuned state-of-the-art models on this particular task. Right? So I think that result really highlights the advantage or the power of using this abstraction for zero-shot adaptation. And in our paper, we actually provide a lot more evaluations and quantitative analysis, and also like error analysis. So if you're interested in this task or this direction in general, please feel free to check out the paper on arXiv. Okay, so now I want to kind of summarize and conclude this talk, and I want to come back to this idea of abstraction as inductive bias that we started. So in the beginning of my talk, we kind of introduced the advantage of this idea of using abstractions as inductive bias. And I think it can be summarized with two main points. Is we can hopefully learn from less data because each of the tasks is simpler. And we also hope the algorithm to generalize better because you're learning a simpler task or learning the underlying structures. And we kind of observe these two advantages already in the semantic abstraction work. And we also kind of shows how we can kind of bypass those limitations for a typical like modularized system or using abstractions, right? So in semantic abstraction, we show that there is a potential way for the model to adapt to different end tasks by designing or learning different reusable modules. We do two different tasks, shape completion and localization. And it's also possible for the model to kind of reduce error propagation by learning the downstream model that explicitly learns how to handle the errors in the earlier modules. So those limitations may not always exist for the abstraction, like modularized system that you designed. And I also want to highlight that just go beyond this one work that I showed today. I really feel like the idea of abstraction as inductive bias will become increasingly more important in the age of large pre-trained models, right? So today we have so many models that are trained with internet scale data like PaLM, GPT-3, CLIP, Flamingos. They are really powerful. They learn a lot of things from the internet scale data. And they are probably already learned a lot of common sense knowledge that's useful for many robotics tasks. But because of their size and their compute or like practical reasons, maybe it will become like harder and harder to fine tune those models for your particular task. And also we kind of see that if you fine tune this model for a particular task with a limited data set, you may even hurt those models because kind of ask them, like make them forget about what they learned in the internet. So with all these things in mind, I think that's the idea of using the right abstraction can be very useful and powerful, right? So it can allow us to directly extract the relevant knowledge from those large models in a zero-shot manner without any fine-tuning, and they can directly be useful for different tasks, especially in robotics tasks. Right, so here I want to show you just a few other examples, right? You can actually use abstractions to kind of extend new capabilities to those large models, right? So here is how we can kind of extend new capabilities like robot navigation or robot manipulation. They are like something that's not, that those are new skills that original large language model or visual language model does not have. But by carefully designing the abstraction layer, you're able to kind of attach a smaller and task-specific model in order to do those new tasks. And actually, both of the work are not my work, but they are presenting in, I think, this CoRL. So feel free to check it out. And I think they're like really showing like very interesting and creative ways of using those large models for robotics tasks. So I feel very excited. And another idea is that you can actually designing those abstraction layers in a way that you can actually combine different large models so that they can share their different expertise to perform various tasks, right? So here is the Socratic model approach that you can combine a language model, visual language model, or audio language model together. And here, the abstraction layer is actually the language, right? So you can use the language basically as different models talk to each other so that you can actually directly use them for many different tasks without any fine-tuning. And I just showing all this work, just really trying to encourage us to think about creative and new ways of like designing the abstraction layer so that we can better use those large models in general. And I think that's the end of my talk. And I guess I'm happy to take questions. And if you have any questions, yeah.
running a little bit behind schedule now. So I think we can take questions offline, or later we're going to have a panel discussion with all the speakers, so we can also take that time. So thank you so much for the presentation. It was really cool. And let's give her another round of applause. Great. All right. So our next speaker, final speaker of this session before we go to coffee break, is Beomyeon Kim. He is an assistant professor in Graduate School of AI at KAIST. He directs the Intelligent Mobile Manipulation Lab. Previously, he obtained his PhD in computer science from MIT CSAIL in 2020, MSc in computer science from McGill University, and BMath in computer science and statistics from University of Waterloo. Beomyeon, the floor is yours.
All right, thanks for the introduction. So what we're going to talk about today is integrating search and learning for some of the long horizon manipulation problems that we have in robotics. So what our lab is interested in are problems like, deploying robots to clean up your living room, help workers at a construction site, or deploying robots at warehouses to, pack things or move things around, right? And what these problems entail are that these are all these are problems that have long planning horizons. So you can think orders of minutes, hours, and days instead of just seconds, right? And all these problems involve a hybrid decision space. So it's got discrete task level decisions, like which object you're going to manipulate. And it also has continuous motion level decisions, like how you're going to manipulate each of those objects that you've decided to manipulate. Right? And you can characterize these problems as task and motion planning problems, which can roughly define as achieving some high-level goal, right, by planning a sequence of low-level motion primitives. So pick and place, pushing, throwing, and etc., given a model of the world. Right. And some of the examples of high-level goals would be, things that I just showed you earlier, like the construction, packing, cleaning, and so on. Right. And so, this is a general problem. And I think in the literature, we have largely two different approaches to this problem. So one is this pure learning approach, where you're taking this data-driven approach to learn a policy. Right. And the other approach is a pure search approach, where you design a planner that can solve these problems using, things like optimization or tree search, right? So I think one representative class of algorithms for learning a policy are these deep reinforcement learning algorithms, right? And they've had successes in, playing Atari games at a super human level. They've had successes in dexterous manipulation, locomotion in the wild, and so on, right? But I think these algorithms have their advantages and disadvantages. In the perspective of robotics, I think these problems, one of the main advantages of these algorithms is that they're quite fast. So in order to compute the next action to execute in the real world, what you need to do is that you just got to put in the input to the neural network and then make a forward prediction, right? And that happens on the orders of milliseconds, right? But the downsides are that they tend to be fragile in the sense that if you ever encounter an input or state that you've never seen before, you're likely to make mistakes. And that mistake will lead you even to a state that is even further than the states that you've seen before. And your errors is likely to accumulate. Right? And because of this reason, these deep reinforcement learning algorithms, they tend to be data hungry. Right? So these algorithms have their advantages and disadvantages. So what about the second approach, right? So building a planner, right? So this is more of a classical robotics approach where you carefully design the models and then build a planner using that model to get you from the initial state to a goal state. So I think these approaches were widely used in the past, but I think learning-based methods have overtaken the field, I think. So I brought some examples of to just show you what these algorithms can do, right? So here's a work that I did with Anthony Simonov, right? And what this does is that it's perceiving the environment with the cameras, but it's making a plan using tree search as to how to manipulate this bottle in order to move it to the target location. So it plans a sequence of push, pick, and place in order to reorient the object and then put it at the right location. Here's a work done by Rachel Holiday, and this is, again, using tree search, right, to reason about how you can use extra end effector that exists in the world to open a bottle, the lid of the bottle, right, that you cannot do otherwise by just using your own end effector, right? And here's another example of a robot using a planner to solve a very complex problem. So this is, again, using a tree search, right? And it's building what's called the truss of a building. That's, you can sort of think of that as a skeleton of a building. And it's all doing this. These robots are all doing this without any learning for planning, right? So these are all performing tree search. And of course, these algorithms have their ups and downs too. I think, in my opinion, the biggest advantage of this planning-based approaches is that they can guarantee you a completeness. So unlike learning-based approaches, they can guarantee you that you can find a solution from the initial state to the goal state if there is one. So they can guarantee you a form of completeness. So it can be a form of, it can be a probabilistic completeness, it could be resolution completeness, but it can guarantee you, right, for the given initial state and a goal state, that it'll find you a solution. But because these algorithms are performing these tree search and optimization that thinks about, okay, what are the available actions at the current state? What are the consequences of these actions that I have available, right? They tend to be inefficient and take a long time to compute the next action to execute, right? So I think we have these two ends of the spectrum for building robot intelligence. One is pure planning and the other one is pure learning, right? And they have their own advantages and disadvantages. And what we do, what our bias is that we should integrate the search and learning in order to do what we call meta planning. So in meta planning, what you do is that you learn to guide planner. So you have a planner as a backbone that computes what to do, right? But you can use learning to utilize your past planning experience to guide a search to a more promising region of the search space. So you can guide your optimization, or you can guide your tree search so that it can compute the next action to execute a lot faster than you would if you didn't have that, if you didn't utilize learning, right? And so advantage of this method is that because it's using a planner as a backbone, you can guarantee completeness, and also you can be fast because you're using learning to guide the search, right? And I think a good example of this is AlphaGo, right? So if you think about AlphaGo, it's solving this long horizon problem with very large branching factor, and the way it solves it is by integrating Monte Carlo tree search, which is a planning algorithm, with reinforcement learning that learns the value function and the policy to guide a search. So at every state, it tells you, okay, you should be evaluating, you should be thinking about what action to take in this particular state, because this state has the highest value out of all the states that you have. And you should be, considering this policy, this action, because my policy in the past have explored this action, and that led to a win in the game, right? So, AlphaGo was a great success, right? That combines this Monte Carlo tree search with reinforcement learning. So the natural question that we can ask then is, can we just directly apply methods in AlphaGo to solve some of the problems that we're contemplating, the long horizon manipulation problems that involve, these hybrid decision space? And the short answer is no, and these are because of two key reasons, right? So one key difference, as I have said, is the difference in action space. So if you think about the game of Go, right, you've got a discrete action space, and it's got 19 by 19 board, so it's a huge action space, but it's still a discrete action space, right? But if you think about task and motion planning problems, right, you've got this discrete decisions like which object you're going to manipulate, and you've got these continuous decisions that are related to motions as well, like which base pose are you going to use to pick up an object. So task and motion planning problems have this hybrid action space. Another difference is the difference in the state representation. So in the game of Go, you can use a board image as an input to your value function and policy, and that would contain a sufficient information. But if you think about the task and motion planning problems, what it involves are what the state needs to encode are things like, okay, there are objects in the world, and how these objects are related to one another. So does one object include one other object? Is the object reachable from where the robot is? Or can this object be manipulated into a particular a region like kitchen or a room, right? And another thing that the state needs to encode is sufficient information to infer the existence of a feasible motion plan in the given state. So can you plan, with the given information in the state, a motion that manipulates an object or a motion that gets you to a pre-manipulation configuration, right? So because of these two key differences, right, you cannot just directly apply the AlphaGo system to task and motion planning problems. And so what I've done in the past is taking the high-level intuition from the AlphaGo, which is using learning to guide planning, and then try to adapt that to task and motion planning problems. Okay, so I'm going to talk about that today. And so I think to do that, we need to talk first about how do you perform planning? How do you perform search in task and motion planning problems, right? It's because we've got this like complex decision space with discrete and continuous actions, and you also have to think about the low-level motion planning as well. So I'm going to introduce to you a very simple algorithm. So it's not a sophisticated algorithm; it's a very simple algorithm, right? But I think it demonstrates the right. I think it demonstrates the things that go inside a task and motion planning algorithm. So think the kinds of decisions that you need to go through, right? So this search algorithm is called sampling-based abstract edge heuristic graph search, or SAS for short, right? And as its name implies, it's a graph search algorithm, right? So it's a heuristic graph search, and as in any graph search algorithm, it starts with a search queue, right? And let's say the robot is situated in this room with 8 different objects, and you first make the discrete level choice, right? So you have a pick action that you can perform, right? And you could either pick object 1, object 2, or object 8, right? And so what you do in this particular algorithm is that you put the state and discrete action pairs on the search queue, right? So you have a search queue that looks like this now, right? And then based on your heuristic function that evaluates which one of these state and action pairs are most promising, right? You dequeue them, and then you go down on that branch. So let's say this picking up object 1 seemed the most promising according to your heuristic function. So now we've went down on this branch, right? And you dequeue the particular state and action pair that you've selected, right? So it's gone from the search queue. Now you have to make your continuous level choices. So now you have to choose the base pose and a grasp that's going to enable you to actually pick up this object, right? And so you can use random sampling to sample these, continuous actions that goes with picking up object 1. And then what you do once you selected your base pose and a grasp is that you need to call the motion planner to check if there is a feasible motion with the sampled continuous actions, the base pose and a grasp, right? And if there is one, right, you can simulate the next state where the robot has picked up an object, right? And so you can think about building this, tree that goes through, making the discrete level choice, the continuous level choice, and motion planning until you have a trajectory that leads you to a goal, right, in your search tree. Okay, so you can imagine how this is a very complex and time-consuming process, because it not only involves making a decision among the discrete set of objects, but also you have these like continuous parameters that you need to choose, and you also have to plan your continuous motions, right? So this is a very complex search problem. So, one way to make this, complex search efficient is, of course, by using learning. And one of the ways that you can use learning is to evaluate these state and discrete action pairs, right? So, as I showed you earlier, in this initial state, the robot has 8 different choices, right? And the question that we are asking when we're choosing among these actions is whether one discrete action is better than the other action, right? So is picking up object 1 better than picking up object 2? Is it better than picking up object 3, and so on, right? And so to guide this decision-making process, we can actually learn what I call an abstract action value function, right? That tells you which one of these abstract actions is better. So here it's an abstract action because you haven't fully instantiated these picking objects with your motion plan and continuous parameters, right? But you're learning what we call an abstract action value function to guide a search at the discrete level. Okay, so this is one way to guide a search, and I'm going to show you how we can address this problem. So I think there are many different challenges, like, how do we design an objective function that learns efficiently from, past planning experience, and things like how do we design the right input to the network so that we have the sufficient information we convey the sufficient information to the network so that it can predict the abstract action values reliably, right? But because of limited time, I'm just going to talk about how we address the second challenge. Okay, so how should we design the input to the network so that the network has sufficient information to infer, to tell the search algorithm, oh, this is a best action that you should consider at the given state? So to answer this question, we took the intuitions from planning literature. So if you read, literature on planning, whether motion planning or task planning, one of the common theme that arises is that given an original, very complex problem, you define a relaxed planning problem first, right? Solve that relaxed planning problem, and then use a solution to guide a planner, right? And so this happens with trajectory optimization in motion planning, where you first plan a trajectory that ignores obstacles, right? And that'll get you a straight line path. And you can use that as initial seed for doing your trajectory optimization, right? And if you're familiar with task planning literature, they have a similar idea applied over and over again, which is you ignore some of the delete effects in your operators, you plan the motion with that relaxed problem, and then use a solution to define a heuristic function that'll guide your search, right? So, these planning algorithms all go through the step of relaxing the problem, use the relaxed problem representation as an input to a planner, right? Use a planner to solve the relaxed problem, and then use the solution to that relaxed problem as a planning guidance. Okay. So, we realized this intuition was applied over and over again in planning literature. And what we decided to do was that replace all the planners with learning. So instead of giving the relaxed planning problem representation to a planner, we're going to give it to a neural network, namely our value function. And then we're going to use learning to solve the relaxed problem, right? And then use the output as a planning guidance. Okay, so the advantage of this is that the planner, despite the fact that it's a relaxed problem, still has to solve an NP hard problem. So it typically takes a lot of time to solve the relaxed planning problem. But here, because we're using a neural network, right, we can just make a prediction, right, and then that takes a significantly less time than if you were to use a planner for this solving this relaxed problem. Okay, so how can we do this for training a value function for abstract actions, so these discrete action choices? So what we do is we represent the problem abstractly. So we relax the problem by representing the problem abstractly, where we ignore all the geometric details like poses and shapes of the objects, and represent the world with what we call geometric predicates. Okay, so whether it tells you whether the object is reachable, whether the one object occludes another object, or whether the object could be manipulated into a particular region, right? So we're going to represent our problem with these set of geometric predicates. So here's an example of what we call the abstract state that's represented with these geometric predicates. So you're given a scene like this, right? And our state looks like this. So it tells you whether the object one is reachable or not, and it's evaluated to false here because there are two objects including the path to the goal, this target object. We've got these occludes predicates that are evaluated to true for these, object 2 and object 3 that are in the way of object 1, right? And so your state representation becomes an evaluations of these geometric predicates over all the other objects in the scene. Okay, so this is how we're going to represent the input to our abstract action value function. Now, of course, the question is, how do you actually evaluate these reachability and occlusion predicates, right? So after we designed these geometric predicates, what we realized was that all these predicates encode information about the reachability and occlusion of objects in the regions. And these are, in fact, well-studied problems in robot motion planning. So there are papers on navigation among movable obstacles. There are papers on minimal constraint removal that tells you what are the minimal set of obstacles that you need to remove in order to get to a particular configuration and so on. And so what we realized is that we can use these robot motion planning algorithms to evaluate these predicates. So our overall computation is as follows. So you're given some kind of long horizon planning problems, a task and motion planning scene, right? And what you do is that you perform low-level geometric reasoning using motion planning. And this will get you the abstract state that tells you about the occlusion relationship, reachability of objects, and so on. And what our abstract action value function does is performing this high-level reasoning, right, based on these predicates, evaluations, right, to tell you, okay, this is a particular action that you should take in the given state, or this is the action that you should explore first when you're performing a search. Okay. And of course, because these are not just binary values, it's actually encoding a relational information. We represent our abstract action value function f theta with graph neural networks, where each of the nodes is associated with each of the objects, and each of the edges encode the relational information between the objects. Okay. And so we apply this, trick of integrating search with learning to this problem of packing tasks. So the robot here has to move all these blue boxes from this room to this kitchen environment. And you can see that there are, movable obstacles in the way. So the robot has to figure out, okay, in order to move all these blue boxes, what objects I need to clear and to where, right? So here is a plan that the robot has found. So the robot at each step is, performing motion planning to determine the geometric predicates and where these objects, the movable objects, should go, and where all these blue boxes should go in order to accomplish the goal. And so, so one of the advantages of using this abstract problem representation is that you can collect the data from an environment that has a significantly different geometric details than your target environment, and then just apply it without retraining, without collecting additional data, because your problem is represented abstractly. So we collected our training data only in this environment where the robot is manipulating this big box objects, right? But we also apply that same value function to guide a search in this environment where robot has to rearrange these small objects in this shelf to fetch this yellow object and put it inside in the green box. So here's a plan that the robot has found, right? And again, it's reasoning about its motion, the swept volumes of its motions, and where the object should go, right? In order to retrieve that target object and then put it inside this box. Right? Okay, so before I show you our experimental results, so our central hypothesis was that for these kinds of long horizon problems, pure learning is going to perform worse than meta planning because it lacks generality, right? And pure planning is going to be slower than meta planning because it does not use prior experience to guide the search. And as I'll show you in our experimental results, that these hypothesis has been is supported, right? So here we can so on the x-axis you're going to see different algorithms, right? On the y-axis are planning times, right? And we have 2,000 seconds as planning time limit, right? And so pure learning approaches, right? Most of them. So this is a median of its algorithm, and you can see that pure learning, for most of its cases, fails to solve these long horizon complex problems that I just showed you earlier. And this is because these algorithms cannot generalize well to the states that it has not seen in the training set, right? But when it does solve the problem, it can do it really, really fast. So you can see that for the problems that it has solved, it solves them with like near 0 seconds, right? But most of them fails because it just lacks robustness against generalization across different states and problems. So here are the results for pure search algorithms, so pure planning algorithms. So this is a state-of-the-art planner. This is our planner plus our hand design heuristic functions, right? And it does better than pure learning in terms of number of problems solved. So, right, so the median has significantly gotten lower, right? No one, I think only one problem got 2,000 seconds. And you can see that, these planning-based approaches, because they're thinking about, they can guarantee completeness, it's more robust to changes in the environment, right? But they're still slow, right? These algorithms are still slow. So here is a result on planning with learning to guide on discrete taskable decisions. So this is a result on guiding the search with the discrete taskable decisions with the value function that I showed you earlier, right? And you can see that it can reduce the time, right? Than when you're using a pure planning approaches, right? And when I didn't have time to go through this today, but when you actually use learning to guide a search both at the discrete level and the continuous level, you can even get it lower than what you had here, right? When you're just guiding the discrete taskable decisions, right? So compared to this state-of-the-art planner, or compared to this pure learning approach, right? You can see that our approach can solve a large variety of problems, right? And it can solve it in a much it can solve them much faster. Okay. So one key takeaway from this talk is that, for many complex long horizon problems, pure learning or pure planning alone is insufficient. And what I believe is that just like humans, a robot has to also think about, the consequences of its actions and choose which one to execute by reasoning about the consequences, and use learning to guide its search process. Okay, and with that, I'll end the talk. And if there are questions, I'll be happy to take them.
Oh, okay. Byung-Yoon, can you hear me? Yes.
Yeah.
Okay. Yeah. So the question was, can this approach be extended to multiple robots?
I think there are people who are trying to extend this to multiple robots. So I think it definitely can be applied to multi-robot setting. But so task and motion planning wise, there are actually works already that are out there that extends to multi-robot setting. And in terms of learning, I think the challenge there is how can you come up with a representation that can encode different constraints that multiple robot imposes on the planning problem on the problem itself. So we were able to come up with these geometric predicates because we were focusing on a single robot. But these geometric predicates, I think, would get more convoluted and when you involve multiple robots, and there needs to be a special way to deal with that efficiently.
Okay, thank you. And all right, so yeah, I think we're gonna end the session now so we can have some time to go get coffee, and we'll start at 10:30 for the next session, right? 10:35. Okay, 10:35. So we have a little more time. All right, thank you very much.
Hello, Michael, are you there?
I am.
Great. So I guess probably you can give it a shot to start sharing the slides while I introduce you.
Yeah.
All right. So now we're back. So thank you everyone for joining us again for the second session. So next speaker is Michael Luther. He's currently a research scientist at Boston Dynamics. But before that, he actually did his PhD in TUM Darmstadt, for which he actually got the George Giroir Award this year for best PhD thesis in Europe. And he also got the German Computer Science Foundation Award for the AI newcomer in 2019. So Michael, it's a pleasure to have you with us. So please, the floor is yours. Thank you.
Thank you for the nice introduction. So yeah, I am a research scientist at Boston Dynamics right now, and I will make the advertisement before. So Boston Dynamics is not all about MPC anymore. So we have an RL team and also computer vision and machine learning teams inside Atlas. So if you're looking for jobs in the next 12 months, we're actually growing the Atlas team quite a bit. We have been growing quite a lot, and we will be growing quite a lot next year. So if you are looking for jobs and have any questions about like Atlas jobs, feel free to reach out to me or check our homepage. But in this talk, it will be not about my current work. It will be more about my prior work in my PhD, which I completed at TU Darmstadt. So I want to start off this presentation with the question, how should you program a robot? And depending who I ask, I might get very different answers. So there's one party or one fraction which will say, oh, classical robotics is all you need. Just get a lot of smart control engineers, let them design a perception system, let them design a control system, define very precise interfaces between them, and everything will be good. Then there's a different fraction which will be more in the direction of, oh, deep learning, end-to-end, and data is all you need. Just get sufficient amount of data and train a deep network to do whatever you like. In this talk, I want to argue that this is not black or white. It's more a trade-off between two different approaches. First of all, we can have, in the classical domain, we have a lot of manual engineering, but very little data, while in the end-to-end approach, we have a lot of data, but no manual engineering. However, we can mix and match this however we want and get a trade-off between manual engineering and data. So in this presentation, I want to look at 4 different projects, which I did during my PhD, which explores the difference between these trade-offs and use prior knowledge or learning, or use prior knowledge as an inductive bias for learning. So let's start off with the first one, which is structured movements for robotic juggling. So here we wanted to learn how to juggle 2 balls with the single arms. So we kind of wanted to start off with something like this, where we can't juggle at all, and then suddenly move on until we reach something like this, juggling 2 balls in columns with 1 arm. And all we did this with a bam. This is quite a challenging problem because it's very high speed. And because it's very high speed and like really drives the robot to its boundaries, we have to learn it on the physical system. However, if you want to learn it on the physical system and not destroy the robot in the meantime, we have to make it as sample efficient and safe as possible. So here what we opted for is actually starting with an initial guess of how to juggle. So we had an initial trajectory and then only explored in the vicinity of this trajectory to find the optimal solution. We choose this because this naturally narrows down the search space quite a lot. It makes the parameters a lot smaller and also much safer because you kind of know where the robot will explore and whether the robot will crash into its joint limits or not. And then with this approach, you can just use any episodic reinforcement learning technique and just optimize the trajectory until the robot learns juggling. And we had quite a success with this approach. I mean, even though it's simple, it's very efficient for the chosen task. So here on the left, you see every sample the robot ever draw. So it starts out with just like throwing the balls a bit up and down. However, it doesn't really catch them. With times and more samples, it gradually improves until all episodes succeeds and the robot identifies the optimal trajectory to balance it. And here with only like 400 trials, the robot learned to juggle perfectly, which 400 trials approximately correspond to an hour of real-time experience. And the learned policy is actually really good at juggling. It's better than we ever were able to like tune it ourselves by hand and tweak the policy or tweak the trajectory by ourselves. So it can juggle up to 36 minutes without a problem. And it's like 4,000 repeated catches, which is quite amazing on a physical system. And it's also very reliable. And the second part, we looked at more, or we kind of switched from structured movements to structured dynamics models. So instead of structuring the movements, we wanted to look, can we structure the dynamics model to learn a very good dynamics model? Here, we also wanted to be more on the classical side. So here we have a classical approach enriched with more modern learning techniques. So we focused on learning dynamics models via system identification. However, we didn't want to just look at classical identification of robot arms, but more at a task which classical algorithms from system identification cannot solve. For example, here we looked at ball and cup. So here you not only need to learn the dynamics model of the manipulator, but you also need to learn the dynamics of the ball and the string. So classical approaches don't really apply here because you can only learn the dynamics of the manipulator, but not of the ball and the cup. So what we did here, we wanted to use differentiable simulators as well as gradient-based optimization to optimize the dynamics parameters. So we just used the equations of motions, differentiated them, and then used backprop to optimize the parameters. We also employed different strategies to parameterize these things and parameterize the dynamics parameters such that it's always guaranteed to be physically plausible. And then we wanted to see whether or how good such a learned model can be for model-based reinforcement learning or used for planning, whatever you want to call it. So here we just took 4 minutes of data from the physical system, learned the system, and then used an episodic reinforcement learning technique to just optimize a trajectory offline and then apply it to the physical system. And when we just do this with a nominal model, which we got from the manufacturer, and with a measured string model, it kind of doesn't succeed. It always overshoots. However, if you use our learned model with differentiable simulation, we learn it quite good and it naturally transfers to the robot. If we compare it to something like deep networks, we see that these models are heavily exploited by these methods. So here, on the data, on the training data, this model actually looks really good. However, if we apply it to a planning or model-based reinforcement learning technique, the model is just exploited. And if you look in simulation, it actually finds a solution where the ball magically tunnels into the cup if you perform random movements. However, it doesn't really work on the physical system. We also tried it for very different string lengths and different seeds for the optimization techniques. And we were able to apply it to very different string lengths from 35 centimeters to 45 centimeters. And depending on the seed which you use for starting the optimization for the solution, you get very different solutions. You have ones with multiple pre-strings, you have one with few direct ones. So a lot of them transfer. It's not perfect, so there are a few cases where it doesn't transfer. However, if it doesn't transfer, it's usually very close. So sometimes it bounces off the rim of the cup or just behind the actuator. We were actually really surprised how good this worked on such a challenging problem with the spring in a cup. With like these experimental works and more like enriching classical methods of learning, we want to switch to the other side. Here we want to look at how can we enrich deep learning with knowledge to actually learn better things. So here we first look at deep Lagrangian networks and then at robust fitted value iteration. So with deep Lagrangian networks, we're going to again focus on learning dynamics models. So here we want to learn a dynamics models of an arbitrary dynamical system. However, we want to do it with a deep network and with very little knowledge. So we went in and came up or used physics-inspired networks to learn a dynamics models. So here you have bare bones deep networks. However, you have some assumptions about the system which help you to incorporate an inductive bias into these networks. And in our case, it was we assumed that the systems we are observing can be described via Lagrangian mechanics and that we are observing generalized covariance. If we make these two assumptions, we can learn a physically plausible model which conserves energy. So how this then works is, instead of using one deep network to just predict the dynamics or predict the change in state, we use two networks. One network predicts the kinetic energy, or more precisely, it predicts the mass matrix or the lower triangular matrix of the mass matrix, which is then used to compute the kinetic energy. A second network predicts the potential energy, and then we combine it into the Lagrangian, which is just simply the kinetic energy minus the potential energy. And using the Lagrangian, we can derive the equations of motions or the change in dynamics or change in state quite well. And then we have our forward dynamics. And using this approach, we have a few advantages over just using a deep network. We get physical plausibility. So every combination or every parameters of these networks is guaranteed to like model a mechanical system. It might not be the mechanical system we want. However, it's always guaranteed to be something like a mechanical system that conserves energy. Second, we have an unsupervised learning problem. So instead of just learning either the forward or inverse models, we actually get a lot more information. We actually learn the kinetic and potential energy unsupervised, and we can, from these, we can infer a lot of more things. We can also infer like Coriolis, gravitational, or centrifugal forces, which can be later used for control. Lastly, we have this interpretability because we can define or compute these forces, and we get multiple models. So if we just use the deep network, you can learn either the forward or inverse model, but not both together. With deep Lagrangian networks, we get multiple models. We get the forward as well as the inverse model and the energy models, which classical deep networks cannot even learn because it's not observed. Then to learn this approach, we first collect some data on the physical system and then learn the or optimize the network parameters by minimizing the residual of the Euler-Lagrange differential equations. And by minimizing this, we actually, or you implicitly minimize the loss of the forward or inverse dynamics, and you come up or you learn the parameters of the energies. You can also do this online and incorporate this controller into your data generation. We then wanted to observe whether we're actually learning the right system, the right decomposition, because despite having all the structure, we might not be guaranteed that we learn the right decomposition or just imagine something. So what we did here as this experiment, we took a very simple two-joint robot, let it execute a few trajectories, in this case it's characters, and then learned the model from it, and then looked at the decomposition and whether the and observe whether the decomposition matches the ground truth. So here in red is the prediction, and in black is the underlying the ground truth. And we can nicely see that the learned deep Lagrangian networks actually infers the inertial force, which is the second column, the Coriolis and centrifugal forces, which is the third column, And the last column is the gravitational force. This is very well. They match the system very good. There are a few errors, but they are not really significant. You can also do this for like non-simulated data, and you get a very comparable result. It's not as clean as simulation, but it still infers a good solution. And to further show that we actually learn the system energies correctly, we looked at energy control. So here we use an energy controller to control this underactuated system. So the FUTEC pendulum can only be moved at the lower part, but the pendulum is passive, and you have to inject energy into the system to swing it up. And here we use an energy controller, where the control input is proportional to the current energy minus the desired energy to actually pump in more energy. And instead of using an analytic model, we use the learned energy model of deep neural networks. And we can nicely see that the energy learned of the system transfer to energy control, and we can use it for control. The analytic model compares signal or comparable, where the system identification methods which we use here fails a bit. This is most likely just due to noise because we use linear regression to identify the parameters, which can be really susceptible to outliers and therefore learn something wrong. We also did it for a couple. So here you see it for an unactuated couple. And this is quite a nice example because the couple is very high friction. So this is a plastic cog wheel on a metal drive, which has very high stiction. And despite the stiction, we were able to learn the friction as well as the underlying energy model and swing it up successfully. Lastly, I want to look a bit more want to move on from learning dynamics models to learning policies. So here we looked at, can we actually use knowledge from our system dynamics and improve our learning of robust policies? So what we did here, we actually looked at reinforcement learning, but made a few assumptions. So we assumed that we know the reward function and we know the dynamics models, and then they also have a very specific structure. So the reward function is going to be separated into a cost or a state-based cost and an action-based cost. So it's both separable, which is quite a common approach where you want to be at one location where you penalize or incentivize the distance to this desired location, and usually you want to penalize large actions. So this is quite a generic framework. In addition, we assume that this is a mechanical system. So with a mechanical system, we get control-affine dynamics. So the dynamics can be nonlinear. However, it's linear with respect to the actions, which is quite often given for, which is always given for mechanical systems. And using this problem statement, we want to learn an optimal policy, which solves the task and also bridges the symmetry gap, because we want to apply it to a physical system to solve the task. To do this, we don't solve just a reinforcement learning problem, but we solve an adversarial reinforcement learning problem. So here we want to maximize the reward, but there's a second player, which is the adversary, which wants to do the opposite. The adversary wants to minimize the reward. So you have two fighting objectives, which should resolve into a robust optimal policy, where the policy is robust to disturbances from the adversary. And further, for the adversary, we have like very different adversaries. The adversaries can disturb the state, the action, the observations, or the more parameters. And the adversaries are bounded. So they have not infinite energy or infinite like forces. They have to be force limited, because if you make them too strong, you won't learn a robust policy, but you won't learn a policy which does nothing, because the policy learns that the adversary is always stronger, and therefore doing nothing is the optimal strategy. And using these assumptions, we can actually use fitted value iteration to compute the optimal policy as well as the optimal value function. Because the very neat thing is that we can just solve this maximum and minimum in the optimization analytically due to the assumptions. And then we can just do value iteration in continuous states and actions, which was previously not possible even for the adversary case. So the nice part, the solutions are very intuitive. So the optimal policies always follows the optimal value function upwards. So it just follows the gradient upwards of the value function. and it projects the gradient of the value function onto my controlled quantity, which is the derivative of the dynamics with respect to the control. And then this projected gradient is rescaled based on the cost of the actions. So if the action cost is very high, we take a lot of small steps. If the action cost is very small, we take very large actions, which is quite intuitive. And also the adversary. Here, the adversary does the same thing, except that the adversary doesn't want to follow the gradient of the value function up. It actually wants to go down. So it follows the negative gradient of the value function. And it's also, again, projected onto the controlled quantity, and then H maps it to the domain of the admissible set. So this basically limits the act or the force of the adversary. And using this knowledge, we can actually design various different cost functions to also incorporate action constraints. So depending on how you choose G, you can get very different action or optimal policies. So if you use something like a quadratic, which is quite often used, we know that we get a linear optimal policies, which is in line with IQR. But if you use more different action costs, which go to infinity if you come close to the boundaries, such as the log cosine cost, we actually get very bounded actions. So this way we can, on the one side, learn an optimal policy that is robust, but also adheres to action limits of the physical system. We then applied it to our two lovely unactuated systems and compared it with different dynamics. So this might be a bit hard to see, but for the bigger weights, it's good to see. We have added or glued different weights to the pendulum to change the dynamics. And in the top row, you see it without the adversary. And in the bottom row, you see it with an adversary. The very neat part is that the adversary, or the robust version, is much more robust to the disturbances, despite whatever you glue onto the pendulum, it swings up the pendulum with a single pre-swing. And if you look without the adversary, if you add more weights, it gets a bit more like random and has to pre-swing the pendulum multiple times before it swings it up. However, we can also see a bit of an disadvantage of the adversarial formulation, because the adversarial formulation always expects the worst case. It's kind of very forceful, so it will do it with much more force than needed, which you can see when the pendulum is balancing upright. It's a bit of a chattering because it learned that bang-bang control is quite good for balancing. The same we applied for the couple, and also here we see that the robust version has a much better symmetry transfer with very well changes in mass in the pendulum. One additional fact here is a bit that in the balancing, the robust version is actually much better than the non-robust version, because here applying very high forces on balancing is actually quite good, because you have to break stiction, which otherwise, if you don't apply so much force, you have to fall a bit until the forces become so big to break stiction. That's why without the adversary, it kind of balances around a bit more. This already brings me to the summary and a bit of the future work discussion about whether inductive biases for robot learning work quite well. So in this talk, I wanted to convince you that structured representation actually helps for robot learning. Structured representation can improve models. You get a lot of more information out of it. You can get sim-to-real transfer to robustness. You can incorporate robustness into your networks. You can incorporate physics into your networks. Especially when you have very low dimensional representations, you get very sample efficient and generalization out of it. For example, in Ball in a Cup, we only learned from 4 minutes of real world data, and I learned a sufficiently good dynamics models to solve Ball in a Cup. And it even generalized to like very different situations. In robot juggling with the structured movements, we only needed 56 minutes of real world experience to solve the task, which is very low compared to the deep reinforcement learning approach. Can generic knowledge be used in robot learning algorithms? Yes. So in the first ones, we didn't really use very generic domain knowledge, but we used more very specific knowledge about the systems and the tasks to incorporate it in our models. However, in the later part, we also showed you don't necessarily need very precise knowledge or very specific domain knowledge about the system, but you can be more generic. So in the case of deep Lagrangian networks, we used Lagrangian mechanics, which contains a lot of mechanical systems, and learned and incorporated this knowledge into our deep networks. With robust value iteration, we used, again, a very wide class of systems and used this to learn robust policies. So the final question is, are we there yet? No, we are not. So in my PhD, I looked at a lot of like various ways to introduce knowledge into learning approaches. However, we have only looked at very simple problems like you've seen if you look at the more deep learning based approaches. We mainly were stuck on two-dimensional systems, on unactuated systems, which are quite finicky to control, but it's not where we want to be. So in my opinion, in our future work, we kind of have to go further and see how we can scale these methods to higher dimensional systems and manipulation. And I think there's a lot of work needed to come up with strategies how we can actually do this. And that's already it.
Thank you, Michael. That was a very interesting talk. Do we have some questions from the audience? Are we shy today? I'm not sure about the people in the chat in the online version. But I can probably start. Michael, so I actually have a question regarding the kind of the lessons learned when it came to apply the deep Lagrangian networks using this barred worm. So usually when it comes to implement this and to actually make them work, I'm curious about like what actually we need to consider if we want to use this kind of networks for other kind of dynamical systems.
Yeah, I mean, it's learning dynamical systems. So one of the critical systems is, or one of the critical parts is to excite the system. You somehow will not get around to like getting rich data, and without rich data, you won't learn as much as you want. So for example, if you want to apply this to a slow kinematic manipulator where gravitational forces dominate everything, it's very hard to apply to this because it will search for inertial and Coriolis and centrifugal forces to actually like solve for kinetic energy. If there's no like signal on these two quantities in it, it will usually converge to a bad optimum. So just as like system identification, you have to really like drive the system past to observe and feel these forces. So this was one thing which we needed to solve. For example, for the Fruta pendulum, we had to swing it up and down in quite high velocities to fully learn the full characteristics of the systems. But this is more generic to a lot of system identification approaches, which need really good data.
Thank you, Michael. Do we have some questions? Yeah, please. I mean, you can probably, you don't mind to approach here, probably this is here.
Hey, Micha, thanks for the great talk. I was wondering, so do you consider a perfect pendulum with no, or the friction is always the same? Because I'm interested in if you have a broken pendulum where the friction is suddenly changing and you cannot really estimate in which joint regions you have that.
So yeah, so in both of my works, so in this one in deep Lagrangian networks, as well as the other one, which is this one, we had friction models involved. So we incorporated friction models into the optimization. For the Fruta pendulum, we had a viscous friction model, while for the cardboard, we had a stiction model. And for the ball string, we had like air friction models, which we optimized for. And we can we always learn the friction models, but one of the things which we were kind of surprised, or in the hindsight is quite intuitive, is how hard it is. So for the friction models, it was always really hard to like infer them, and you have to initialize. You have to have a good initialization to have a good initial guess, because if you're far off, there's way too much ambiguity. So if you move slower than your model predicts, it can have multiple reasons. It can have you can either have more friction or you can have a higher mass, and it's really hard to disambiguate between them. And especially because you have if you have a viscous friction model, you have such a nice gradient where you can just slow things down, and this gradient is really, it keeps on giving to you. So you often end up with a local minimum where it just like ramps up friction and comes to like really diverted solution. So we tried a lot in terms of like resolving the ambiguity between like what's friction and what is the dynamic system. We had very little success in this. So I think it's a very good problem how to disambiguate between like what's dynamics, what is friction. But we found it to be very hard, and I'm very much looking forward to your work and whether you can get better insights and like optimizing both simultaneously.
Yeah, I agree. Especially discontinuous changes in the friction are so difficult to model, and at least my networks always have the difficulty to properly approximate these, region changes.
Thank you.
All right, Michael, thank you very much again. Let's name the speaker again, please.
Thank you, and have a great workshop.
So we hope to see you later in the panel discussion, Michael. So I guess we can now move on to the next speaker. So let me see, we have Francisca online.
Yep, I'm here.
Great. Maybe we can try to share the screen.
All right, can you see my slides?
Yes, so Francisca Maya is our next speaker. She's actually currently a research scientist at Meta AI, but she holds also a PhD from the University of Southern California. She actually also held a couple of positions before being a research scientist at Meta. So she worked at the Max Planck Research Institute in Tübingen, and she also was a postdoctoral researcher at the University of Washington. So Francisca, I think you can go ahead, the floor is yours.
Okay, thank you for the introduction. I'm excited to be presenting some of our work today. And for today, I decided to mix a little bit of some prior work with some recent work, and that's why it's a wide spectrum from structure to pre-trained representation biases for robotics. I'll start with where I'm coming from, like what is like the long-term vision, and then I'll go into a bit more detail of how I see structure being important, and then I'll talk of some of the work I've been doing in this direction. So when I think about robots, I always have this very ambitious view of, well, I'd like a robot to be able to eventually do and help with all of these things that you see here on the screen. So we humans are very capable at doing many different tasks, and well, can we get a robot to do so as well? The challenge, of course, is this is many skills with infinitely many variations, and like variations can be homes, but also just, you know, different plants to give water to and things like that. So the thing here is you can't, like, it's, in my opinion, you can't prepare a robot for all of them. In fact, I think a robot will have to perform lifelong learning. So a robot will always have to be ready to learn and adapt to a new skill. And from that perspective, what I think are some of the more important topics to focus on is, well, if we want a robot to be able to ready to learn and adapt in the real world, then it needs to be able to do autonomous learning, which means we need to minimize expert intervention. it needs to be able to learn in the real world, which translates for me into learn from a really realistic number of trials. And it also needs to be able to do continual learning where new skills and models are learned without forgetting previously learned skills. And today I'm mostly going to focus on the first two. Basically, this autonomous learning for me, I have been thinking a lot about how can we learn from visual demonstrations and how can we learn rewards so that we don't have to tune rewards for each, or cost functions. You can also think of cost functions that we need for new tasks. Otherwise, the robot, we always need an expert for the robot to learn a new skill if we can't figure out cost functions autonomously. And then for learning in the real world, the questions that I'm thinking about are, well, how can we learn representations that generalize? And then how can we utilize structure for that? So those are kind of broadly the themes that you will see throughout the talk today. And I will start with the learning from visual demonstrations, and then I'll show how utilizing structure actually helps with this. And then I will go to actually pre-trained representations and make a little jump. All right, so I'll start with learning reward function from demonstrations. As I've just motivated, I think we should be able to figure out reward, cost, loss functions autonomously. An agent should be able to do so. And ideally from visual demonstrations that are given from a user. Humans are quite good at this from a young age, as you can see here in these GIFs. And so how can we get there with a robot? So just to make it very clear, what we're trying to do is we're trying to give a visual demonstration of a task, like placing this bottle here, trying to extract the reward / cost function. And then we want to use this reward and cost function for a robot to repeat the task, and ideally also generalize to new task settings, of course. The first question here is, because this is from visual demonstrations, we do need a visual representation. In this work, we've chosen key point detectors because they're nicely interpretable, so we know what we're doing. We've learned this key point detector in a self-supervised manner, so we collected some random rotation movements on the robot to collect visual data, and then trained the key point detector. And here you see a sample output from that key point detector. The dots are what the key point detector predicts. Okay, once we had that, we now wanted to then figure out, okay, so how can we learn this cost function? And this is roughly what the pipeline looks like. We have the key point detector that predicts the key point. We take the current joint state of the robot and an action. And then in purple here, this sort of represents the key point dynamics. This is a neural network which predicts the current predicted, the predicted key points and the predicted joint state. And we unroll this over a time horizon that we set a priori, and then we have a goal position. We say we have a goal position that we want to achieve, and we extract the key points on that goal position. And now the question is, what are the actions, given the dynamics model, what are the actions that will bring the key points into the goal configuration from its initial configuration? And so basically the robot, if the dynamics model works, the robot will be able to optimize the action. And also if we have a cost and reward function. So basically, given the cost, which you would think maybe a simple mean squared error between the predicted key points and the goal key points will work, but I'll show you what happens if we do that. So if we have this cost, then the goal is just to basically optimize actions into the goal configuration. And to do this, because we do not have the cost and the default cost doesn't really work, we're actually learning this cost function, and I'm just going to go like very quickly over this today. We're using bi-level optimization to learn these cost functions, where at the upper level, we're trying to maximize the reward. And then we're using the reward, the current reward in the lower level to optimize the trajectory. And this predicted trajectory is brought back into the upper level again to optimize the reward. And I'm happy to go into more details about this later, but we've used this bi-level optimization of reward and cost functions for multiple approaches, like reward learning for model-based reinforcement learning, model-free reinforcement learning, and also for loss learning of regression and classification tasks. Okay, so now I'm going to show you what happens if we use this bi-level optimization framework to learn cost functions. I'll start though, I'll skip this today. I'll start with what happens when we use a default cost, because I think that's interesting. So this is the human demonstration we're given. You see the goal configuration that we want to get into here. And the default cost, which is just a mean squared error loss between the goal key points and the current key points, basically leads to this collision against the shelf, right? It's just trying to maximize the direct path towards the goal. And so that doesn't work. So what we actually want to learn is to reproduce the shape of this human demonstration. And now we tried different cost functions, and we actually infused structure into this cost function. So the first one was a weighted mean squared error loss, which just puts each dimensions, each key point gets a different weight, basically. That also didn't work very well. This is what happens when we do that. It doesn't really learn that there's a movement in X and Y, sort of. And then we have time-dependent cost function. Both the time-dependent and RBF cost functions are sort of structured cost functions that try to learn weights for different time steps and for each key point, basically. Dimension, it's the dimension not for each key point, and those work much better. So this is sort of showing us, okay, we can actually learn cost function and reproduce from visual demonstrations, and then reproduce that demonstration on the hardware. And we do also have experiments where we start from new starting configurations that the robot can sort of generalize with some caveats from. All right, so this whole approach, the master plan here was, okay, once we have a model that can predict from the current state, which includes the visual state as well as the robot state and action, then the next state, and we have a cost, then we're good, right? We can reproduce this task whenever we're from whatever configuration we want. Unfortunately, this is actually not super trivial. This dynamics model is actually incredibly hard to learn. So as I've told you, this dynamics model is a neural network, and we all know neural networks can be hard to learn such that they generalize. And so one of the questions we then asked, okay, so how do we improve this generalization of this predictive model here, the key point predictive model? And specifically, we ask, how can we use structure and analytical models to improve the prediction performance of these predictive models? Just to bring it to some key points of why learning this visual dynamics model was so difficult in a way that it generalizes is we're actually using 2D image key points, meaning the dynamics model is learned in a 2D space, but control actually happens in 3D. The key points do not necessarily always fall on the object and are not forced to consistently track the same part of the object. And then just poor generalization of learned neural network models. And so what we did is, okay, all of these 3 questions we actually answer with the same structure by using a learnable and differentiable robot model that we've developed. We create a link for each of the links of our robot, and we can attach new links for objects that the robot has grasped. And any of the parameters that we're uncertain about in this in each link, we can make learnable, and then basically from data estimate these parameters. And so this means we have both differentiable and learnable kinematics, as well as differentiable and learnable dynamics. And this we will use this capability of having learnable kinematics now to actually improve our predictive model. Okay, so specifically what we're going to do is in this work, we present an approach that learns visual key points by merging visual and proprioceptive information. So we will first tackle the improving learning robust visual key points. And then we will show that we can learn an extended kinematic chain that includes an object in the manipulated descent from the visual key points. So we basically will extend the differentiable robot model with an object that has unknown kinematic parameters, but we will estimate those from the visual key points. So to the first part, the key point detector that we've trained follows roughly this autoencoder setup where we go from image projected down in some visual feature representation, then bottlenecks it through key points, and then tries to reconstruct the image from these bottleneck key point frames through another ResNet, basically. And what we've done here is to infuse the visual feature map with a kinematic feature map. So just a Gaussian plot around the estimated end effector position given the joint state configuration. So basically we measure the joint state of the robot, we use the differentiable robot model to predict forward where the end effector is and create a visual feature map. We fuse that with the pure visual feature map and then predict key points from there that are used to reconstruct the image again. And here is a quick overview of the results. What we're measuring is basically the error in predicting the center of the object. So how close are the key points to the center of the object? Lower is better in this case. And we've done this for different amounts of key points and for different objects. And so this is what you see here, the multiple graphs. You can see for all of the tests we've done, our multimodal key point detector works better. Another interesting test that we have actually done is do we need the proprioception for all the data? What if we only have a subset of data that we've collected with proprioceptive information and the other set of data is passive data, for example? And so we wanted to test that at what point do we lose accuracy for the key points? And you can see if 100% of the data has multi-proprioception, then we're doing really well. Actually, 75% we're doing slightly better, interestingly, on average. And then at 50% of the data being, so 50% means half of it is passive data without proprioception, and half of it is with the end effector projected into the image space, so with proprioception. Then we start losing some accuracy, but it's not as bad yet. But then at 25 and 0%, it goes up. Okay, So this was basically about improving the key point detector. And here is a typical output of the original key point detector that we used, where some of the key points just fell on the robot or, on some wall. And this is what our key point detector consistently detected. All right, so now, as I've mentioned, the dynamics model, the key point dynamics model, which is really a kinematics model, is extremely hard to learn. Or I should say, it's easy to learn in neural network. It's just really hard to learn a neural network that generalizes. And the approach that we're taking here is, well, let's take our differentiable kinematic model of the KUKA arm here, and we attach an object that we say has as many links as we predict key points. So for each key point that we're predicting, we assume there's one link in this attached object. We just don't know where, what the length of these links are. And now what we're going to just do is assuming we have, so we have also depth data, which will give us 3D position of these key points in the workspace. So we assume we have camera calibration. We can now actually just regress these link positions by projecting forward what the current position would be. So we initialize this with some length, and then we predict forward what would be the position of these key points in the visual space. If this were the length, we compute the difference to the actual key points predicted from the key point detector, and then we minimize the loss and adapt these positions and the link lengths through that. And then once the loss has been minimized enough, which means close to 0, we will lock it down, these key points, and that will then be our kinematic / key point dynamics model. And so this is what we did here, and you see these are now, we show this in red because once we estimated these link positions, which reflect our visual key point dynamics, we actually fix them and we don't adapt them online anymore. So they stay robust, they stay fixed. And when we do this and use this with our learned reward function, so we can use this also to now learn a reward function. When we use this extended body schema / kinematic chain versus a neural network, these are sort of the results we see. So in orange, you see this is the predictive performance of the kinematic model over time. The time horizon for this task is 25 high-level steps, so to say. And in orange, you see the predictive performance of the extended kinematic chain. And in brown, purple, and red and blue, you see the predictive performance of neural network configurations. We've tested different combinations where some of them are the 2D key points and action predicting to the next 2D, and some of them are you taking the 3D key points. And so you see that this, the extended kinematic chain outperforms all of them. Yes. And the numbers reflect this as well. And we did this evaluation on hardware as well, and the errors remain small with the extended kinematic chain. So this transfers very well. So we did evaluation and simulation, and then we transferred this to hardware, and this performs really well on hardware as well. All right, so far I've used structure as an inductive bias for generalization and sample efficiency. And structure here for me is really both the kinematic chain, but also just thinking about what visual representations we want to use, right? Key points here are a nice visual representation that are interpretable. And so this makes life easier when working on hardware. And so both of these sort of helped with generalization and sample efficiency on hardware experiments. I don't know if you've noticed, but there were no, to repeat the task on hardware, there were no, like once we learned the cost function, which required the demonstration, we didn't need rollouts in real life or trials to actually repeat this. The only thing, I mean, the only caveat is that we do need the dynamics model, and that needs data, right? So yeah, so basically this first half or first 3 quarters really focused on structure and how we use that to get there. But then more recently, I've shifted my focus on, well, how can pre-trained representation be a bias for robotics? Specifically, I think, how can we pre-train representations that generalize for all kinds of tasks, right? Going back to my big vision in the beginning, I think about all tasks that I want a robot to be able to do. Can we pre-train specifically visual representations that are useful in all of these scenarios? And we call this Cortex, and the inspiration really comes from what we see in computer vision and natural language processing, where large scale foundation models are trained to perform all kinds of downstream tasks. And the question is, can we achieve the same? Can we pre-train a visual representation that is useful for all kinds of downstream tasks? So this is a very new project, and I just wanted to give you a glimpse at where we're at and discuss this in the context of biases for robotics. So what does it mean, pre-trained visual representations for robotics or embodied AI? It means that we want to pre-train a visual encoder from data that is offline data. That visual encoder is then used to project the image to a low-dimensional latent space. In my previous work, this was key point representation, and this is still open for discussion, what this really should predict. But let's say it's just some latent space right now. And then we have a policy that takes this input, the latent space as an input, and predicts an action. And the policy is then trained either from demonstrations, so via imitation learning, or through reinforcement learning. This is gathering a lot of excitement right now, this direction. So we see work from within Meta AI here on the right side, but we also have work, of course, like from like Berkeley and OpenAI in these, and also DeepMind in the same direction, and many other places that I haven't put on here. So there's lots of excitement, but I don't actually know or see yet how well this generalizes specifically for robotics tasks. So how the question of can we learn pre-trained representations that generalize across many different robotics tasks is still sort of unanswered. So the current efforts are fragmented. We have various pre-training algorithms. We have evaluation on different downstream tasks. We use different approaches, behavior cloning, reinforcement learning, and then with or without fine-tuning of the visual representation. And so as a result, the results are not comparable, and it's unclear where we are with these pre-trained representations. And really, our goal should be to train one visual foundation model for all robotics tasks, if feasible. And our initial milestone with this work was to create a comprehensive evaluation benchmark of current visual representation learning approaches, where we take up to 5 pre-training data sets. We focus on trajectory data sets. We then have multiple visual representation learning algorithms that we evaluate that train a visual representation that is then used to train several downstream tasks, which I'm going to introduce in a second. We have currently 20 plus benchmark tasks, which we're also working on. And then we collect the results, and then we see how well are we performing compared to from scratch learning if we were to learn the representation from scratch. Two of the data sets that we're using are Ego4D, which are trajectory videos of humans performing like everyday tasks, and then HGSP, which is sort of a navigation data set. And then one of the questions, of course, is, so I never forget the question of bias and structure. As some of you may know, I have some prior work also on how to infuse structure into loss functions, or how to infuse bias by using structured loss functions, for example. And so this is how I think about how we can infuse bias into these pre-trained representations, which are pure neural networks. Most of the work currently uses frame level encoders, meaning you take one image at a time and predict one latent representation. For two examples are masked autoencoders and MVP. But in robotics, we typically deal with trajectory data. So we have actually temporal information. And so we can use that temporal information through, for example, including it into the loss function to pre-train these representations. And then we have this other end of the sort of the other spectrum, which is unstructured, which just takes in all the frames into one encoder and predicts one latent representation. And the results that I will present in a second, they are focused on the first two right now. The downstream tasks that we're looking at are several. Our guiding principle is that we want to have diverse, challenging tasks in embodied AI, some of which also have a real-world equivalent. So we have the habitat navigation tasks, we have deep mind control tasks, we have dexterous manipulation tasks, like the Adroid dexterous manipulation suite. And then we also have the tri-finger manipulation tasks, both in simulation and on hardware, though for now we're focusing on the simulation tasks. We've done a large empirical study. From what we know, this is the largest empirical study to date to pre-train on 3 video data sets totaling over 4,000 hours, and are on track to actually make that 5+ data sets. We've evaluated more than 10 self-supervised learning algorithms, including new ones developed for this effort. And then we also have 20+ embodied AI tasks in simulation, which include visual navigation, tabletop and dexterous manipulation, legged locomotion, and these are across diverse simulation environments, Habitat, Mujoko, and PyBullet. And we plan to expand this to 50+ tasks in simulation. Okay, so what are our current findings? Can we pre-train representations that work well for all of these diverse tasks, right? Can we actually achieve generalization? And I have to say, I learned that in fact we can pre-train visual representation that match or outperform from scratch in domain learning. And this is true for all tasks. So this was something that was not necessarily clear to us in the beginning, but in fact, we have results that show that this is feasible. And this is without fine-tuning the visual representation. So we are just pre-training the visual representation on these data sets that I showed you, and then we're using them to learn the policies and for all of the downstream tasks, one policy per downstream task. Another insight that we have is that increasing the diversity of pre-training data sets improves performance of the frozen pre-trained representation. And then we also see actually signal, I forgot to put this, that including the temporal information can help. But I don't have like a very clear statement yet. That's why I haven't added it. And then fine-tuning the visual representation can further improve performance. It does depend how much performance improvement we see, if any, depends on the simulation tasks. So we primarily see performance improvement for the visually complex tasks like the habitat navigation tasks, and not so much for the visually more simple tasks. All right, and that's kind of it for this part of the talk. We will open source this very soon, so stay tuned. And yes, and that was my talk. None of this work would have been possible with a lot of help from many, many people. And so I just tried to give an overview of the team here.
Thank you, Francisca. Do we have maybe one question from the audience? Yeah, please go ahead. Probably if you don't mind. I mean, I could also. So, Francisca, I'm not sure if you get that, but so they're asking here, like, if you could elaborate on how you actually pre-train these models.
The visual representation, yeah. So they are basically, we take offline these data sets that I've shown, and then we try different self-supervised learning algorithms like masked autoencoders, R3M. So we actually take existing algorithms, VIP, and then we pre-train them in this self-supervised manner. Basically, they're autoencoder, sort of autoencoder frameworks, or contrastive with contrastive, or masked autoencoder losses. Does that answer your question?
Can you say it again? So could you tell us which method works best, at least in your experience?
Yes, what I'm currently seeing, so these are initial results, so take this with a grain of salt, but what I'm currently seeing is that we see on average masked autoencoders performing the best.
All right, thank you, Francisca. So let's thank the speaker again. All right, so I guess we can move on to the next and final talk of this second session. So I guess we can set it up here. In the meantime, I will introduce Kelsey. So she is currently a research scientist at DeepMind. She holds a PhD from MIT, carried in the computational cognitive science group. And she also got a bachelor degree from the University of British Columbia in physics. So now we're setting it up.
I'm Kelsey Allen. I'm a research scientist at DeepMind, and I'm excited to talk to you today about relational inductive biases for simulation and innovation. And this is going to be a little bit different from the prior talks because a lot of it's going to focus on actually tool creation and things that we think of as generally very human-like abilities, both for robots and also for animals. So tool use and tool innovation are really critical to a variety of different kinds of human reasoning. For example, you can imagine using stacks of books to try to make table legs if you happen to not have wood, right? Or you can do very flexible different kinds of phone games, like some games we developed in my PhD, or if any of you have played this very fun phone game, Happy Glass, you have to draw a tool in order to reroute some fluid into some kind of container. These are extremely flexible processes that happen almost every day in our various lives. But the ability to create tools is also central to engineering, innovation, and robotics, right? We do things like create entire landscapes to assist with activities like irrigation that totally transformed our societies. Or we've created some of our most modern tools like airplanes that allow us to cross the globe in a matter of hours, especially to get somewhere as far as New Zealand, for example. And so the central question that I'm going to be addressing for most of the talk, although stay tuned for the end as well, is how can we create machine learning models that can do these kinds of very interesting human kinds of processes? They can use tools, can they create tools in 2D or in 3D, and even do things like engineering level precision to assist with things like airport wing design. So the way that we're going to tackle this is to try to use a very general framework. And so I'm going to describe that to you now. So we have just some initial way of setting up our scene, which is governed by some parameters alpha. Now here in this running example, I'm going to show you alpha could be a pipe on the wall from which water is going to flow. We then have some design function that takes in a set of design parameters phi and creates some initial scene. So here, for example, the design parameters phi are representing the height map of a landscape that we're trying to optimize in order to do something useful. That's going to create an initial scene that here we're calling GT0. We're then going to run some simulator on that initial scene over many time steps until we get a final scene that we're going to compute some reward function on. This reward function can be parameterized by parameters theta r, for example, which in this case is indicating pools that we want to direct water into. The design optimization process is then very simple. You just start with some initial random parameters phi, and then at each iteration, you run your simulation, get a reward, backpropagate, or do some other kind of optimization to improve your design, etc., until you get a very nice design that's solving your reward, getting very high reward. So now I want to get to the sort of meat of the talk, which is how do we design this forward model FM to allow us to do these very complex kinds of tool innovation and design tasks. Now we're going to use graph network simulators. And there's a variety of reasons why we want to use GraphNet simulators. The very first one is that they just work for many different types of physics. So I'm showing you a variety of those things here on the left. They work for things from as complicated as a bunch of rigid objects of very different kinds of shapes being tossed together in a scene, to different kinds of fluids and different materials, to even very complex engineering kinds of simulations like wind flow or structural mechanics and deforming physics. They're also efficient, accurate, and very stable for forward prediction, as a variety of prior work has shown. They're also critically differentiable, right? Because they're represented as neural networks, which might permit us to do very complex kinds of gradient-based design optimization, which would be very helpful and nice. And most importantly, they generalize well, right? That was a critical thing from the previous talk about how difficult it is to make networks that generalize. Graph networks can do that really, really well. So let me show you an example of that. Here is a graph network, and what we're seeing is training, the training domains in the little insets on the lower left and upper right, and then the generalization domains that you're seeing is the big picture here. So for example, in a wind case, you can train on a single cloth flapping in the wind and then generalize to these sort of wind flag tunnel type things with no fine tuning whatsoever. Similarly, in these fluid cases, you can train on just a block of water interacting with just 1 to 4 line segments, and then generalize to these crazy sort of fluid maze situations really, really well. What that allows us to do is to now think about pre-training graph neural network models on very generic kinds of dynamics data that have no task information associated with them at all, and then using them directly for different kinds of example design tasks, like I'm showing here on the right, where you have to get the fluid into this yellow region by optimizing these different tool shapes. So how do graph neural networks actually work? I'm going to give you a very brief primer on this. So graph neural networks are composed of 2 kinds of functions: edge functions represented as FE and node functions represented as FV. Here, each node is indicated by V. So VI is representing the feature vector for node I, and EIJ is representing the edge that goes from node I to node J. So in order to embed our edges into a higher dimensional representation and take advantage of the graph structure, this edge function FE is going to operate on the edge that it is operating on, as well as the node representations that that edge is connecting. And that same function is going to be applied to all of the edges in the graph. So this can handle graphs of arbitrary sizes. The node function, FV here, is going to take the current node representation as input, as well as the summed representations of all of the edges that come into it. And again, this can be applied to all of the nodes independently in the graph. What's nice is that we can apply these 2 functions iteratively, and this allows us to propagate information across our graph. In our case, for these kinds of physical dynamics models, each node is going to be a particle or mesh vertex, and the edges are going to join nearby particles and vertices and convey relative position information, which I'll describe in a bit more detail a little bit later. So now that we've talked about how we're going to represent this FM simulator, I want to talk briefly about the different kinds of ways we could consider this design optimization process. The first is to do gradient-based with handcrafted models. So this is a very popular method, both in robotics and in engineering more generally, where people spend quite a bit of effort, right, paper level effort, to design a differentiable simulator that you can then use the gradients of to do system identification or planning or a variety of other things. The benefits are that it's analytical and you know exactly what it's going to do. The downsides is that it can take a lot of time to actually make these things work for different kinds of dynamics data. And so we might want something that's a little bit more generic. The option that is sort of in between now is that we could try to learn those models, right? We could try to learn a differentiable model like a graph network. And this is a much more generic approach where we just need data to learn from, but it still permits these nice gradient-based optimization procedures that can let us do a bunch of cool things. The alternative is that we could also just use sampling-based techniques, right? So this doesn't require a differentiable simulator anymore. All we have to be able to do is run our simulator forwards and then do some kind of population or other technique like Bayesian optimization to find our different design parameters. So in this particular paper, we looked at one example of each of these different representative optimization cases. For the gradient-based with handcrafted models, for airfoil wing design, it's very common to use this defoam optimizer, which was built in 2020. We're going to just look at, for our GraphNet procedures, gradient descent with Atom through our learned GraphNets. And finally, we could also look at the cross-entropy method, which is a very popular population-based sampling approach for any kind of black box forward model that you want to use. So now let's look at how well these things do for a variety of different tasks. So first, I'm showing you our simplest environment, which is just this 2D tool creation environment, where the goal is to get the blue fluid into the yellow region. And what you're seeing is the optimization process unfolding for this gradient-based optimization through the learned GraphNet simulator. And it does a really nice job of finding different kinds of tools like containers or ramps or funnels with not too many optimization steps. Again, this is all just optimization. There's no more learning going on here. By contrast, this population-based sampling procedure, the cross-entropy method, finds much less both just worse designs overall and much less globally coherent ones, right? So the containers it finds kind of work, but they don't look particularly smooth. The ramp that it finds totally fails. And the funnels, again, they don't naturally funnel things into the right space. Instead, they're sort of a random collection of line segments. If we look at the overall reward of these different approaches, then we can see across all three of these different environments, the gradient based through the learned model outperforms the cross-entropy method here. But perhaps more surprisingly, it still outperforms the cross-entropy method, even when the cross-entropy method has access to the ground truth simulator for optimization. So this suggests that learning a differentiable simulator as a graph network, the gradients are actually preferable to even having the true simulator if the true simulator doesn't have gradients, which is kind of interesting. So then we looked at trying to dramatically scale up our different design optimizations in this much more complex environment where now we have thousands of particles as well as an extremely large design dimension space in order to optimize it. So again, here you need to optimize the green landscape to reroute the blue water into the different pink regions. And what we see is that the gradient descent model through the learned simulator is outperforming this sampling-based approach by actually 1 to 2 orders of magnitude. Especially basically because it can do these globally coherent optimization procedures as opposed to having to sample things independently and randomly. And finally, for this section, we looked at how well these things could do for this extremely difficult engineering design optimization case of trying to design an airfoil. So here what you have is an airfoil and you're trying to design its shape such that it has high pressure on the bottom, low pressure on the top, such that it has high lift and reasonably low drag. So this is the solution that you get from the defoam optimizer. Blue is regions of low pressure and yellow is regions of high pressure. And the reward that it receives, you can see on the right-hand side of the screen as this dashed orange line. Now, if you just try to optimize through a single GraphNet simulator, that's designed to try to, that's trained to try to predict regions of low and high pressure, you get pretty good reward, like pretty close to defoam, but not quite there. And what you can see is that the shape, if you switch between these, does vary a little bit. In fact, it has a little bit higher drag. But if you use an ensemble of GraphNet models, where each model is trained on a different subset of the data, you can do just as well as the defoam simulator, and you get very comparable designs, which is really nice. Not only that, but this approach is actually 16 to 48 times faster on a GPU than defoam on an 8-core workstation, suggesting that we could really speed up different kinds of engineering processes. Some other sort of surprising facts about these GraphNet simulators. One is that they have stable gradients over extremely long rollouts. So here we designed tasks that you either looked at the reward after 75 time steps, after 225 time steps, or after 300. And the solutions from this gradient-based optimization procedure continue to improve up to 225 time steps, and they outperform the sampling-based method all the way up to 275 time steps, suggesting that their gradients are really stable and quite robust. There are two sort of crucial properties to these graph networks that allow them to work so well for design optimization, which we investigated here. The first is translation equivariance. So critically, in these GraphNet representations, you can choose to put node features inside nodes, or you can choose to put edge features inside edges. Now, one feature that ends up being important is the position of the particles. If you put the positions of the particles into the nodes directly, that's the absolute thing on the right here, then you don't have translation equivariance. That means if you move the entire graph somewhere else in space, the features are going to change. If you instead represent the relative positions between nodes in the edge vector as xi minus xj, now you can move the entire graph network anywhere around in space, and it will see exactly the same features. And so it should generalize essentially perfectly. The other thing that ends up being critical for these kinds of, for training these things to be robust to different kinds of rollouts is to add noise during training. So this adding noise during training, what that means is that we take the particles in the fluid and jitter their representations with just some Gaussian noise. And then the next state prediction is unjittered. And this allows the model to be robust to small changes that might arise during rollouts so that it can still have reasonably accurate forward predictions. If you remove either of these components, so you remove the noise injection in red or the translation equivariance in purple, you do not get a model that you can actually use for design optimization. So both of these things are critical to enabling the graph network to work well. Perhaps like the most surprising thing about this is that the learned models actually sometimes produce more physically realistic rollouts than the ground truth simulator. So what I mean by that is that in this simulator, it was not this analytical simulator that we used for these fluid prediction problems on the left here was only ever built to handle just like 16 line segments. If you use 36 line segments, it can have this very weird behavior where the fluid can get sort of artificially stuck and shows this sort of viscous property that isn't present in the training data. By comparison, the learned model actually looks more realistic for these cases. And that's because it was only trained in regions of the simulator that the simulator works well for, which is the 1 to 4 line segment case. So it learns just the correct relative physical rules and is actually better at extrapolating that than this analytic simulator, which is surprising. So to conclude this first part, these graph neural network based learned simulators support general purpose design over very complex physical domains. This task agnostic training on data still permits this very out of distribution design. Their gradients are useful over hundreds of time steps, and they can even match the accuracy of these specialized engineering solvers for airfoil shape optimization in just a fraction of the time. Now, I just want to dig in a little bit now. If you were thinking like, okay, this is interesting, but this isn't really roboticsy, I'm going to get into that now. And specifically, I'm going to get into this question of learned models can produce more physically realistic rollouts. Is that actually true? What does that mean? So, oh my gosh, that's loud. Okay. I don't know if anyone in the audience is familiar with this paper, but I thought it was really cool. It's from Frommer and colleagues at CoRL 2020. And what they did was oh my God. I don't know how to get the bouncing to stop, so I apologize about that. What they did was they recorded the position of a cube being tossed on a real, how to make sure. Oh, here is this possible. There we go. Okay, perfect. No more weird thunking in the background. So they recorded this cube being tossed onto this table, this real world cube. And in a follow-up paper, they looked at, from Acosta and colleagues in this year's IROS, they looked at how a variety of simulators could actually capture that real world cube toss. So this is Drake, with system identification performed on a variety of the cube tossing data shown in blue, with the re-rendered real trajectory shown in gray. And what you'll see is that Drake is really not doing a very good job at predicting this, what we should think is a reasonably simple problem of tossing a cube onto a table. So we were interested in whether graph nets could actually capture this better than analytic simulators for real world data. And what we found was that yes, they could. So what I'm showing you here in the black dashed lines is the performance for positional and rotational error of Mujoko, Drake, and Bullock. And then in red, I'm showing you contact nets, which is a hybrid simulation that combines deep learning and analytic rigid body dynamics in red. And in blue is our GraphNet simulator. And we looked at how well the GraphNet simulator could match a held out set of real world trajectories based on training on only a subset of the training trajectories, so between 4 and 256. And what you'll notice is that, first of all, for position, Mujoko is just not doing a great job here overall. The GraphNet simulator very quickly surpasses that. But even with as few as 32 trajectories, the GraphNet simulator is actually doing a better job of predicting the rotational error of this simple cube toss relative to these different analytic simulators. And by 256 trajectories, it's reducing the error by almost 2x. If we look at some of the re-rendered trajectories here, where here green is the re-rendered real cube trajectory and blue is the graph network rollout, we can see why these numbers look so good, in that the GraphNet is capturing very, very closely exactly the behavior of the real cube on held out test trajectories. If you're going to complain at me that that's just a cube, then I have one more fun data set for you here. This was a data set collected by you and colleagues for a 2016 paper at IROS, which is frictionful pushing. So here there's a robot tip pushing a variety of 11 different kinds of objects along 4 different kinds of surfaces at a variety of different speeds. Now this is challenging because friction is pretty difficult to model and to measure. And so, and beyond just friction being difficult to model and measure, you also have state estimation errors. So what I'm showing you here is a re-rendered trajectory from that data set, where the blue circle is the tip and the red object is the thing it's pushing. And this is re-rendered, so this is what the state information looks like. So if you see that, it basically looks like the tip is moving the triangle without actually touching it, right? The second case, the blue tip is clearly penetrating the object. And so this object in analytic simulators would simply fly away, right? So these state estimation problems can cause really big problems for analytic simulators. Now, how does the graph network do? First of all, it does a pretty good job at predicting how the objects will move. So here, the gray dashed line is the initial state of the object, with the blue representing the GraphNet's final prediction, and the gray representing the true final position, and the small cylinder representing the movement of the tip, with the arrow being the direction that it's going in. So it's qualitatively capturing this very nicely. But quantitatively, it's also doing a really, really good job of predicting how these objects move relative to analytic simulators once again. So I'm showing you here how the error looks relative to no movement, because these objects move very little. So if we got 100% error, that would be basically predicting that the object doesn't move at all. So any improvement above that is saying the object is moving in the right kind of way. And what we see here, the GraphNet simulator in blue is outperforming any of the analytic simulators with as few as 128 trajectories. And keep in mind, these 128 trajectories are randomly seen across 11 objects. So that's only about 10 trajectories per object. And it's already performing better than these analytic simulators doing system identification with a much larger portion of the data set. At its most, it's getting around a greater than 2x error reduction. So to conclude the second part, these GraphNet-based simulators seem to outperform analytic models for fluids, for these real cubes, and even for robotic pushing along different kinds of surfaces with friction. Towards the future, we're very interested in a variety of problems, both within robotics and more generally design. I'm particularly interested in trying to think about how to use GraphNets to do more sustainable design for things like windmills or fire breaks. We're also very interested in doing different kinds of joint design and control, where you might have to jointly design a robot's body as well as a policy for using that body to succeed to do something, or designing and controlling different kinds of tools to solve a variety of different tasks. And we're interested in looking at more complex design spaces, things like compositional design, where maybe you have to make an espresso machine, and then you've got to compose a lot of different parts, or very abstract designs like circuit diagrams. How do we deal with that? So with that, thank you very much for listening. Sorry for the technical troubles to get started. I hope the videos were at least fun to watch. I'm happy to take any questions if there's time.
Actually, I was wondering if you had evaluations that can give a bit more insights. How did you do that? Were there random examples that you generate over the model form? I was thinking, are there corner cases where the analytical models are so much better than the graphical network with the short effort?
Yeah. So actually, no. When I'm just showing random examples. We didn't cherry pick them, but we did not find, I think, even a single test trajectory that looked better under the analytic simulators. At best, they look the same. And if you're interested in this, we did a much more thorough evaluation in this. Actually, the graph network simulators can learn discontinuous rigid contact dynamics, which is a paper here at CoRL that we're presenting on the last day. So feel free to come chat with us there, and we could talk a little more about that.
Thank you for the great talk. I was wondering for the last one, how would the comparison with like the differential, an actual differential simulator? I don't know, not using that or any of these.
Yeah, so we're actively looking at that. I'm particularly interested in comparing to this new one, Dojo. I don't know if you've seen it. I think so far the gradients for particularly these rigid body dynamics models that I showed here with the cube in particular, the gradients are not that good at the moment. So we tried some initial optimization tasks with those and they didn't work particularly well, but I don't actually know if Dojo has shown really compelling like control tasks with these kinds of very complex rigid contact dynamics either. So I think it would be a very interesting thing to look at, and more generally, a very interesting question of, can we train these things in ways that give us better gradients for optimization, right? So like different kinds of smoothing procedures or something in the training that might make them more useful in comparison to those differentiable simulators. But it's a great question, actively looking at it.
Questions. So the first question is like, have you seen how the graphical network simulators perform on the distribution data? This all within the hello samples that you have, are still in the data distribution issue? And I guess the second question is, do you perhaps consider training the networks like end-to-end, including the optimization? Like in the sense that they're trained with the objective being like the required optimization.
Yeah. So to answer your first question, these are super out of distribution design. So out of distribution tasks. So for these cases that I was showing between like these 2D and this 2D fluid tools case here on the right, what you're seeing on the left is the training data, which never has any curved line segments at all, and never has more than 4 line segments at all. And then these test tasks are 36 line segments and curved line segments. So it's really dramatically out of distribution, actually, like quite astonishingly so. For the other, oh my God. Okay. For these ones, we just used the data set that was available from Frommer and colleagues in their contact nets paper. So they're not out of distribution per se. but we looked at various things. We did again, if you're interested in looking at some particular out of distribution cases on this, come talk to me on Saturday. I'd be happy to chat more. To your second question, one thing you could naturally do is actually fine tune the GraphNet model during optimization to try to optimize it for the particular task. We tried a little bit of that, but didn't see any advantage of it in our initial investigations. But I think it would be particularly critical if more dramatic things were changing potentially in the dynamics between the training and the test cases, not just like the viscosity of the fluid is changing or, you know, something like that. But thanks very much for the questions.
All right, thank you, Kelsey. It was a pleasure. All right, guys, so I guess now we'll go for the lunch break and also the outcome for the opening session. We're going to be back here at 3:30 p.m. I guess you can start. All right, so we have our next speaker of the last three today. Before we go into the panel discussion in the end, we have Joseph Lim here today, who is an associate professor in Korea, and he was previously also an assistant professor at the University of Southern California and has a PhD from MIT, and also completed a postdoc at Stanford University, and also held several positions in the industry setting. And I leave the stage to you now.
All right. Okay. Thanks for the introduction and invitation to the workshop. Yeah, it's actually very exciting to be back to online or offline this talk now, finally. So today I'm going to talk about skill-based robot learning. So let's first watch a video here. In recent years, as we all know, we have seen hardwares performing very well, even beyond human level in some of the tasks, right? And also, it's also the same thing applies to the learning method as well. So including reinforced learning method as well. So leveraging this, our goal is how to actually solve long horizon complex physical tasks, which is of course hard. And the reason behind it is, so at least one of the reasons behind it is, if you think about it, the long horizon tasks actually come with huge variations. For example, there is task variation and also environment variation, and as well as this agent variation as well. So this high complexity and variation coming out of task is actually the reason the humans, of course, cannot manually hard code everything, but also this applies to the learning method as well. So learning method suffer from this complexity issue and effectively sample inefficiency issue. And this problem gets even more severe because we often treat individual tasks very independently out of other tasks. And also we are doing data collection in a usually more online manner per task, right? But so if you think about it, humans also have the exact same problem, but we don't have as much of issue as a robot learning problem algorithms. So why would that be? So how about humans, right? So of course, humans learn from our prior experience, right? Even at the kid level. So we can actually utilize our experience when we were younger. And also, we can also watch other people doing it. Basically, we can learn from demonstration of others as well. And even not just object manipulation, even for completing cooking tasks, right? So even if it's a new kitchen, right? We can actually utilize and exploit our knowledge based on our prior experience or even other people's demonstrations. So in other words, offline data and experience. So how can we make an agent that can transfer this offline experience just like humans do? So in other words, transfer information from previously learned task to our new task that we want to be able to solve. So in other words, how do we make this prior experience reusable and curatable and even shareable? So there are many different methods and approaches around it. In other words, how to reuse the data from priors, right? So of course we can learn models, as many people do, and also we can learn shareable representations and all whatnot. But also, specifically in today's talk, we're going to talk about how to use this learned reusable skills. Okay, so we are going to focus on this skill today. Again, skill-based robot learning for long horizon physical task. So when we are talking about skill-based learning, there are effectively two components. The first component is how to get all these skills from various sources of data, like predefined, human, manually predefined skill set, or maybe from our offline experience, or maybe even external knowledge like language, etc. too. And then the other component is actually how to relate these skills to our downstream task, in other words, our target task effectively, right? So all these things utilizes many techniques like meta learning or reinforced learning, or even large language model, etc. And for today's talk, I'm going to go over a few of the works that I have related to this, okay? So let's first talk about utilizing offline experience. And if I have time, I will go into this predefined skill set or external knowledge, but probably I will mostly spend most of my time on this utilizing offline experience, okay? So in terms of our first work, essentially accelerating reinforced learning with learned skill priors. This work was led by two of my students who are just graduating, CoRL and Youngwon. So they're in the market. So if you see them, you can say hi and try to recruit them for whatever. Okay. So but anyway, before going into technical details, so let's first watch the video here. Okay. So here's a video. So of course, probably I assume none of us has been to this room here. But even though we have never been to this room, we can actually walk around and already execute. We can imagine executing many different skills. For example, entering building, opening the door, making a left turn, a right turn, or even traversing hallway, and even actually climbing up and down of the stairs, right? So, okay, that's good. So we actually learned the skills from prior experience, so we can execute them here, but they're actually a little more than that, right? The hint was already in the title, so we can actually utilize some prior knowledge. So what does it mean? So when we got to this point again to the point that we have never been around, but I'm pretty sure many of you already know, we can make a short left turn here, and we can also make a long left turn here. But also at the same time, even though you're exploring first time into this house, basically if you're imagining you're a reinforced learning agent, even though it's actually your first time exploring this space, how to navigate the house, I'm pretty sure none of you is gonna turn right here because you're gonna just bump into the wall, right? So we already have this prior. Right. So how can we actually utilize this prior knowledge of when is good to execute its different skill, or when is not good to execute its different skill? Is this the main focus of this project here? So in short, again, given this many different types of offline data from this prior experience, we can of course extract skills from it, right? So that's also already something we already knew. But the main contribution of this talk is how to get actually this prior over skills. So in other words, just like this house example, when we're in a situation, you're not going to turn right because you don't want to bump into the wall based on your prior information, right? This also applies to other places, not just a house, right? If you're in the kitchen, right, in the new kitchen, first time, and you see the first knife ever, okay, but you still will not throw the knife, even though you of course have a skill to throw a knife around, right? Because we know that's unusual as a skill, it's probably dangerous and unsafe to do it. So knowing how to do doesn't mean we are necessarily gonna explore them, right? So that's the key message here. So what we do here is that we have large offline data set like this, okay? From this large offline data set, we can extract skills, okay, which are reusable. So this is basically task agnostic offline data set. And from this task agnostic offline data set, we extract all these reusable skills. And then we also extract the skill priors, as I mentioned. So when is good to execute each different skill and whatnot at a time. So we learned this skill priors. And now we have this skill set and also their priors, right? We apply to the reinforced learning algorithm later on for the target task we want to obtain. Okay, and I'm going to talk about how we can do that a little bit now without too much details. Okay, so here it is. So we are given a trajectory, demonstration trajectory here, okay, of some lengths. So what we do is we sample a sub-trajectory of the length h, okay, when we call it as a skill, right? Because any subset of any sub-trajectory can be called as a skill here. So we sample a skill here. And then we encode it and decode it back. And then we basically, our goal is to learn this skill space, a skill embedding space, Z here, right? So we have subsequence of actions, and then we embed it and we can decode it as well, right? So basically that gave us a skill posterior, right? Given this all large amount of data set. Now that we have it, so we are also can extract this skill prior I also talked about. So what we do is that skill prior is conditioned on the state, the current state. So given the current state, how good or how likely is this skill important or useful is what information we are extracting. Just again, just like earlier, some skills are more meaningful and some skills are not as meaningful or maybe bad to perform, right? So this is what we acquire from this task agnostic data. So now that we have extracted this skill prior and skill encoder and decoder, what we do is we go to this downstream task learning. Okay, so it's the same thing as it's a typical stereotypical reinforced learning here. So you have an environment and you have a state, the current state. So what do? We train a policy, right? We train a policy that predicts what action to perform. But because our goal is to do skill-based reinforced learning here, instead what we do is we train a skill policy. So instead of outputting what action to perform, we predict which skill to perform at this point. So we call it skill policy here. And now that we predict the skill, what we do, we can actually apply skill decoder and unwrap this action sequences and execute in the environment. So if you look at this, this is basically skill-based, standard skill-based reinforced learning. So you have skill policy that predict the skill vector, and then you actually decode it, and then you generate action sequence out of it, and you go to the environment, and then you make a loop, right? But okay, so this is a standard skill-based reinforced learning, and what we add on top of it, as we talked about again, is which skill is good to explore or not to explore at a given time, and at the exploration time. So again, I wouldn't throw a knife, even though I can throw a knife, right? So that's basically something we wouldn't do, even at the exploration stage. So we apply here. So we actually add this regularization term here to the skill policy. So the skill prior, given a state, tell me, okay, should I draw a knife now or not knife, right? So that's basically what this skill prior is trying to regularize for me, even based on all this task agnostic data that we have, which is not exactly directly at least related to the target task we are performing. Okay, so that's basically it. And in terms of the actual implementation, we just have to change the 3 lines of the algorithms to the vanilla SAC. So self-vector creating method. Then what we just add is a KL divergence between the policy output and this skill prior, and that actually complete this algorithms. So we evaluated this in 3 different environments, like maze, block stacking, and kitchen. And we, of course, after we train from this training data set, we have to we create a new target task in this domain, and we apply this downstream learning task and see how efficient it is. So I'm not going to show all the results here, but of course, it's just first thing in the maze environment. So given this random, so this is on the left side, I'm showing the skill prior, random skill uniformly sampled. So you can see it's a very noisy in the exploration stage. It's trying to all the random things. But when we have this skill prior, with this learned skill prior, we are actually making more situationally and temporally coherent sequence of actions or skills, right? And we also apply this to the kitchen environment. So in the kitchen environment, we tested the soft-vector creating method again, but even with after a million iterations, it doesn't really learn to make any meaningful action sequences. On the other hand, our method on the right side, you can see it actually can open the microwave or moving the kettle, turning up the oven up and down, and even slide the door as well, right? And quantitatively, it's also, you can see that our method in the blue curve here makes outperform all these other baselines we had, okay? All right, so I talked about, okay, so using task agnostic data, we can actually extract their skill priors and also extract their skills and then apply to downstream task, okay? So this is what this was about, what the spiral was about. So then the natural question is that all we can do with the skills? What else can we do, right? So we have done various different things, but in today's talk, I'm gonna go over a very quick overview over how we can actually use this learn the skills together with meta learning, or even learn the skills for imitation learning. And on top of it, how can we actually abstract out of a action space dynamic model to the skill dynamic model? Okay, so first thing is how can we actually utilize this skill set for imitating demonstrations? Okay, so if you imagine yourself trying to imitate other people, so when we are a beginner, when we don't really have much information about the task, what we do is we just try to imitate at the very primitive action level, literally just controlling your finger to imitate all the other people's experts' demonstration. But what we propose is that as we get more advanced, more expert agent, what we can do is we would actually imitate the skill level at the abstraction level, rather than trying to follow at every primitive skill set, right? So what it allows us is, the goal of this is that so that we can, by utilizing this abstraction or imitating skills, we can actually use this fewer demonstrations for longer horizon tasks more efficiently. So simply, again, going back to this spiral framework, okay? What we can do is, what we are given now is that we have this as task-specific target demonstration, okay? So earlier we were dealing with task agnostic data. So now in this case, after we have all these skills and priors extracted out of task agnostic data, we have this task-specific demonstration. So from this task-specific demonstration, we can actually use this demonstration and skills to get all these demonstrated skills. And out of this demonstrated skills, we can also, of course, get this at the end of the day, task-specific skill posterior. So remember earlier, we talked about skill prior, task agnostic skill priors, and now we have this task-specific skill posterior. So the question is, how can we actually merge these two things? Basically, one from task agnostic data and the other one from the target-specific demonstrations. And we apply this to downstream learning task, okay? So just very brief overview. We have this skill extractor we already talked about, skill encoder decoder, and there's this prior and posterior. So prior from the skill task agnostic data, right? And then there's a posterior demonstration specific task skill posterior, right? And we have this one prior and one posterior, and use it to regularize again our reinforced learning, downstream reinforced learning method here. Okay. So we use discriminator in this case, trying to make the policy to pick the demo-like skill rather than prior-like skill. Okay, so we do this kind of a discriminator-based reinforced learning, and the more detailed you can look at the paper later. So effectively, it outperformed completely on this demonstration-based imitation learning with the skills here too. So you can see the orange curve outperform all the other baselines too. And more interestingly, the main contribution, also another interesting point is that if you look at this, the area where we only have very few set of demonstrations, it actually, our method does work pretty well compared to the baseline. Of course, the reason is because we utilize this skill information, where this skill information was obtained out of this text agnostic data. Make sense? So yeah, skills help to learn even with a fewer demonstration compared to other baselines where where they don't exploit this skills information. Okay, so yeah, I talked about now how to use a skill prior or posterior from target demonstration. So now I want to talk about this, how to apply skill-based learning with meta learning. So skill-based learning, as much as I talked about already, the one advantage of it is actually it can we can make a fast adaptation from the scratch compared to many other methods. But at the same time, it still requires many samples for novel task. So now we heard this, okay, many samples from novel task, then what do? We apply meta learning. Why? Because meta learning is designed to be good at few trial adaptation, right? But one of the downside of the meta learning so far was that it was limited to short horizon density word setup. So taking advantage of both worlds, So we take this advantage of skill-based learning, which is behavior prior from offline data, and meta-learning's advantage, which is learning to quickly adapt. So then we combine these two things and apply to our method, which is we call it simple. I'm not going to go into any technical details here, but you can see when we merge this is skill-based approach with meta-learning, it again performed pretty well against all the other baselines here too. Okay. All right. So for one of the final part of this talk, not the final, but one of the last ones. So I talked about skill prior and also imitation learning and also meta learning. So this work, so now I'm going to talk about skill abstraction. So how do we actually abstract out of action space to the skill level, and we can actually do model-based RL in the skill abstraction level. Okay, so this work is actually the work that will be presented in poster tomorrow at CoRL. So if you're interested in more details, you can come to the poster, etc. But I'm just going to go over high-level overview here. Okay, so let's imagine making a pasta, right? So if I had to tell you, can you imagine how you're going to make a pasta? We are going to plan and think everything in abstract level. No one of us is going to think about how to move exact fingers and legs and all that, right? We actually think about the first thing we have to do is, okay, I have to clean the vegetables. And the second, now I have to cut the vegetables, right? And third, okay, let me turn on the oven and stove. And lastly, let me boil the noodles, right? So as you can see, this is kind of probably roughly how you're going to plan and think about making a pasta. So we can see that humans make and plan things in abstract manner for long horizon tasks, not at low level control level. So how can we actually make our agent to do the same thing? Okay, so again, going back to this spiral chart here. So we have task agnostic data and skill extractions and for downstream learning. So what we do instead here, okay, is that we learn this skill dynamics model. So often when we're talking about model-based RL, we often use action dynamic model, right? Single step imagination. But instead, we actually abstract out of it to the skill space, so we can actually plan and think model-based RL in the skill level, not at the low-level action level. Okay, once again, as an illustration, here is an example. So this is a stereotypical model-based RL, right? So I move a finger a little bit, and I move my finger a little bit again and again. So imagine what will happen after my finger movement at a time, right? So of course, this is very expensive computationally, and even worse, over time, the error will accumulate. So accuracy will be very low as well too, if you're trying to make a long horizon imagination, right? So instead, what we propose is that we utilize the skills again. So given a state, okay, let me open a micro, what will happen? And let me move my kettle, what will happen, right? So I imagine and think about things in a skill level. Again, I move kettle first, and then now I slide the door, what will happen, and again and again. And I pick whatever had the highest reward or score based on whatever metric we have. So what we propose in this work is that instead of planning everything in a single step model like this, right, in model-based RL, let's utilize this skill dynamics model. So given a state, we perform skill instead of actions to plan things around. Okay, so that was basically the basic motivation, and the details and everything you can talk to my students tomorrow in the poster. Okay, so yeah, I talked about spiral, simple, skilled, schema, everything wrap around this skill priors or skill-based abstractions. So the key here was the abstraction again. So for skill dynamics, priors, imitation learning, and meta learning, everything, it was all about skill abstraction and how to efficiently help the downstream reinforcement learning method here. Okay. So that's basically what I talked about, how to utilize offline data, offline experience, especially task agnostic data here. And I have we have a few other works and like with dealing with predefined skill sets or external knowledge. But for the interest of time, I'm going to skip them and jump toward the toward the end of the talk here, which I want to briefly talk about. So I talked about how to leverage skills, right? But one other thing we of course need is that how to benchmark them well. So in order for, especially for long horizon tasks, right? So we know everything in machine learning happened with large scale benchmarks. So in computer vision, we had ImageNet, then there was a CNN, and then there's a large language data, and there's a GPT and ChatGPT, you know, all these big works. So what should we do in robotics, right? So what can we do with robotics, especially for long horizon tasks? So for this purpose, we first released a simulator last year. So what we call this IKEA furniture assembly environment. So with a high quality, realistic, high fidelity simulator that's trying to simulate furniture assembly environments, okay, with many different furniture models, and also with many different agents, with different sensory inputs and all whatnot, so that we can simulate furniture assembly process. Okay, so this is what's good, okay? But of course, the problem with the simulator is it has a lot of domain gap, like dynamic gaps, visual gap, and also, you know, even some of the things we cannot really simulate well, like a screwing actions, for example, although we kind of deal with it now with thanks to NVIDIA. But anyway, so now the real question is, how do we scale this to the real world, right? So for this effort, this is actually in preparation for submission next month. So we are about to release this real world furniture assembly benchmark. The main goal was let's make reproducible real world benchmark, but just not limited to simple and short horizon tasks for longer horizons and skill-friendly environments, okay? So reproducible real-world benchmark for long horizon tasks with dexterous skills, with many different instances, and also providing some teleoperation data. So if you want to do learning from demonstrations, you are more than welcome to do it with some reward system, so you can do reinforced learning on top of it too. So for the reproducibility, we have designed 3D models. You can print at your home or lab, I guess, with your 3D printer. Okay, so you can download all these 3D models and then just print at your home. Then we know that it's exact identical 3D models. And also we try to set up the environment so that it's actually very reproducible to any other lab too. You know, simple, common material with common furniture models, like IKEA table here, and Frankapanda in this case. And we try to cover as many dexterous skills we can imagine, especially related to furniture assembly, you know, grasping, screwing, insertion, flipping, etc. Okay, for long horizon task. And again, for 100+ hours of demonstrations. And we can benchmark. So now, given the initial state, and our goal is to assemble this chair here, then you know you can, as you imagine, it requires multiple different kind of high-level skills to perform and assemble them all together. And with 1,000 different demonstrations, we applied IQL, and we show that it can also successfully assemble one leg in this video. All right, I think it's pretty clear now, so I will move on for the time. And of course, not just the same fixed initial pose, we try to vary. So we have different mode. So of course, with the fixed initial pose, at least LFD is reasonably easier. But when we go to this completely random set, then you know the task becomes drastically harder and also out of order, actually, especially given the number of demonstrations. Yeah, and not just for long horizon tasks, we also want to basically benchmark each different individual skills too. So whatever policy you train based on LFD or reinforcement learning, whatever you want to do, we also benchmark them as well. And not only that, even though we are releasing this real world benchmark, we also make this a simulator you can do proxy experiments in this simulator as well, so that we try to make it as identical as to this real world benchmark set as well. Okay. So today I talked about first how to learn and extract skills from especially task agnostic data, like what we call it is experience here. And also our lab has a little more works on utilizing predefined set of skills or even external knowledge, etc. And some of the works in bold are presented in this workshop and conference in this CoRL. And also I talked about the benchmark, how we can actually benchmark long horizon task, especially formed of a skill set. Okay. And I would like to end my talk with thanking my students here. If you have any more questions, please let me know. Thank you.
Maybe let me start with a question.
Sure.
So regarding that, so you essentially the skills you extracted was in like the same environment of the domain where you basically later wanted to execute your actual task. So how would you expect this to generalize to like a different kitchen setup, etc.? So if you think like your household or something,
right,
different structures, settings.
I mean, I think I will just cheat to answer this question. So the question is how well would it generalize? I guess the answer is as much as it can generalize to any other learning method, in the sense that if there are too much of a difference in terms of the task distribution or environment distribution, they will likely suffer a lot more. But again, then we can solve it by having more data and things like that. But yeah, I guess if the environment differ a lot, then I'm sure it will suffer as much too.
Do you think the offline data set is large enough and offers a large variety of data to still scale reasonably well?
Yeah, I think so. I mean, I'm a believer of data-driven approach in the sense that if we have enough data, I think it can scale to the, any other problems too. Just like we have seen in the computer vision or NLP domains too. Yeah, thanks. Any other question, or do I even have time? Well, maybe I gave too good talk. No question here, huh? Okay. Oh, yeah. Sure. So representation in what sense? Sure. Right. Oh yeah, so there, I mean, of course, it can mean representation can mean just about everything, but I guess when I split them, I was actually more referring state representation or even action representation, things like that. But for skill prior, it's a specific about learning the prior about skills when it's good to know to use. Just action prior. I mean, I don't see why not, but I don't know how. I think it will be hard to incorporate into the learning model exactly because it might be too noisy essentially. So with lower weights, maybe it can be helpful, but it might be too noisy in general, I believe, if you don't condition it in state. Yep, thanks. Okay, should I conclude, I guess? Yeah, thank you. Okay.
Just already made the nice setup.
So do you want, hey Deepak, do you want to use your screen or do you want to use Zoom instead?
I would prefer if I didn't use my screen.
So then you have to use, yeah, then
You already figured it out for us.
Okay.
there we go.
During the opening ceremony.
I learned it all here as well.
Thank you. What I did. Leave the HDMI.
Do you want to borrow it?
Sure.
Okay. It's $100.
Getting expensive to give talks.
Chip shortage. So what do I going here?
Oh.
I select something here?
No, I think it's just
The screen sharing, but somehow it's not working. Oh, there we go.
Yeah.
Need to self-approve.
So you can screen share. Oh, I think you are doing screen mirroring.
Oh, this one. I seem to work.
So I think what you do.
That looks good. All right.
It's paused.
Yeah, I think you're set up. Okay. All right. Okay. So our next speaker is Deepak. He is an associate professor at CMU and at the Robotics Institute, and also affiliated with the machine learning department, and previously also worked for Meta or Facebook back then, and also was a visiting researcher at Berkeley and also received his PhD there. So the stage is yours.
Okay. Hi, everyone. And can people on Zoom see my screen? Because it says on my end that the screen sharing is paused for some reason. Can somebody check on Zoom? It is working, not working.
I think we have to start it. So it's
Okay. Okay, let me start again.
Sure. Yeah, right. When you start sharing again.
Just check again.
Okay, let me share this. Okay, I think it's working.
Okay, check again.
Check again. Okay, so let me begin. So we have seen a lot of advances in robotics, at least on YouTube and videos. So here is an impressive result from Boston Dynamics of this robot Atlas. It can do lots of tricks. Here, this is performing a very complex parkour trick. And this is really impressive to watch. But we know the catch here is that these results are in structured and known settings. And this is where this conference comes into play. Like the goal of learning is to get these kind of results, not just for one task, but lots of tasks and lots of environment. So this is the grand goal of this giant robotics problem. And this problem involves research at all levels, like building robots that can plan, that can reason around humans from very high level to low level, figuring it out what electricity to apply to each motor and how to control each actuator in the robot. So how do we go about solving this problem, this big problem? So today, in my intro, I lay out very broad overview of how I think we can think about these things. And to solve this giant hierarchical problem, there are two ways you can think about. One is top-down approach to robotics, and the other one is bottom-up approach to robotics. Now, what do I mean by these two approaches? So top-down approach, which has been tried several times and lots of ideas have been tried in the old days. So let's start from the highest level. Let's start from the planning part and let's nail down the planning, the long horizon planning, and assume that low-level parts are taken care of. So for instance, you can assume robot can apply low-level skills, like robot can climb doors, climb stairs, open doors, and all those things. And let's focus on building high-level planning algorithms. Now, this has been a theme which has been explored by many works in the last 1 year. With this whole advent of GPT, Chat GPT, and all this, like these can generate very plausible plans. So for instance, here is a paper we had earlier in ICML, where we take this GPT-3 and we prompt it with high-level examples of plans and use it to generate plans. For instance, we take example of how to shave, and it shows some actions, and then how to brush your teeth, and it gives plausible actions, and then we can execute them in simulator. So here is the result, and it almost looks like AGI is here. Like this guy moves from one room, goes to other room, picks up opens the CPU by clicking the button, and then types on keyboard to browse internet. Very good. Like these models can just do it out of the box, no data required. What happens in the real world? So let's take example of the real world. And let's say now I give an instruction to a robot to pick object on the table. And for consistency, I'll show the same robot, Atlas, which was doing all these sorts of tricks. So here you tell the robot to place a block on the desk. So now you can see what kind of failures can occur. On the right, you are telling the robot, open the door and climb stairs. Problem here is not that robot does not know what to do. It very well knows the command is to open the door or climb stairs or a block on the table. But the difficulty, the meat of the problem lies in how to execute those things in the real world. And on the right, challenge for not too long ago, I think 2015 or 2016. And you can see the kind of failures here are there. It's trying to open the door, and the command is very clear. This brings us to this famous Moravec's paradox. What we think is hard is easy, and what we think is easy is hard. Now, this, if you've not read this report, there was a report written by Hans Moravec, Marvin Minsky, Rodney Brooks, after 20, 30 years of working in robotics to nail down what is hard problem. One famous example we have all seen is this example of playing chess. We have systems that can beat famous chess players, but it is very difficult to beat a 4-year-old in the exact ability to pick up a chess piece and move across the board. So what makes control and robotics very hard? Like, what makes it hard is the low-level nitty-gritty details of control. Like, for instance, even a simple task of door opening. If I take this example, it takes 3 seconds to open a door. I measured this myself, so I know if you're not in a rush. And you operate at very high frequency. Like, motor control happens in humans at 100 hertz or 500 hertz. If you take a lower bound, 25 hertz, you have 30 muscles in your hand. If you actuate all of them together and you discretize it in a very coarse manner, like say 10 actions, this space is still this big for just a mere task of door opening. To put in context, this is almost the same order or more than number of atoms in the whole observable universe. This is a very coarse lower bound on this task accuracy. So every time you solve something, you are searching this giant space. This is what makes control and robotics so difficult. The reason we don't have robots around us. So there is like sometimes there may be this common belief or some belief that low-level skills we can assume, then make a plan, and then language is the hardest part for all of this thinking. But it's exactly the opposite what happened in nature. Like, we spent billions of years to learn this low-level skills, this hard part of moving your actuators in a organized fashion. Another few million years to learn this planning part and its components. And language as we know it is just 500K or like very, very recent, blink of an eye in all this. So this is what makes the meat of the robotics. So in this talk, I'll talk about what priors can we use to build this pipeline bottom up. So what really constitutes foundation for robotics? Like, there is a role for planning and language at the high level, but this is only tip of the iceberg. Like, we need robots to be in human environments and talk to humans and get around this. But what makes this problem very difficult to execute, despite knowing the command, is this mid-level part. Like, where do I take my hand if I see a door to doorknob and not the hinge? Which direction the door opens? So this mid-level vision. How can I learn by watching others? Low-level control. What electricity do I apply to each motor at 500 hertz so that they can do all of these things in real time? And there's a lot of talk today talking about foundation. What does it mean for foundation for robotics? While language models can make foundation for NLP, but I think what makes foundation for robotics is this low-level detail of integration of perception and control together. Now, and these things are tightly coupled in almost all of biological organisms. Like, we talk about control and perception. To give an example of this, here is a paper from David Lee from 1980s. And this study has been going in neuroscience about how tightly coupled are vision and control. So this is an example where David Lee puts a kid in a room, and the room has moving walls to confuse the visual system. And this is what happens when she sees the wall moving. The kid just falls automatically. She doesn't even touch the wall. And this experiment has been repeated multiple times. There are various variations of this experiment showing that vision system is not a different component to control, and it has to be relearned every time control changes. So kids go from crawling to walking. They forget about fear of depth. They have to relearn that all over again. So this is very tightly coupled. Now, in this talk, we are going to talk about focus on this part, like how do we get these to the basis of robotics? So how do we build this general purpose skills which can be used across scenarios? And today's keynote from Vincent also focused on this aspect about this skills being the foundation for robotics. And I would say lots of progress have been made for fixed task settings. Like, if you fix a task, let's say for instance walking, let's say your task is fixed, the robot only has to walk, run, whatever, like one task. In these settings, we have made a lot of progress across scenarios. So here is work from us from a couple of years ago called our RMA, where we train this robot to walk across all these difficult scenarios by just training on simulator for fixed single task. And this can really adapt online and change its behavior and function in very difficult settings. So for instance, here is some fun setting we created in our in the home. It was during COVID, and we add this plastic sheet and add some olive oil on the stick to really stress test how far can you take this idea of fixed task training to new environment. So we are very heavily throwing olive oil, and then we add plastic sheet on this, and then we ask the robot to walk, and it can walk over this with no problem. It's difficult to see it at this speed, so let's slow it down. And in slow speed, you can really notice that when the task is fixed, the robot can really learn a nice adaptation strategy, adapting it at very high frequency. So it adapts at 10 hertz, like it in matter of milliseconds, it can adapt itself. And here is some adaptation going on. So I'll skip this for now. It can also adapt to new situations it's never trained for. We never trained it for throwing weights on it. And it is adapting in real time. It is very slowed down. So you can see how it adapts to account for the momentum by bending its leg and moving forward. Now, when the task is fixed, you can really push these paradigms, push these models to extreme. So there is this paper we have in CoRL, it's being presented this week, where we take this same idea, but extend it to apply for more complex robots beyond locomotion. So here is this low-cost system we designed. So I really like cheap robots. The cheaper you can get, the better. But the cheap robot mean noisy motors, non-repeatable, and less precise. So here we created this very low-cost system. It can cost up to as low as 6K as well. Now here the idea is, can we control this whole robot end-to-end through this learning-based system when the task is fixed? And here is an example of this deep whole body control. What we are doing here, user only specifies where the arm should go, the end effector, and the whole body adjusts for it accordingly. So here you can see the robot is bending its leg, it's rolling its body, and this whole thing is happening through a single network. No module for legs, no module for arm, a single thing for the whole body setup. And again, when the task is fixed, you can really push it beyond locomotion to agile tasks. So here is the same robot trying to climb a wall, because I talk to many controls people and they're always said about dynamic tasks. Walking is not very dynamic. So we thought, what could be dynamic? So here, this robot climbing wall from its front leg and then balancing on 3 legs to press the button of its door, and then coming down in a dynamic fashion to go there. Note, in all these settings, what we are showing is generalization across environment, across tasks, and across different scenarios. And finally, you can also learn these policies in simulation through vision with high dimensional data. And vision is required for more complex terrains, like these stepping stones, stairs, etc. So this paper is also in CoRL, so I'll not go into too much detail. But here, this robot is operating directly from vision and outputting actions for its joint. There is no mapping and no planning. This is the exact embodiment of tight coupling of vision and control. All you see is an image on the top right as input and actions as output. There is no map being built. There is no step planning being performed. It allows us to get around all the noisy situations that occur in this fine-grained locomotion. Now, this is a learning-based system with no hard coding for any type of foot movement. So this low-cost small robot can climb these stairs, which are almost as high as the robot. So this is not like humans climbing stairs. This is more like humans climbing hurdles, because the height of the stair is too high for this robot. There is not enough clearance. So it pushes the leg sideways to climb up and goes forward. And we will give live demos of this if you're interested. And we have given live demos at CEPR and all these Mardi Gras events. I think it's New Orleans. If you have not been there, I highly recommend. But this still poses a big open problem. How do I go about from solving single task to doing lots of tasks and lots of environment for which we are all here? Like, what priors do we need for going beyond this? And this is where I think we are stuck as a community, because how do we scale methods like this to diverse tasks and diverse environments? Because there is not much robot data out there. Like, we have simulators, but designing one task in simulator took us 3 years to get to walking. Now, what is a task? There is no such definition. Moving this is a task, pushing is a task, opening something is a task. Is infinite tasks and infinite scenarios. So this approach of designing sims for every task is not very scalable, right? So how do we go about this? Well, other fields like language or vision are really benefiting from large data scenarios, like lots of data out there. But in some sense, computer vision and language got lucky. Lucky in the sense people love to take photos of the same scene that others have taken photos 1,000 times before, but we still take new photos and we upload to internet. So there's a lot of data on the web. For language, we love to write and we love to explain others about life, about research on CoRL or whatever. So there's data out there. But for robotics, we all face this chicken and egg problem. Robot data is missing because robots are not deployed. They are not deployed because they don't work, and they don't work because there is no data. So how do we get around this problem of what comes first? Robots come first or data come first? So our approach has been to use knowledge from the only robot out there which functions 24/7 throughout the world in diverse scenarios. And that robot is human. And I think Anka will talk more about human, but here we are using human as a tool for improving sensory motor control for robots. So there's a lot of data out there on YouTube of people interacting with scenarios. This can be egocentric, this can be third person, and all these situations. Note, I'm not talking about imitation learning. Like when in robotics, we talk of demonstrations or human data, we talk about this, like some human controlling the robot by hand or giving VR demos. I'm talking more about learning by watching. And you can learn by watching, like by just watching others do things, even when they're not teaching you. Like you can see kids going around the house at certain age, taking everything in the house from a mouse to keyboard and saying hello to it as it's a phone, because they have seen their parents talk to some rectangular device very, very often. So this kind of learning is fundamental to scale robotics. But there are many challenges in learning from this kind of data. First challenge, human is different from a robot. Now, I can design a very human-like robot, but that's not practical. Like there is no reason for robots to look like humans, and they have their own benefits. But how do we transfer across embodiment? But the bigger challenge, I believe, is that when you watch videos of things on the internet, it does not tell you about forces, about contexts, about the 3D information behind the scene. And this is what we saw earlier. This is what makes meat of robotics. Like, how do we get these kind of things to emerge? So the idea here at a very high level is that we want to use YouTube videos of humans as prior to bootstrap robotics. So these are just priors. Just watching is not enough. You have to also go and bootstrap from these priors to explore in the real world and improve your policy as you go. So watch videos, lots and lots of videos, learn priors, and then also practice on your own and then improve. Okay. So, but what priors can we learn from videos? And this goes back to to old times in computer vision. There is lots and lots of literature, especially from James J. Gibson and J.J. Gibson, who basically devoted his life to concretize what does world offer to robotics? And the answer he gave was affordances. Like when we watch people do things in the environment, we can learn a lot about the environment. Surprisingly, across the world, you can pick any kid, your nephew, niece, or your kids. You can see they show similar behaviors. Every kid at certain age goes around the house and put their finger in the socket, in the electric socket. Why? Because they have seen people do something with their hands. So they have some prior that this is interesting thing. They don't touch walls, they touch sockets. They know where to touch on the door. They don't touch arbitrary places. They touch the doorknob. They know what to do, but they just cannot figure out how to do it. So these affordances are what makes environment conducive to robotics. And there's a lot of work in vision in trying to achieve these affordances, like how do we get them from videos? And this can involve trying to observe humans, figuring it out where they touch, work from hotspot and all this. So they are different kind of work in trying to extract this information. But all these works have mostly been limited to vision settings. Like we define affordance, we evaluate them, and we say they'll be useful for robotics. And robotics people don't care about any of this. Like they don't use any of these ideas, and then we build control from scratch. So we are looking into how can we learn these priors that are indeed useful for robotics. Okay. Now there are, so this is in submission, that's not public, but I want to still give some high-level ideas. So when we see a video, we can detect two things very well. From videos, we can see where humans are interacting in the scene. So where, and when they interact with something, how do those things move afterwards? Okay, so let's take a step back. What does a robot really need if it needs to scale to lots of tasks? Well, figuring it out where to go in the scene. Like I don't have to perform RL from scratch to figure out that to open a door, I should touch the doorknob. This is something which we can see across videos, across examples very easily. I don't have to perform all search in the real world. Okay, so figuring out where to interact and what to interact, we need this. Reaching the doorknob, it's okay. It's still an easy problem because I can perform reaching in my own body. I have forward kinematics, I can go there. What we also need is when the robot goes to that place, how should it move afterwards? Like I can get a good initialization from videos that if a person reaches the door, it either moves inside or it moves outside, but in the direction perpendicular to this axis, right? So we parameterize these affordances as contact point and post-contact trajectory. Like for instance, take this example of a robot. Without taking a single action in the scene, from YouTube videos, we can extract a lot of information about what things in this scene is useful for robot. This heat maps are trained completely from YouTube, and you can see it can already tell you that you should touch this area of the drawer. You can touch that object. It is not covering everything, but it is still covering a lot of interesting scenarios which robots can use to collect data. Then you can also know from videos where the human moved their hand afterwards, and you can approach and you can run the robot to do the same. So how do we do this? This idea is very simple. We watch a human video and we detect human in these videos. Now, computer vision may not work for arbitrary categories in the wild videos like chair, etc. But for one category, it works really, really well. And that category is human. Vision people have been treating humans as special for many, many decades. And these things actually work. You can detect humans in 3D because we have very well-defined structure across scenarios. So they are easier to work with than something like chairs. Like chair is very hard. What is even a chair? It's very hard to define. So what we do, we detect humans, and then we look at where they touch the object, and then how did they move their hand afterwards. But these frames have humans in them. So what we do afterwards, we project this information of contact point and how the human moved afterwards to an earlier frame in the video when human was absent. Because every video starts with something and the human may not be there, or they're in a small part, you can crop it out easily. So you can project this knowledge of contact point and direction back into the frame where the human was not present. And from that frame, you can try to learn basically an affordance model which predicts, given an image, where all can human touch and how will the human move afterwards. And then at test time, you can directly deploy this on the robot. And this acts as a generic prior for any kind of robotics downstream application. So we can perform imitation learning, we can perform exploration, we can perform goal condition learning, or even use this as an action space. So you put a robot in a new scene, and the robot already has good idea about what all objects it can touch and how will they move afterwards. So we call this approach VRB. So to give one more example, like our system trained completely on YouTube, you see this image, it already fires what all to touch, and it also fires where to move things in which direction. Now this direction is 2D because videos don't have 3D, but we can sample around it to figure out which one of this is good with very few, with much less practice. And here are comparisons to previous works in vision, which do not take robotics into account directly and just define affordance from vision perspective, and we get better generalization from all of them. But again, just watching is not enough, because if watching was enough, all of us would be playing like Federer. We have seen so many games of Federer playing tennis. We have to also practice and improve on our own. And this is where the exploration really comes into play. So we take these priors, we extract the priors, and then we have to allow the robot to practice and improve. So for instance, to give an example, a human comes and let's say opens a drawer over here. You can use this knowledge from YouTube to learn the exact priors, and then the robot practices on its own around these priors. So in the beginning, this robot cannot open the drawer, but it knows where to try and where to move the drawer afterwards. So it keeps on practicing 1 to 2 hours, and then until it succeeds reliably after practicing directly in the real world. This whole training is happening in the real world, no reward, no simulator in 1 to 2 hours. Okay, so this is a loop of extracting priors from videos and then using those priors to improve after using exploration. But how does the robot know when it has succeeded or not? Because humans are present in the scene. If you just compare the videos, most pixels are completely wrong. So representations don't capture it very well. So we do a very simple trick over here. we just in-paint the model, the humans out there. Now, this was before stable diffusion and all this, so this is much easier now. But this is a video example. You can in-paint the human out and robot out, and it still looks reasonable. Now, we don't compare pixel by pixel, we compare representation, but this is already giving much more information about what do we care about in the environment. We don't care about the exact human movement. And as I was saying earlier, there is this task specific objective to make the scene look like what human made it look like, but also exploration. And here we encourage the robot to explore using curiosity, which allows it to explore new and new settings. So we call this approach whirl, in the wild human imitating robot learning, and blah, blah, blah. And here is one example of what this, but the main interesting takeaway is that this is learning directly in the real world, not requiring any simulation, not requiring any reward function. And the approach, you can check out in the paper later, it's more like a zeroth order policy learning. So it's not RL because there is no reward function, but it's directly optimizing for the policy by watching videos of humans continuously. And the main thing here is that the more you explore in the real world, the more time you put in, the closer you get to being a federer. And so here, the performance improves the more you explore. And here is one more example of robot improving itself. But the main point here is that this method can train directly in the real world without simulation, without reward. So we were able to scale it very quickly to lots of tasks in lots of environments. So here, this robot is performing 20 tasks across 20 different environments in CMU. I think it was snowing that week in Pittsburgh. And if you know the RSS deadline in January, so it's very bad in Pittsburgh. So we cannot take the robot outside. So through tunnels, we took robot to every single building and every single kitchen to perform all these tasks and have it learn in those scenarios. So you can see the robot is opening tap, it can fold, it can picking up garbage bags, opening drawers, opening dishwashers. And these are all not in lab settings, they're actually real world environments. And the idea is basically the same, extract priors and then perform curiosity exploration around that priors. Now, you can also apply similar effort on different robots, let's say dexterous hand. For instance, like from these videos, if you have a hand robot, that is much more easier, because you can actually find correspondence between hand of human and hand of robot. Unlike prior scenario, when the robot is totally different, you have to rely only on practice. But when you have a hand, you have much more help because of the structure of the hand. So to give an example, we go to YouTube, find videos, and extract human hands. So I'll show a live training of this system. So these on the left are frames from YouTube videos. And as the training goes on and on, the human hand starts to align with the robot hand. And this system is trained fully on YouTube data, not using any data from robot. And these are the frames from YouTube videos. And once it is trained, we can use it to teleoperate robot from a single RGB camera. No gloves, no VR, no mocap. So we call this robotic telekinesis. We thought it's a cool title, but I realized later that it has already been used 10 years before, but it was too late to change. In any case, so we can also do this over Zoom call. We have had visitors in our lab try this. So here is an example of the same thing controlled over Zoom call, because there is no depth or anything. It is working directly from RGB camera by observing human hand and trying to mimic that, and train only on YouTube, nowhere else. But no, this is not a policy. This is still teleoperation. Like this is a demonstration of how powerful YouTube data is for actions. But we can combine it with few examples from the real world demonstration. So from videos, we extract this visual priors, this representation, and then we use this telekinesis way to transfer the robot data, the video to robots frame, and then we can collect few in-domain demonstrations. So like we have 3,000 videos from YouTube, and then we collect 10 demonstrations per task per object in the real world. So 10 demos in the real world through the system, which is also trained on YouTube, and 3,000 videos from YouTube, and then combine into a single framework. So you are extracting human videos data to not just learn visual representations, but also action representations. And then you combine that with some few demos from in-domain data and transfer that to the robot. And here are completely unseen scenarios for the same setup. Now, this is not teleoperation. This is operating autonomously and on a new object. This is a new cloth, new objects, new object over there in all these situations. And this system is trained on 90% data from YouTube and 10% data from in-domain examples. And this can generalize very well. So here are some examples of, like, in most cases, this method outperforms other methods which only learn representation, which only learn action, and only learn on robot data. So it helps in all these three scenarios. So just to summarize the talk, so I believe if we really want to build foundations for robotics, the way to build scalable systems is to really go and learn and look at lots of videos on the web, which everyone does. TikTok, etc., so famous. Our robots should do the same, but not just learn visual representation, but also an action representation, and then improve around those representations in the physical world with few examples. This can either be some demonstrations from humans, or it can be some practicing going on its own for a few hours. And then once we have this system, we are looking into combining our legged robot like adaptation work back into the same thing. So just in summary, building general purpose skills is basically the meat of robotics control. YouTube data provides sort of initialization for all this, but just videos are not enough. We have to also adapt and practice in the real world. So thanks to all the students who are behind this work, and you can find them during the conference. Most of them are here, and I can take any questions there.
Okay, yeah. Just a quick one, yes.
So this is very cool. Very impressive stuff. When I was in grad school, and that CMU is the one right now.
Yes.
It occurred to me we were making our robot open that fridge door, and it was tricky. What occurred to me is that the way that we humans do it, just reach for the handle open, is not how the robot can do it robustly, right? Because its sensors are craftier, its hand is craftier. Why the strategy of sort of touch visual computation, touch the door, go until localize it, and then sort of sneak it on. So I was thinking, I mean, in part you're addressing this because you're saying, look, the way the human does it is a fire and we add exploration. In part you're addressing this because you're sort of what we're trying to match with the embedding of the human and the robot that moves to really affect objects. So I'm aware of all this, but nonetheless, there's something in me that's bugged by this human pride, because a lot of the times, I would argue the way a robot should do it is completely different than the way a human should do it. So what's the kind of the right way to think? It's close, but not the same. Is it really a prior? Is that, should I really think of it as like, this is the most likely thing that you should do what a human does? Or should we be using one of these donut distributions? So it's probably kind of in this vicinity, not too far, but not too close either. What's technically the right way?
This is a great question. And I would say this is like, I, of course, I thought about all possible scenarios here, but I would mention like this fridge example. I think fridges are still lighter, but I totally understand. I'm realizing this with doors. Like the way humans move doors, we move our hand backward like this, and then we go outside. But there's a video of Boston Dynamics robot opening a door, and it's very different. Like robot first opens it, then puts its leg in between, then goes around here, then pushes the leg outward. Very different motion. And I think it varies by difficulty. Like for instance, playing like Federer requires a lot more practice than opening door like Federer. So I think that there is no clean answer I can provide. But here, I think these are priors about the environment, that at least doorknob has to be touched and door has to be opened. And the way robot will do will be very, very different for different difficulty of task. But at least I believe 70% of daily life tasks we can mimic by watching humans. May not be door opening, remain maybe very difficult fridges which are hard to open like French door. They will remain, but I think many of these will, and they will require more practice and innovative ways of robot collection. I mean, you can set up and I can take one more question. I don't know.
Yeah, we can continue because of the time now.
Okay.
So thanks again for.
I'm sure.
So Joseph.
You're presenting over Zoom or want to directly present?
I guess I'm doing it over Zoom. I don't know how to do it directly.
Right, you can do it if you want. Let's say here, I did it.
Oh, I see. So I can just stop share. Oh, that's good. Okay.
Yeah.
So we just do this.
Yeah.
Shows a figure this out earlier.
Okay.
Just like normally how you present classes, just share the screen and share the call.
It's just like.
Does this work?
No, but to share the screen from
Oh, I
here
have to share the screen up for Zoom still. I see.
for people to see. Otherwise, this would work from here.
Okay.
So not like presenter mode.
Now I'll do presenter mode. Is that okay?
Yeah, I think you can minimize this.
It's a weird resolution though. Yeah.
Yeah, it's a bit weird.
Okay, screw this. Let me just, can I do it over Zoom? Is that,
You can also just share it with Zoom.
I think that will work, right?
Yeah, that should also work.
I think it's. Yeah.
We need Joseph back.
Shows us that it's obviously.
Oh.
Right. It has to be this one.
Oh, looks here.
That looks good. Ish.
Yes, but it's not on the main screen. This shows it. Why is it not on the screen? What is
Doing something over there. We can try on pressing on the options.
I'm not sure what he did.
Okay, what about if I slide?
His trolls are still here. Because he changed it like earlier.
How's this? Oh, okay.
Okay. Wait, you just switch back, then it's working. Oh, it's fine.
Yeah. Okay, well, whatever. I mean, it's a weird
can
resolution.
minimize.
but I don't even know how to get to this. My
I
God.
think it's
Full resolution. Can you go to the next slide? Let's just
I think it stops here, right?
Oh, like this.
No, it's fine.
No, it's fine.
Okay, cool.
that's fine. Okay, then. Okay.
Can I just minimize this? Where's the map?
Oh, it's our computer. It's the resolution of the presentation. All right. Okay. All right. Okay. So we have the last speaker for today. After this talk, we will also have a short panel discussion. So in case you have any more questions for Deepak, you can also ask him there. All right. So we have Anka here today. She's associate professor at the University of Berkeley, and also was involved in the Berkeley iResearch lab quite heavily from the start, and has won multiple awards. So we'll keep it short, so we can start.
Sounds good. I want some stuff. Hi, everybody. Thanks so much for coming. So I will keep the theme of the workshop about talking about how to induce geometric structure or human knowledge into these models, but I will talk about it from the perspective of building human models for human AI interaction. And so to start off, this is a video I love showing because we have a human being there, labeled very clearly human being on the right-hand side. We have a quadrotor on the left-hand side, and the quadrotor just needs to get to its goal location and not hit the person, which sounds kind of easy enough. But from a technical perspective, what's interesting is that this quadrotor now, if you want to evaluate its cumulative reward and expectation to come up with a policy for it, you can't do that anymore without having access to a policy for the person as well. Its reward depends not on just what does, but on also what the person ends up doing. And so to solve these kind of it's hard to even call this interactions, more like in avoidance, really. But even for that, you need to start making these predictions about what will the human do so that the quadrotor can figure out what a good thing for it to do is. And then it gets more difficult when you start talking about collaboration. So no longer just, we interact by avoiding each other, but we're actually trying to do something together. I was very interested in this in the context of robotics and likely getting, especially since the COVID thing happened, getting stuff with real humans and real robots was a no-go. And so what did we do instead? We set up this really cute little benchmark based on the game Overcooked. I don't know how many of you have played Overcooked. It's like, let's get together and cook some stuff. And it requires you coordinating with the other agent. So we simplify this down. It's a kind of a task and motion planning problem. It's complicated enough that sort of state-of-the-art task and motion planners have a hard time with this. So there's some low-level motion to it. You can't bump into the other agent. There's some high-level task of you have to go, you have to pick up onions, put them in the pot, wait, grab a plate, and then go and serve them to that soup delivery gray location. And so the idea here was, can I get an agent, an AI agent, to play well with a real human in this environment? And this is much more difficult than avoidance. And what happens with this, so here's humans playing together, first off, okay? They're just kind of doing their thing, loading up onions. At some point, they have to do this like role allocation of who's getting plates versus who's still putting onions in, yada, yada, yada. Everything works out. However, what's difficult about placing a robot in or an AI agent in this context is that if you have the wrong expectation about what the human will do, you end up doing the wrong thing yourself, and then you have actions that conflict. So here we have this kind of situation where the robot expects that the human should get an onion. So the robot should go get a dish. That's the optimal thing to do in the task. But that's not what the person does. The person right in front of the dish dispenser. So very clearly, they're actually going to get a dish, sort of violating the robot's expectation. And then you end up with these coordination failures where we both end up, we don't have the right sort of role assignment. And so I spent a lot of my time thinking about how we can get good predictive human models, human policies that we can give our robots so that they can collaborate and interact well with humans. So where does this, like, if I have a quadr or whatever robot I have, how can the robot figure out what the person's policy might be so that it can actually plan or learn its own policy in response? And clearly I can't just like write down what people will do. And so naturally, this is a place where we want to leverage data. And the question is how? And in this day and age, of course, it's very tempting to say we're going to collect a bunch of data and we're going to treat people as these black boxes where state or history of state goes in and actions or distribution over actions goes out. And we're just going to do supervised learning. And that's going to be our human model. So imitation learning, but to get a human model, not to get a policy for the robot. And so we did this. We had humans play together. We collected data. We trained a policy for human behavior, and it did really well, not too surprisingly. So here we have the policy actually playing with itself, and you notice some beautiful things happening. So there's coordination. One of them grabbed the onion, the other one grabbed the plate to be, the one with the onion is ready to put the onion in once the other one with the plate can take the soup over. So they're kind of doing this whole thing, not only delivering soup to the gray zones, but actually sort of achieving complementary roles, adapting to each other, blah, blah, blah. So this is beautiful, right? You look at this and you're like, great, we're so close to having an AI agent that can collaborate well with the human, at least as long as we have a lot of data in these kind of environments. And then, the skeptic in me came out, and I'm going to pause this here for a second. So what I had, this is my student Micah Carroll's work, and I asked Micah to do is to test out the same policy, but put a plate on the counter. So you see the plate on the left. Plates don't end up in counters very often in human data. You kind of have to get something wrong in the task so that you set up the plate down and then you go and you do the correct thing. And so the plate ends up on the counter accidentally. And then we just saw what the same policy does in this situation. And they're doing stuff. It's not like they're not doing stuff, But if you look closely, it's completely nonsensical, like they're little zombies going through some motions, but in a way that completely has relinquished the notion of we're serving onion soup. So that one on the right there, just put a plate with onion soup on a counter as opposed to delivering it to the gray area. This one on the left is just wandering around with a plate full of soup, not delivering it, sort of kind of stuck. And this is what happens because, oh my God, there's a plate on the counter and we've not seen plates on the counter. So we do not know how to function in this world, how to coordinate what onion soup is, none of that. All of that goes out the window because of the novelty of a plate being on the counter. I like to play with GPT, and these days with ChatGPT, but these are examples from GPT-3. And this is, I think of this as the kind of the pinnacle of imitation learning, the most data thrown at a problem, and so the best sort of behavior clone model. And I asked it, Anka throws the ball to Chris, who throws it to Lucas, who has the ball, and impressively, it's able to say Lucas has the ball. So these sort of like multi-step reasoning, like so impressive, so good. But I like to be sneaky, as you know. And so the equivalent like plate on the counter thing is Anka throws the ball to Chris, who throws it to Lucas, who has the cat. And GPT says, Lucas has the cat. At least it used to. I think the newest model has been trained to be better at these trick questions. And I asked why, because he caught the ball that Anka threw him. That even doesn't make sense. Just as I was sitting there, I did a false belief test. Anka's in a room with two boxes, A and B. Anka puts a mango in box A and walks out. Trevor enters the room and puts the mango from box A in box B. Anka returns. Well, we should look for the mango. This is called the false belief test. It's very hard for children until 4 to 6 years old, but after that, they get it. GPT says, Anka will look for the mango in box B. Wrong. Why? Trevor moved the mango from box A to box B, so that's where it would be. Yes, that's where it will be, but Anka doesn't know that that's where it will be. And so it's kind of pretty flaky at these sort of tests as well. Okay, so these are weird prompts, right? The cat, the who has a cat is a trick question. The false belief is a very subtle. These are weird prompts. So I think what we can all accept is that these high capacity models are great in distribution, but they can fail on their distribution shift. And we have really no idea how to get that to work better. What's worse is that this matters because distribution shift occurs in interaction quite often. So let me share a little bit about why. I work in self-driving cars quite a bit. So this is imagine a situation where I have a self-driving car in orange and it needs to take a left turn. And there's this human-driven vehicle in the white car there. Now, interestingly, here you can make predictions about what the human will do. They'll keep going forward. In their lane, which is true, but it's only true for the situation where the orange car brakes and merges behind. If the orange car were to do something else, like accelerate and try to go in front of the person, you'll see a very different response from the person, which is to slow down and give the other cars some space. And so what's interesting about interaction is that you can't just make predictions about people in isolation. What they will do depends on what your robot decides to do, which becomes very tricky for learned models of human behavior. If I plug in a learned model of human behavior for the white car here, and I try to say, okay, autonomous car in orange, use this model to figure out what to do, it has to say, well, hypothetically, if I did X, what would the person do if I did Y? What did the person do? And so on and so forth. Whether you do this with planning, or really this would be model-based RL, or do you do it with model-free RL, and this is your simulator, it doesn't matter. The point is that when we think about human models, the robot actions, robot policy ends up changing the distribution of states X that the human policy is responding to. And so not only are high capacity models brittle on their distribution shift, but the bad news in interaction is that almost we're guaranteeing distribution shift when we are learning these models and then using them to figure out what our robot should be doing. because they'll query these models off distribution to figure out what the right answer is for the robot. And so this is bad news for high capacity models with no assumptions. Now, there's an alternative that I want to touch a little briefly on, which is also problematic, which is to say people aren't black boxes. People behave in the way they do because of stuff happening in their heads. So people behave the way they do because they have objectives, intentions, things they like to accomplish. And that ends up driving their actions. So I walk the way I do because I'm trying to get to the exit, right? And so my actions aren't arbitrary. Can we leverage that? And then sort of the naive way to leverage that is to say, well, how can we think of objective-driven, intent-driven agents? We have a framework for that. It's basically reinforcement learning. We can think of the person as having some utility or reward function, capital UH, that depends on some parameters that we'll call theta H. And we can think of these parameters as sort of being trade-offs that the person makes between things that they care about, right? I want to navigate to my goal. I don't want to bump into stuff. I want to be efficient. We can think of theta H as being just sort of the goal index of where's the person going. We can think of these as being weights in a neural network, describing the reward function. But the idea is, let's think of people as being these optimizers of some reward function as well, and parameterize that reward function by some parameters, theta H. And then we can say, what do we expect people to do? Well, we expect people to take actions that maybe aren't perfectly optimal, because they're not robots, but they're sort of epsilon optimal. So an expectation, the Q value of the person's action in a particular state should be sort of epsilon optimal, where Q star here is the optimal Q value function for theta H. And so if you set up that problem of maximize entropy, find a human policy, a distribution over actions in a state, or any state, that maximizes entropy, but in expectation, the person should be epsilon optimal, you get this thing called a Boltzmann distribution or a Gibbs distribution, where you're saying, what do I expect the person's policy to be? What will UH be conditioned on the state and on these parameters theta H? They'll be approximately optimal, right? So the probability of an action is exponentially higher with the Q value of that action according to the parameters theta H. This is a model of human behavior that really kind of, and then, that predicts what the person will do. Its roots are really uncommon, and then making its way through inverse reinforcement learning, but still with sort of people acting completely optimal, and then with works like Bayesian inverse reinforcement learning or Maxent IRL, so they made their way into AI and robotics in this form. And I've used this model in, I kid you not, 30, 40 papers, something like this. Just this very simple assumption that people are sort of noisy, approximately rational, and that you shouldn't learn the whole thing because the human actions are this consequence of them sort of planning over time in a particular world with dynamics for their objective. And instead, you should just learn about their objective, and that will give you that full distribution through dynamic programming or approximations thereof. And of course, that doesn't mean that that's the policy that the robot uses. Again, just to remind ourselves, this is a model of how the person behaves. What the robot does with this is it plans an expectation, its own policy that does well, assuming that that's how the human behaves, or thinks of basically being in a game with a person in computer-Nash equilibrium. And this has been also kind of an okay thing to assume. So just like with the black box approach, I want to share with you sort of a success story and then a failure story. So the success story is Endorser's work. We did this for driving. We collected a bunch of data. We told we fit a model, we fit theta H as what sort of trade-offs people made between wanting to be efficient, wanting to get destination, stay on the road, blah, 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 things that we knew people care about. We fit that to the data. And then we gave that model to the car in orange, and we told the car in orange, your reward is to be very courteous. Your job is to get the person first through the intersection. And we wanted to see, well, what does the robot think is the optimal policy that will do that, given this model that it's learned? What would you do? Someone might have seen me give this example before. If you have, don't say anything. But if you haven't, what would you do if you're the orange car and your job is to get the white car first through the intersection? What do? You can signal. So this is a common thing. You can signal, and it's, you can flash your lights. The problem with flashing your lights is that whenever people flash their lights, I don't know if they're saying go, or they're cursing at me, or they're honking at me. Same with honking. I'm like, does that mean that I should stop and let you go, or does that mean that I should go? I don't know. But good thinking. What else could you do? Yeah, back up. So that's what the car decides to do. It doesn't go, because that's not getting the person first through the intersection. It doesn't just sit there and wait for that would work, but there will be some delay for the person to realize, oh, the car's not going, I won't go. It decides to start backing up. And I kid you not, people go faster through the intersections. We did a user study on that. Let me skip the details of this. And if you look at human robot interaction literature, where people try to figure out how to get robots to behave well with people, this is called a backup strategy. So people do this not with cars, but in social navigation. They investigate this thing with, okay, if I have to squeeze through a space, maybe I get the robot to back off to indicate to the person that they should be going. And the car just invents it here. Now, let me blind the screen for a second to talk about why I'm sharing this particular example. Imagine doing this with a black box model. If it's a black box model with the orange part, which is communication learning, that's up. You don't see this in the data. You're not going to invent this strategy, right? It's just not in the data. But even if you're using it as your model of the human, so now we train a black box model of how humans run, and now you tell the orange car, okay, get the person first with the intersection. How are you going to use that? How are you going to come up with a backup? Well, you can't, because there's no way that your black box model is going to know anything about what might happen with the person if you expose them to that backing up, because again, that's totally artificial. It's not something that we see. So that's really interesting, that by sort of giving the structure to the robot, saying, look, there's something we know about humans. They care about avoiding collisions and being efficient and so on. That goes from models that it's only seen like the model actually was trained on just driving on the highway, and then you can take it into an intersection and can expose it to things like backing off. And what does it do? Well, it says like, well, if I remove myself as a collision risk, chances are the person is more likely to go through the intersection. So, noisy rational humans, yay. But then again, people aren't noisy rational. That beautiful equation, the Boltzmann formula, that's not how people work. It's wrong. Here's lunar lander, people crash all over the place. They're not noisy rational, they're just completely biased. And in Overcooked, that toy environment I showed initially, we tried this, and here's what I want you to focus on is the dotted line at the top. That's random prediction of human action. And then the purple bar, that's what the noisy rationality assumption gets you in Overcooked. It's basically on par with random. When you collect data on Overcooked, people aren't acting in a noisy rational way. It's a terrible way to predict human behavior. So that's kind of a bummer, right? It's like we have this thing, look, and self-driving, blah, blah, blah. It makes sense to capture structure in what people want. But people are sometimes so biased, so suboptimal, that it's a terrible way to think about it. And so, let me skip the slide. It's not new. Behavioral econ has warned us for a long time that we're just a bag of heuristics and irrationalities. And so the thing that I've been having fun with lately is, well, now what? There's this noisy rationality model a lot of us know and love and use all the time. It's delivered some nice things. There's black box models that don't make any kind of assumptions. Those also work a lot of the time. Those also deliver very nice things. They all fail miserably in sort of different situations. Now what? And in kind of maybe 2 minutes, since I started also 15 minutes late, let me share sort of 2 lines of thought. One, I call this sort of the practical thing to do. That sort of, you know, people get excited about, gets papers in, but I kind of find obvious in a way. It's not what I get excited about. And then there's the thing that I get excited about, but I don't know if it's practical at all. Okay, so here's the practical one. The practical one is, an example of this is what we did this year at Neurips. This was also mine. So Micah basically said, look, we're not getting enough leverage out of the data when we train the black box model. We can actually get them to be much more robust by essentially kind of coming up with a foundation model, equivalent large model, the large language model equivalent first, and then fine tune it. So he thought, look, what is behavior? It's a sequence of actions. I observe behavior, and I want to do tasks like goal conditioning. What does that mean? It means I fix the start, I fix the goal, and I ask what to do. What if I want to do prediction of human behavior? What do? I fix the things that I've observed up to a particular time point. I ask what happens next. What if I want to do, you know, reward conditioning? So that kind of achieve max reward. Same thing, you fix the rewards, you predict the behavior. What if I want to do waypoint conditioning? You know, you fix some waypoints around, you ask what's it. So basically, Micah said a lot of the stuff that we do in sequential decision making, whether it's prediction, imitation learning, offline RL, whatever, is kind of like these different masks on behavior, where you mask certain things and you ask to predict what you've masked. That's what people do to train language models, and they do it with random masks, right? They just like randomly mask different parts of the input, and they're like, here, predict what's going on. Let's do that. Let's do random masking on behavior. And it turns out if we do this and then fine tune on your particular task, say behavior cloning, you end up at doing much, much better than just solving the behavior cloning. It's because you're forcing, in a way, the idea of the model to learn some structure in the data. That was Micah's idea. Another fairly obvious, in light of what's happening in large language models. So I see someone's trying to take a picture. That's the thing that, yeah. The other thing that is also very obvious is it's a prior. What, you know, this optimality, noisy optimality assumption is really just a prior. Let's pre-train with that and then fine tune to with real data. And that also does much better than just using real data. It depends on the details of how you fine tune. So all these I think are fairly obvious and they do help. In a nutshell, what's the interesting thing? Okay, so we live in a world where I think more and more, as someone who loves math, I get concerned that we like pass it on the back and keep drawing on. We have avoided writing this math. We just threw data at it and like, you know, the thing figured it out. I didn't have to write the math for it. Yay, go us. And so for one project, we kind of did the opposite of that, which is we took pride in like writing a little bit of math instead of using a crap ton of data. So here's the idea with that project, and this is Cassidy's work. Cassidy observed that, yeah, people in Overcooked are not always optimal, but they're systematically suboptimal. So, you know, the person, this is the optimal action rate to go counterclockwise. The person goes clockwise, they're going to keep going clockwise. They're not going to like turn around and start going counterclockwise. You know, they're just like, people have biases. I don't know how to describe them. Behavioral econ lists like 150 of them. But what's interesting about them is that they're systematic. They're not just like noise. And so if you look at Boltzmann rationality, what Boltzmann rationality does is if you try, you know, you say that the probability of a trajectory is proportional to the exponent of the cumulative reward. If you try to figure out the next action, it only depends on the current state. It doesn't depend on anything that you've done before. So you can't capture systematic suboptimality. So Cassidy basically just said, look, if we want to capture systematic suboptimality, we have to go beyond predicting distributions over trajectories or actions. And instead, we have to couple these action choices over time by predicting distributions over policies. A policy is what enables you to capture how all of your decisions across time link together. And so he did a Boltzmann policy distribution instead of a trajectory or an action distribution. The noise rationality assumption that I shared with you earlier in the talk is one policy. This is a whole distribution over policies that are approximately optimal. And the advantage of that is as you see the human behave a little bit, take some actions, that gives you evidence about what policy they're following. So it influences your future predictions. And with that, I'll skip this because I know you want to get to your panel. With that, you're able to capture systematic actions over time, systematic suboptimality over time. The way we do this in practice is through basically using this sort of latent condition policy network that we train to sort of mimic the Boltzmann policy distribution. And then when you want to do inference, you either update what your distribution of your latent is, or really what we did is we threw a transformer at it to directly predict the action. This is just looking at sort of initially in this latent space, you have this particular like a Gaussian distribution over policies as you observe some actions. So these the graphs in the middle are the only ones that are going to make any sense to you right now. You're sort of shifting what policy you think the person is executing. And when you try this, and this is really the mind-blowing thing to me, is when you try this in overclock and you compare it to behavior cloning from a lot of data, it's not it's not some magic thing. It's not like it's going to do without much data as well as something that consumes so much. But it's, it reduces that gap from random to sort of like your nice behavior cloning performance very, very drastically. So you're almost as good as behavior cloning without using really much data at all. You just observe within episode actions from the person and refine your distribution. And so this is like completely amazing to me because all we did is we went from, instead of a trajectory distribution, a policy distribution. And all of a sudden, we could do almost as well as collecting a ton of data about human behavior. And I think that's really encouraging. That basically says that it doesn't get messed up with plates on the counter either because it's approximately rational. So like it will do the approximately rational thing. So yeah, I think a little bit of math can save you a lot of data. And I think maybe more broadly, it gives me hope that maybe there are mathematically elegant ways to capture human suboptimality that are not going to bore me to death. Like they're actually interesting to think about. They're intellectually stimulating, but can also work to make these models more robust and drastically reduce their sample complexity. So I'm sort of looking for that currently. And with that, I'd like to thank you. There's more stuff to look at if you're interested, but thanks, and especially to Cassidy and Micah, whose work I talked about.
Are there any intermediate questions to answer for now?
But I want to throw a lot of math at it and not think about how people.
But how do you disentangle when can human press the buttons correctly? For some reason, I'm not able to control joystick or mobile phone to press the things nicely. How do you control for that part? In the car example, it's already controlled because that is that practical. In the game, in particular, the humans being random or not noisy, optimistic. How do you control for that? Are they pressing the buttons properly, or there mistakes that it will be random, or they are thinking rational?
Yeah, so if it's random noise, then Boltzmann, just vanilla Boltzmann will take care of it. if it's basically you have this kind of systematic bias of, you tilt the joystick more to the right then, or you overcorrect. That's exactly the kind of thing that built-in policy distribution, will be reasonably good at capturing this, because like once you've went way further to the right once and again, it's like, okay, it seems like when you're supposed to go a little bit more to the right, and I'm going to start anticipating that about you. But it's a good question overall. I think there's a number of things of other works we do where I worry about that. And maybe the last thing I'll say on this is, there's this work that we did in CoRL last year called assisted perception, where we treated people as approximately optimal under false beliefs about the state of the world. So we learned their sort of biased perception model explained by their actions, and then we fed them observations that got them to take the correct actions. What I work with that kind of work is, when we're learning the biased perception model that they have, is it really that their perception model is biased, or is it that they're, joystick is the And there's no way to really disambiguate that. All you can see is, well, yeah, they take better action, but then you have this risk of they take better action with distribution. If it's really the joystick thing, then when you try a different task, that biased perception model you learned that compensates for the joystick delay is not going to be a good predictor anymore. So I do worry about disentangling these effects of, and most general way I found to do that is this sort of Boltzmann policy distribution thing, but it's sort of task specific, right? And if I change the task, then I don't know anything about how the person will act under the new task. So. Okay, can we move to the panel?
So probably we can slowly move to the panel discussion. It would be very short actually, because we don't want you to get too late the work in the session. Do we have you? I don't know. You need the microphone, otherwise. Here, should be fine now. Okay, cool. So probably for those speakers that are still with us, so I will be happy if you can join us here. We can also have the chance to, you have guys some questions that probably were left out during the presentations would be good. Also, it would be a good chance to start with that. So yeah, maybe please go ahead.
Does the Boltzmann probability distribution or the Boltzmann model in general, I think it could model an adversarial human. Like if like at least with certain cars, what if we don't actually want the car to like the car's trying to back off and you're just like meeting you're like, I don't want you to move ahead. But like with overcooked, you don't take the plate and throw it away. What do you do next?
Yeah. So yes, in the sense that you can learn that the person's reward function is negative to robots. But really the right way to do it is through this work where you don't assume noisy rationality in execution, but you assume strategic noisy rationality, where you know that the human and the robot are part of this general sum game. And we're learning the human's reward function, but not assuming that the robot doesn't exist, or the person gets to know everything about the robot and to be the best response, but rather they're playing this game and they're at a match. What's really hard, so I'll share that we've made progress on this problem. There's a little bit of work that does inverse reinforcement and learning rewards in that context. But it gets really complicated when you're starting to assume of like, well, does the person assume that the robot knows their reward function, or is it, is it part? And what does the person know about the robot's reward function? And all of these decisions lead to fairly different policies down the line. And they get the real thing you're trying to capture is both impossible to compete with. We've made a lot of progress on basically general sum games, full observation for observability. But yeah, the rough answer to your question is you can get to a first order of these effects what's going to happen is you're going to learn a reward function that has the person be more aggressive or blah, 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 care about collisions. That's not really what's happening. It's just the person knows that they can influence the robot. They care about collisions, but they know they can influence the robot. And the right way to capture that is through game theory.
Any other question from the audience? I do have one question for Deepak. So,
should we sit down?
Yeah, sure. Whoever wants to sit down.
Typical thing at panels.
I think that the word that you show regarding like learning from videos is actually very interesting. Something that actually puzzled me a little bit was the kind of motions you were learning, right? So they look fairly simple in terms of kind of manual translation motions, right? And I was wondering, like, when you do this exploration part, and if you want to actually learn like more like orientation based motions, can you actually like leverage this exploration to kind of understand better how these like orientation changes may play in the videos? Like, yeah.
I think the translation motion is more artifact of the hardware. So if you know about this Hello Robot, it only translates. So it made our life very difficult, because if the robot, it can only extend its hand outwards and inwards and can go up and down, and then it has to move around. So let's say if you take your hand here, but the object was there, you cannot move your hand like this. So you have to go all the way back, reorient yourself, and then come back and extend your hand again. So that was artifact. The translation looked part of the artifact of the hardware. When we use hand, then it is less linear and there is more orientation involved, because that actually helps you in doing that. But on the flip side, the hardware is constrained. That's also a feature and less of a bug, because now it is very lightweight, very low cost, like system that you can take all around CMU, etc. But in those videos, the translation was mostly of the artifact of the robot. Like for instance, when it has to open door, etc. So it has to move its base, but it will still look like translation, because the hardware is that can only do this. It has all degrees of freedom, but they're in a very weird way, which is very non-human like. So I believe that may be because of
like
the hardware.
in the videos, you still, I mean, it's still a 2D representation of the world, right? So how can you get like information
About 3D
regarding orientation, right?
Correct.
So
Yeah. So that's a good question. So like while extracting affordances from videos, we had two things: where the human touches in the scene, and then which direction does it move. So I skipped this part. How do we deal with that? Like the direction part, it's 2D, because from images, you cannot, if a drawer moves sideways like this, you cannot know, is this down? Is this direction? Because projection all looks the same. So what we do in there, we sample the robot and ask it to sample around all possible directions during practice phase. Yeah, and then it improves over that. So the orientation is still involved, but it is more transferred to the practice phase. But I guess if you have a lot more data, there is also very good intuitions you can build. Like if you see a flat thing, and if you see human moving this way, you know that human is probably not moving downwards, it's moving more perpendicular. Like general priors, which people have explored in vision community, like 10, 15 years ago, quite a lot. We are not using them yet, but there are ways to get around practice to a large extent.
You can also think about unsupervised 3D reconstruction and then basing it on that, which you think, well, maybe, what's the point? Maybe it learns that implicitly, but it might not. And then actually forcing it to go through a 3D reconstruction.
Agreed. So our human was in 3D. It's just that we did not know the scaling of that. Like the scale is not clear. So for that we sample, but I totally agree. Like putting more structured priors in there could be useful. Like
actually, like, I mean, connected to this question, and maybe probably trying to make a connection with Kelsey's talk. So actually, these GNN networks that you show, they seem to be actually very good at predicting or kind of getting a good model of the motion of this object that you showed, right? And I was wondering, like, did you try to use this like to predict human motion, like maybe actually from videos or something like that? Like,
we have not, but certainly other people have done work like that. The biggest challenge for that is actually extracting something that looks like a graph from a video, right? Because the graph network models operate on graphs. So a big question for both the physics stuff that I was showing, as well as what you're talking about with representing human bodies, is how do you go from an image to a graph? And people have worked on that for human pose estimation, like quite a bit, to make skeletons of how humans move. And as Anka was alluding to, I think there's a lot of promise in unsupervised 3D representations with things like NERFs and others that might allow us to bridge that vision to graph gap. And then we could use graph nets that do generalize super well for some of these problems. So I think it's an exciting direction. Yeah.
Yeah, that's right. Because I mean, I've seen some works in terms of like scene segmentation, and they do use some hierarchical structure behind, right, to actually express the relationship between objects, and maybe if we have humans, there is some work to do there. Right?
Yeah, totally.
Okay, thank you. That's it. So yeah, sure, go ahead.
This is for Deepak. So in your work, you use YouTube to get a sort of driver for behavior and also, I guess, the goal for each task. And then you have this practice phase. Do you have any ideas on what to do with data collected in different practice phases for different tasks? Is there a sort of shared thing that you can learn in a sort of foundation model that you do?
Yeah, so this is the what I'm currently working on. So these all the results are very recent. Like this last paper is just got submitted, so we have not even released it. But this is the next part. Now can I use this data across all these CMU kitchens, whatever, and then put them into a single thing, and then. But yeah, this is what we are currently exploring, and yeah, I don't have any concrete answer, but. Yeah, still investigating this.
Any further question from the audience? Comments?
I have one for Deepak. Oh, go ahead.
I can ask you a question on that. So you're kind of arguing, you're kind of saying that the medical gazer of humans struggles from outcome, right? Somehow the learning objective of the human does not. You know, I just wonder, where is that coming from? Doesn't you have the same problem there?
Yeah, so very good. I didn't get a chance to talk about this at all in the talk. It depends a ton on how do you decide to represent the reward space. And you know, one thing I'll say is, of course, the intuition behind why learning the reward and then passing it through, you know, computing Q value functions out of that, it seems to be more robust is usually because the policy is a more complex beast in many, but not all environments than the reward function. All right. So the policy or the value function are this interesting result of taking the reward function through all these dynamic programming exercises that mesh it with the dynamics of the environment. And so it's usually a much more complex beast. And another reason to be hopeful about rewards that I like a lot is that, and really the only place where reward learning has actually been successful in terms of generalizing is really when we know a lot about the features that are important to people, which in some tasks we do. And we don't know the features that are important to their policy. Like we know what matters to them, but like for driving, you know, it's a little bit like that. But the reality is we don't know anything. And if you know, all this stuff, even like adversarial IRL, definitely Gale, model-based, like all of this stuff that's really imitation learning that we kind of think of as IRL, but it's really just imitation learning. It's like robustified imitation learning with RL. You can't really use the reward function that comes out of that as a reward function. It does not generalize at all. If you change the dynamics, you're screwed. For the most part. I mean, you know, except like in ARL, they make some particular assumptions where like, well, it's really state-based and then blah, blah, blah. So there's, you know, maybe that goes the furthest, but even that is incredibly brittle if you really use it as a reward function in other domains. So the reality, it's a very good question. It's a very deep question. The reality is that if you don't assume anything about the reward function and you treat it as a high capacity model that can really express any arbitrary mappings of state action to reward, then you're exactly back to square one.
Question about the policy distribution. Like, how does it work when, as you're going out and updating your policy distribution? Is there such a case where the human can act out of distribution, and if so, how does it most update its next distribution, right? Or how robust it is to human acting out of distribution?
I see. So if I take a human who is, say, optimal most of the time, and just there's like this weird thing that they do once, does that throw it off? And the reason this is hard to answer is because again, with completely arbitrary policies, if you keep a distribution over that, all that you can really capture is, if you think about it, is in the same state, they will know you take the same action again. So from that perspective, they're not at all thrown off by this. They'll just say, well, your policy is the thing that did this, and there's a particular state that do this weird thing. And, I'm going to assume that that's basically what you're going to do next time you're in that same state. The promise of Boltzmann policy distributions, I think, comes that we haven't really materialized, and like really overcooked. That's what you saw. Like it's really just out of almost any transfer across states you get out of just like plain neural network ability to interpolate. Like that's all that's going on there. I think there's an interesting thing about Boltzmann policy distributions of actually figuring out this, across different states, that you have some propensity, and then how you represent state is really important. In our work so far, it's been just whatever, a representation emerged out of like throwing the raw state into the neural network. Okay.
Wonder how you compare it to Google DC or other offline CoRL based algorithms, because they're kind of known to be able to somehow kind of filter out like scopable or improperly better applications. So you have any insights about it?
Yeah, so let me poke a little bit back at to see what you're asking. With filter BC and offline RL, you got a bunch of combination of good and bad demonstrations, or pieces of good with offline RL, pieces of good demonstrations, but not in the same episode and stuff like that. And the idea is now when you condition on good reward, you can extract really good behavior. This is the opposite of what you try to do with human models, because remember, what we're using this for is to model the human so that the robot knows what to do in interaction with the human. So I don't want to make that more optimal. I know how to make it more optimal. I just do self-play, but guess what? That is a terrible model of human behavior, and it makes for really optimal robots. It's an amazing model of human behavior in zero-sum games like AlphaGo, right? Because in zero-sum games, if you assume that the person is more optimal than they are, you only stand to benefit. In collaboration, it's the opposite. You train against an optimal person, and then at runtime, the person does something suboptimal. You're relying on the optimal action to get reward, and now you get screwed by that, right? So that's what's really a bad idea, to assume optimality. Yeah, so our problem is not how do we get more optimal out of this. I kind of assume that we can do RL, we can do like all this good stuff on the robot side. On the human side, you can think of the human as being part of the transition function, right? That you don't know and you have to learn about. I want to get an accurate, robust model of that I can actually run RL against, because that RL is going to take that model off of distribution and expose also like, what about this state? And that's where these assumptions get you, especially the optimality assumption is going to really like draw RL to like, oh yeah, let me go here where I think the person is optimal because we make such a good team, you know? And so like, then you go off of distribution because of that. It's really weird, but yeah. Does that make sense now? Yeah.
So I did have another question, maybe for both of you, actually. Like, so in both works, you guys like exploited in some way inductive bias from humans. So in the case of Deepak's talk, you use a bunch of videos from humans, and probably we can see like in the other part of the spectrum, you actually liberalize like a mathematical model, this Boltzmann model. And I was wondering, like, what's the dirty laundry that we didn't see in that process of including this inductive bias in your work? So maybe you both can tell us a little bit about that.
Yeah, I think dirty laundry in our case, what the question was asked just now, like, how do you absorb all this into a single thing? Like dirty laundry was already in the video when the robot is practicing in that phase. It fails miserably multiple times. But in that environment, after it has practiced, it can do things. And generalization is a little bit because we're not training on giant. We're not distilled this into a single model yet. So to truly generalize, I think that's where we'll see more of dirty laundry. But here in these examples, so far, robot is trying to figure out a task in the real world. So dirty laundry part is in the training, but once it trains, it's like a 80-90% accuracy, and then 10% time the hand slips or something happens, like hardware problem. Yeah, but I think this dirty laundry part will come when we are distilling this whole thing into a single piece, and we go to a completely new task which we have not seen anything, no practice. Yeah. Now what can you do in those situations? In Anka's case,
yeah, I mean, our dirty laundry is that it's all wrong. So Boltzmann is wrong. Boltzmann policy distributions. Think about, so I mentioned the assisted perception paper in the last question I answered. So think about a situation where the reason people act the way they do is because they misestimate state. So they have perceptual biases. Not only do they not know where they are, they don't see stuff in the right way, or they don't absorb all the information. Sort of, they don't apply Bayes' rule correctly to figure out how to manage their state belief over time. And now, so let's assume that that's what actually is going on in the human brain for a second, or part of what's going on. And think about papering over that with a Boltzmann policy distribution. The right thing to do is to model the person as having false beliefs and understand and make predictions based on that. Boltzmann policy distribution is going to, once you've seen, the person take that action, that state, right? As though you don't know why that's happening. And the moment you don't know why that's happening, you're not going to generalize properly to other states. Like, it's really a way to capture, it's the main way to fix, like, I'm in the exact same state or a very similar state. Let me not assume that all of a sudden the person will do something completely drastically different from what they've done. That's what it fixes. And it turns out to have a huge effect in some tasks, which surprised me, right? It's a very simple change. So I like it from that perspective, but I mean, it still doesn't actually solve the problem, which is, how the heck the human, like, it's not the causal model for human behavior. And as long as it's not the causal model, it won't generalize.
So in the really cool video with the you put on the model of the sheet and the walk across it, I assume that you like did some, like, did you actually train on that kind of a surface?
No, so those were like both the weight throwing and this one were out of distribution. It's hard to define what is truly out of distribution, but they were out of the ranges. Like there was no throwing of weight and all this. I think over there, what was really happening is that the robot has not seen all possible terrains, but it has probably covered a good span of space of how it can fall through this procedural way. So this was really an hindsight realization for me personally. Initially, when we began this project 3 years ago, we were like, oh, we'll simulate every possible terrain out there. I contacted this DARPA program manager where they scan all terrains in US and trying to import that but in the end, turns out none of this matters. Like as long as you can get the failures some other way, like failing on a steep incline like this is similar to failing when somebody slides below your feet. Now, this insight may not transfer all the time to every scenario. Like in manipulation, there is much more diversity. So that's where you need more priors, etc. But I think this was what basically saved us in locomotion, that it learned how to fall in all possible ways. And I did not go into the method, but method actively queries for situations where you will fail in training time. So it tries to find where you fail, and from that failure, it learns the right thing. So this is how it adapts. And I did not go into this, but this is what is here.
We did that in RMA.
Yeah, so the second phase was more like this dagger phase scenario. So the adaptation module corrects, regress to this Z variable, and then policy uses it to act. And then we use the same data to train the model. So it's a bad data in the beginning.
So it's a dagger
Yeah,
thing.
yeah. So the,
But it's not mining for failure. It's more like rolling out the current thing, seeing where it fails, and then feeding that back in.
yeah, it's just mining in the sense wherever you will fail. Yeah, so it's not actively mining, but in the beginning it just fails everywhere.
Yeah.
So you basically see lots and lots of failures, and you train on that data. So you don't train data from phase 1 where you had good data.
Yeah.
So you train on the bad data. So it's not actively mining, but it is seeing a lot more bad data.
I thought you were doing some really fancy thing with like trying to do adversarial.
Yeah, so we also tried that, but it turns out that in supervised learning, so the second phase is supervised learning. So it's really good in supervised learning because we know how to do it well. And it's simulator. So whether it's 100K examples or 500K, it does not hurt us as much because it's very fast, Isaac, Jim, and all this. But so it did not help, but maybe in more complex tasks that may help. Like in the manipulation case, we actively search for it because it's curiosity-based thing.
Mm-hmm.
So it actively searches for it.
The source, like adversarial attack.
No, not adversarial attack. It's more like dagger. So wherever you fail, you use those examples to. So it's dagger not for action regression. It's dagger for this latent space adaptation.
So this is the way our community has come to refer to any process when you pull out your policy and do something to account for that data.
Yeah. So it's, in that sense, it's dagger. So, but nobody would call it dagger otherwise. So, but yeah, you're totally right.
Any other question, guys?
I have one question for Anka, if you have time. So you mentioned a lot of places this generalization in human models. At a meta level, is it truly feasible to have a human model that can generalize across tasks? Like, do you think, is it at which point will human models like am I suboptimal in similar ways across tasks, or so how feasible is this as a problem statement at the end?
I don't want generalization across tasks. I just want to put a plate on a counter and have the thing not barf. It's not that tall.
So how far, how far can you push it? Like how do you constrain this? Because this is, I think about a lot, as in what do I call something out of distribution? Like the question you asked, like it's hard to define. Like if I train on 1 to 4 is 5 auto distribution, 6 auto distribution, 7 or 100 auto distribution. Like and similar problem occurs in humans as well.
Yeah.
Okay. There's a layer that I haven't talked about at all, which is while getting the models to be more and more robust, which I'm excited about, there's also the notion of, at the end of the day, the model is only important through what it makes the robot do or not do, right? Because what we use it for is to get the robot to act. And so what you really care about is, does the robot in an out of distribution setting, it doesn't matter what the model predicts as long as the robot does something reasonable. And so that's the ultimate goal, is for the robot to do something reasonable, to not be tricked up by that model. So for instance, this parallel stuff that we looked at, like Andrea Baikshi has looked at with Jaime and co have looked at, can I detect online that my model is wrong, right? And and enable the robot to take a more conservative response. And maybe that's okay. It's not going to be the best response that you would get to a model that's great, right? In that new state. But, it's sort of this two-pronged approach of like, get the model to be better and better and better so that you go into the 99999 or whatever. And then as long as you push that far out enough, it's acceptable for the robot to, only be able to sort of detect that something is busted and basically increase its entropy over predictions, and therefore be like, okay, I don't know what's going on, so I'm going to do something that sort of works regardless of what the person does. As long as that happens very rarely, that becomes acceptable. Depending on your product, your use case, right? Where that bar is very different. But I think it has to be two-pronged. You can't just say, I'm gonna come up with the because you would literally have to download the person's brain to be able to have the actual causal model. So that's it.
All right, so I guess in the interest of time, thank you, Anka, Deepak. We really appreciate also everyone that stayed until now.
And thanks for organizing this.
Yeah, thank you. Thank you.